41 light-years from Earth, there's a world where rocks don't just melt, they vaporize. Where the surface glows brighter than molten steel. Where an entire year passes in less time than it takes you to sleep through the night. This is 55 Cancri, and according to everything we thought we knew about planetary science, it shouldn't have an atmosphere. It shouldn't be able to hold on to gases at all. Yet somehow, against every prediction, it does. The discovery announced in May 2024 changed the game completely. Let's start with something that sounds impossible. Imagine a planet twice the size of Earth, but 8 times heavier. Now place it so close to its star that it completes an orbit in just 17.7 hours. The planet's surface temperature reaches 3,770 Kelvin on the side facing the star. That's 6,330 degrees Fahrenheit. Hot enough to turn silicon, iron, aluminum, and calcium into vapor. The night side, perpetually locked in darkness, still glows at temperatures exceeding 2,000 degrees Fahrenheit. This isn't science fiction. This is 55 Cancri, officially named Janssen, and it represents one of the most extreme environments ever confirmed to exist. The planet orbits a Sun-like star designated 55 Cancri A, located in the constellation Cancer. When astronomers first detected it using data from 2003 and 2004, they had no idea what they'd found. At the time of its announcement in 2004, Janssen became the first super-Earth ever discovered around a main sequence star. Nothing in our solar system prepared us for this. We have rocky planets like Earth and Mars. We have gas giants like Jupiter and Saturn. But we have nothing that bridges the gap quite like this, a world that defies our categories and challenges our models of how planets form and survive. The numbers tell a story of extremes that push physics to its limits. Janssen orbits at just 1.4 million miles from its host star. To put that in perspective, Mercury, the closest planet to our Sun, orbits at roughly 36 million miles. Janssen is 25 times closer to its star than Mercury is to ours. At this distance, the gravitational forces and radiation levels would absolutely devastate any world in our solar system. What happens to a planet in such proximity? It becomes tidally locked. One hemisphere eternally faces the star, baking under relentless radiation. The other faces the void of space, never seeing direct starlight. This creates a planetary environment unlike anything we experience on Earth, a world split between fire and relative cold, though even that cold side maintains temperatures that would instantly incinerate any known form of life. Early observations using the Spitzer Space Telescope between June and July of 2013 revealed something strange. The hottest spot on the planet wasn't where it should be. On a tidally locked world with no atmosphere, you'd expect the point directly facing the star, the substellar point, to be the hottest location. But measurements showed the peak temperature shifted 30 to 41 degrees eastward from where physics said it should be. Something was moving heat around. But what? Scientists initially proposed 2 possibilities. Either the planet had an atmosphere capable of redistributing thermal energy through winds, or something else entirely was at work, perhaps exotic rotational dynamics or internal heat transport through the planet's presumed magma ocean. For years, the debate remained unresolved. Spitzer's instruments, though revolutionary for their time, couldn't provide the spectral resolution needed to definitively answer the question. Then came the James Webb Space Telescope. Between its near-infrared camera and mid-infrared instrument, Webb possessed capabilities that transformed exoplanet science. In observations that each lasted about 8 hours, the telescope measured subtle changes in infrared light as Janssen orbited its star. The technique, called secondary eclipse spectroscopy, works by capturing the combined light of the star and planet, then subtracting out the star's light alone when the planet passes behind it. What remains is the planet's own thermal emission, its heat signature, carrying information about atmospheric composition encoded in specific wavelengths. The precision required for these measurements is staggering. Jansen's thermal emission is utterly dwarfed by the brightness of its host star. Isolating that faint planetary signal demands not just sensitive instruments, but sophisticated data analysis techniques that can tease apart overlapping spectral features. Multiple observations were necessary to build sufficient signal-to-noise ratios and check for consistency. When the team analyzed the data, they found patterns that shouldn't exist. Between 4 and 5 microns in the infrared spectrum, less light reached the telescope than expected. This dip, this absorption feature, pointed to something specific: molecules in the planet's atmosphere absorbing those particular wavelengths. The spectral signature matched carbon dioxide or carbon monoxide. Not vaporized rock, which would show a completely different pattern, but actual volatile gases. The kind of atmosphere you'd associate with volcanic outgassing, not a bare molten surface. This was the moment everything changed. For decades, atmospheric scientists operated under a firm assumption: rocky planets orbiting this close to their stars simply cannot maintain atmospheres. The physics seemed straightforward. Intense stellar radiation should strip away gases through atmospheric escape, where high-energy photons give molecules enough kinetic energy to overcome the planet's gravity and flee into space. At Jansen's orbital distance, this process should be devastating and continuous. Yet here was evidence, the strongest to date, that a rocky exoplanet beyond our solar system possesses a genuine atmosphere. Not rock vapor. Not a tenuous envelope of evaporated minerals. An actual secondary atmosphere, likely rich in carbon-bearing molecules, persisting despite conditions that should obliterate it. The discovery paper, published in Nature in May 2024, was unequivocal. The measurements ruled out the hypothesis that Jansen is simply a lava world shrouded in vaporized rock. Instead, the data indicated what researchers call the bona fide volatile atmosphere, one that's continuously replenished by outgassing from below. This is where the magma ocean hypothesis enters the picture. Scientists believe Jansen's interior remains so hot that vast portions of its mantle exist in a molten state. Temperatures and pressures keep enormous quantities of rock liquefied. As this magma ocean churns through convection, driven by the extreme temperature gradient between day and night hemispheres, dissolved gases bubble up and escape through volcanic activity. Think of it like champagne releasing carbon dioxide, but on a planetary scale with molten rock instead of wine. The outgassing rate apparently matches or exceeds the rate of atmospheric loss to space, creating a dynamic equilibrium. Gases escape. More gases bubble up. The atmosphere persists not because it's stable, but because it's continuously renewed, a planetary system maintaining itself against impossible odds through sheer volcanic vigor. Renyu Hu, a planetary scientist at the California Institute of Technology, pointed out something profound about this discovery. By observing this extrasolar example of atmosphere-magma interaction, we gain insights into how the early solar system worked. Earth itself, during the first 100 million years after formation, would have been hot enough to maintain widespread magma oceans. Venus likely experienced similar conditions. Mars too. Studying Jansen gives us a window into processes that shaped our own world billions of years ago, except we're watching them unfold in real time rather than trying to reconstruct them from ancient geological records. The implications extend far beyond one peculiar planet. If rocky worlds can maintain atmospheres under such extreme conditions, what does that mean for our understanding of planetary habitability? What does it tell us about the diversity of rocky planet evolution? The conventional wisdom just took a serious hit, and scientists are racing to understand the mechanisms that make this possible. But there's more to this story. The controversy surrounding Jansen's very existence reveals how challenging exoplanet science can be, and how easily initial observations can mislead us. When astronomers first analyzed the radial velocity data that revealed Jansen's presence, they thought they'd found a planet with a 2.8-day orbital period. This measurement stood for years, shaping early models of the 55 Cancri system. Then in 2005, researcher Jack Wisdom questioned the planet's existence entirely, suggesting the signal was an alias, a false pattern created by the way the data was sampled. The debate intensified. Some analyses seemed to confirm the 2.8-day planet. Others cast doubt. Finally, in 2010, researchers Dawson and Fabrici demonstrated conclusively that the true orbital period was 0.7365 days. Not 2.8 days. Less than 18 hours. The planet was real, but it was far closer to its star than anyone had imagined. This correction wasn't just a minor adjustment. It fundamentally transformed our understanding of Jansen's environment, moving it from merely very close to extraordinarily close, from extreme to apocalyptic. When the planet's transit across its host star was finally observed and confirmed in April 2011 using the MOST Space Telescope, it vindicated Dawson and Fabrici's work and opened the door to direct characterization of the planet's properties. Transit observations are crucial because they let astronomers measure a planet's radius directly by watching how much starlight it blocks. Combined with mass measurements from radial velocity data, this enables calculation of density, a fundamental clue about internal composition. For Jansen, the density measurements revealed a world unlike anything in our solar system, setting the stage for decades of follow-up observations that would culminate in the James Webb Space Telescope's groundbreaking atmospheric detection. Now we understand that Jansen represents something extraordinary, a natural laboratory where planetary science meets its most extreme test case. The discovery of its atmosphere forces us to reconsider fundamental assumptions about what's possible in the universe. And the story of how we came to understand this world reveals the messy, contentious, ultimately triumphant process of scientific discovery itself. What we're learning is that the universe doesn't care about our assumptions. It will create worlds we never imagined, operating under conditions we thought impossible. Jansen is just the beginning. The temperature measurements tell a story that defies intuition. Jansen's dayside reaches 3700 Kelvin according to the latest Spitzer data reanalysis from 2022. That's 6300 degrees Fahrenheit. Hot enough to vaporize calcium. Silicon boils at these temperatures. Iron exists as vapor, not metal. We're not talking about a place where rocks melt, we're describing conditions where the distinction between solid, liquid, and gas becomes almost meaningless for materials we think of as permanent. The night side presents its own puzzle. Even though this hemisphere never sees direct starlight, it maintains temperatures around 1400 Kelvin. That's 2000 degrees Fahrenheit. Glowing red-hot in perpetual darkness. Something is redistributing heat across this world with remarkable efficiency, and for years scientists couldn't agree on what that something was. Here's where things get genuinely strange. When the Spitzer Space Telescope mapped Jansen's thermal emissions between June and July 2013, astronomers expected the hottest spot to align with the substellar point, the location directly facing the star. Basic physics suggested that's where maximum heating should occur. Instead, they found the temperature peak offset by 30 to 41 degrees eastward. 30 degrees doesn't sound dramatic until you realize what it implies. That offset means heat is being transported across the planet's surface through some active mechanism. Atmospheric winds could explain this. But so could more exotic phenomena involving the planet's rotation or internal dynamics. The offset is too large to dismiss as measurement error, yet too consistent to be random variation. Think about what this redistribution requires. You need energy transport powerful enough to shift the thermal maximum across hundreds of kilometers of surface. On Earth, our atmosphere and oceans accomplish this through convection and circulation patterns. But Jansen's environment is so extreme that conventional atmospheric models struggle to explain how gases could survive long enough to establish stable circulation. The debate raged for years. One camp argued the planet must have an atmosphere despite the hostile conditions. How else could you explain the heat distribution? The offset hotspot, the surprisingly moderate night-side temperatures. Another group countered that we were simply seeing vaporized rock, a tenuous shroud of silicon, iron, aluminum, and calcium boiled directly off the surface. At Jansen's temperatures, rocks don't just melt. They evaporate. This rock vapor could create something atmosphere-like without being a true secondary atmosphere. Distinguishing between these scenarios became crucial. A rock vapor envelope would form from the planet's own surface material, constantly replenished as long as temperatures stayed extreme. It's not really an atmosphere in the traditional sense, more like the haze above a boiling pot. A true secondary atmosphere would require ongoing volcanic outgassing from the interior, implying active geological processes in a fundamentally different planetary state. The Spitzer observations provided tantalizing clues but lacked the spectral resolution to definitively settle the question. Infrared brightness measurements showed patterns inconsistent with a bare rock surface, suggesting some kind of gaseous envelope. Yet the data couldn't identify specific molecular signatures that would prove the presence of volatile compounds like carbon dioxide or carbon monoxide. Scientists needed better instruments. They needed precision spectroscopy capable of detecting absorption features from specific molecules. They needed observations that could distinguish between the spectral signature of vaporized rock elements and actual atmospheric gases. Enter the James Webb Space Telescope. Webb's near-infrared camera and mid-infrared instrument can measure thermal emission spectra with unprecedented detail. The observing strategy was elegant. Watch Jansen complete multiple orbits, capturing data when the planet is visible beside its star and when it disappears behind the star during secondary eclipse. During eclipse, you're seeing only starlight. Before and after eclipse, you're seeing starlight plus the planet's own thermal glow. Subtract one from the other, and you isolate the planet's emission spectrum. Each observation session lasted about 8 hours, covering nearly half of Jansen's 17.7-hour orbital period. The precision required is extraordinary. The planet's thermal emission is utterly dwarfed by the star's brightness, like trying to detect a candle next to a searchlight. Multiple observations were necessary to build sufficient signal-to-noise ratio and verify consistency across different orbital phases. When the team analyzed Webb's NIRCan data in 2024, they saw something unmistakable. A dip in the spectrum between 4 and 5 microns. Less light reaching the telescope at these specific wavelengths. This wasn't random noise or instrumental artifact. This was absorption. Something in the planet's atmosphere was absorbing infrared light at wavelengths characteristic of carbon-bearing molecules. Aaron Bello from JPL explained the significance. That spectral dip suggests carbon monoxide or carbon dioxide, both of which absorb strongly in this wavelength range. The MIRI data extending from 5 to 12 microns confirmed the pattern. This wasn't vaporized rock. Silicon, iron, aluminum, and calcium would produce completely different spectral signatures. What Webb detected pointed unambiguously toward volatile compounds, gases you'd expect from volcanic emissions, not from evaporated surface material. The implications hit immediately. Jansen has a bona fide atmosphere. Not rock vapor. Not a temporary artifact of extreme heating. An actual secondary atmosphere, likely rich in carbon dioxide or carbon monoxide, probably both. Gases that had to come from somewhere, that had to be continuously replenished against the relentless stripping force of stellar radiation. This shouldn't work. Conventional planetary science said rocky planets this close to their stars couldn't maintain atmospheres. The radiation environment is too hostile. High-energy photons should give atmospheric molecules enough kinetic energy to escape the planet's gravity entirely. Atmospheric escape should strip away any gases within geologically short timescales. Yet here's Jansen, maintaining an atmosphere despite conditions that should make retention impossible. The answer lies beneath the surface. Renyu Hu from Caltech explained the likely mechanism. The atmosphere isn't primordial, it's a secondary atmosphere, constantly regenerated by outgassing from a magma ocean. Imagine the entire planetary mantle in a molten state. Temperatures and pressures high enough to keep vast quantities of rock liquid. As this magma churns and convects, dissolved gases bubble out, similar to carbon dioxide escaping from champagne. This outgassing process creates a dynamic equilibrium. Yes, the stellar wind strips atmosphere away. But volcanic emissions from the magma ocean replenish it at rates matching or exceeding the loss. It's not a stable atmosphere in the sense of Earth's, it's a constantly refreshed envelope of gas maintained by ongoing geological activity. The magma ocean model explains multiple observations simultaneously. The heat redistribution. Convection in the molten mantle transports thermal energy. The offset hotspot. Preferential outgassing on the dayside creates atmospheric circulation patterns. The nightside warmth. Heat from the interior prevents complete cooling even in permanent darkness. Computer simulations of Jansen's interior dynamics reveal fascinating complexity. Using surface temperature contrasts as boundary conditions, researchers modeled two-dimensional mantle convection under different climate scenarios. If the dayside hosts a full magma ocean while the nightside remains solid or only partially molten, large superplumes form on the day hemisphere. Hot material rises in massive upwellings. Cold material descends on the nightside, though without forming strong downwelling structures. In some simulations, the superplume shifts tens of degrees toward the terminator, the boundary between day and night. This asymmetric convection could drive preferential outgassing on one hemisphere, potentially creating atmospheric composition gradients between dayside and nightside. Different gases on different hemispheres. Chemical stratification driven by the extreme temperature gradient. What makes this discovery genuinely revolutionary isn't just confirming the atmosphere's existence. It's demonstrating that our understanding of planetary atmospheres was too narrow. We built theories based on solar system examples: Earth, Venus, Mars, the gas giants. None of those worlds experience conditions remotely like Jansen's. We assumed extrapolation would work. The universe just proved otherwise. Diana Dragomir from the University of New Mexico, who contributed to discovering Jansen's transits during her doctoral work, emphasized the broader implications. This challenges fundamental assumptions about what's possible. If rocky planets can maintain atmospheres under such punishment, what does that mean for planetary habitability elsewhere? What does it reveal about the diversity of rocky planet evolution? The magma ocean mechanism opens new questions. How common are lava worlds in the galaxy? Do other ultra-hot rocky planets maintain similar atmospheres? Could there be a whole class of worlds we've completely overlooked because we assumed atmospheric retention was impossible under extreme stellar radiation? Jansen gives us a window into processes that shaped Earth billions of years ago. Our planet spent its first 100 million years hot enough to maintain widespread magma oceans. Venus likely went through similar phases. Mars too. But we can't observe those ancient conditions directly, we're stuck reconstructing them from geological traces. Jansen lets us watch in real time, studying atmosphere-magma interactions as they happen rather than inferring them from billion-year-old rocks. The implications extend beyond theoretical interest in planetary science. Understanding how rocky planets retain atmospheres under extreme radiation could reshape our approach to finding habitable worlds. Current habitability models focus on moderate environments, Earth-like distances from Sun-like stars. But what if that framework is too conservative? Consider red dwarf stars. They make up roughly 70% of all stars in the galaxy. Most known exoplanets orbit red dwarfs. And red dwarfs present a problem: their habitable zones, where liquid water could exist, sit uncomfortably close to the star. Close enough that stellar flares and radiation would seemingly strip away atmospheres. Conventional wisdom suggested rocky planets around red dwarfs couldn't maintain the atmospheric protection necessary for life. Jansen changes that calculation. If a world can hold on to an atmosphere while orbiting at 1/25th Mercury's distance from a Sun-like star, while enduring temperatures that vaporize rock, then maybe our assumptions about red dwarf habitability need revision. The mechanisms keeping Jansen's atmosphere intact might operate elsewhere. Different scales, different temperatures, but the same fundamental principle: continuous replenishment overcoming atmospheric loss. This doesn't make Jansen habitable. Nothing lives at 3,700 Kelvin. But it proves atmospheric retention works under conditions we thought impossible. And that matters when searching for life beyond Earth. The detection methods used for Jansen also demonstrate how far exoplanet characterization has advanced. Webb's instruments measured infrared light in the 4 to 12 micron range. Each 8-hour observation captured nearly half the planet's orbital period. The planet completes a full orbit in under 18 hours. That rapid orbit initially seemed like a disadvantage, less time for detailed observation. But it actually helps. Multiple orbits can be observed in a single observing session, allowing astronomers to build up signal strength and check for consistency. The secondary eclipse method Webb employed is deceptively simple in concept. Measure the combined light from star and planet. Wait until the planet passes behind the star. Measure just the star. Subtract. What remains is the planet's thermal emission. Simple in theory. Extraordinarily difficult in practice. The planet's contribution to total system brightness is minuscule. Like trying to detect a candle next to a searchlight from 41 light-years away. And not just detect it, measure its color spectrum precisely enough to identify specific molecules. Aaron Belorra from JPL pointed out the telltale signature, a dip in the spectrum between 4 and 5 microns. That's where carbon monoxide and carbon dioxide absorb infrared light. If the planet were surrounded by vaporized rock, silicon and iron compounds would create completely different absorption features. The spectrum doesn't match rock vapor. It matches volatile gases. This distinction matters because it confirms the magma ocean model over alternatives. Some researchers have proposed that Jansen might be a bare rock world with a thin envelope of evaporated surface material. Under that scenario, the planet would essentially be sweating rock vapor. Silicon, iron, aluminum, the elements that make up planetary crust, would evaporate from the day side and circulate before condensing on the night side. That could explain some observations but struggled to account for the heat redistribution patterns and the stability of the thermal emission over time. The volatile atmosphere model fits better. Carbon dioxide or carbon monoxide released from interior outgassing creates a genuine atmosphere, not just surface evaporation. This atmosphere can transport heat through winds and circulation patterns. It can maintain relatively stable composition despite continuous loss to space because volcanic activity keeps replenishing it. And it explains why the planet's thermal emission shows less variability than expected for a bare rock surface. But questions remain. The atmosphere's exact composition remains uncertain. Is it primarily carbon dioxide? Carbon monoxide? Some mixture? Do other gases contribute significantly? Nitrogen, sulfur compounds, even water vapor from the magma ocean? Webb's current observations can't fully resolve this. Future observations with longer integration times and coverage of additional wavelengths could narrow the possibilities. The planet's internal structure also invites speculation. Standard rocky planet models don't apply straightforwardly. At the temperatures and pressures inside Janssen, rock doesn't behave like rock on Earth. Phase diagrams, the charts showing which states of matter exist under different conditions, become exotic at these extremes. Materials that normally form solid minerals might exist as superionic phases, where some atoms remain locked in crystal lattices while others flow freely like liquids. Bizarre states of matter that laboratories can barely reproduce. Some research suggests Janssen might have a carbon-rich composition rather than the silicon and oxygen-dominated chemistry of Earth-like planets. The host star, 55 Cancri A, shows elevated carbon abundance in its spectrum. If the protoplanetary disk that formed the system was similarly carbon-rich, planets might have incorporated more carbon than typical solar system bodies. Under the extreme pressures in Janssen's interior, that carbon could crystallize into diamond. This sparked the diamond planet hypothesis, the idea that Janssen's mantle might contain diamond layers hundreds of kilometers thick. It's a tantalizing possibility. The temperatures and pressures are certainly sufficient. Pure carbon at those conditions would form diamond. Whether Janssen actually contains enough carbon, and whether it's distributed in ways that allow large-scale diamond formation, remains speculative. But the chemistry isn't impossible. Density measurements provide some constraints. Janssen is roughly 8 times Earth's mass and twice Earth's radius. That gives a density of about 7 grams per cubic centimeter, higher than Earth's average density of 5.5 grams per cubic centimeter. Higher density suggests either more iron in the core or a compressed structure from the planet's gravity. Or both. It doesn't definitively prove or disprove the diamond hypothesis, but it's consistent with various compositional models. The planet's thermal variability adds another layer of mystery. Observations show the planet's brightness changes over time, not just the expected variations as it orbits, but longer-term fluctuations that suggest surface conditions aren't static. One explanation invokes massive volcanic eruptions. Picture Mount St. Helens scaled up by factors of thousands. Eruptions violent enough to inject vast dust clouds into the atmosphere, temporarily blocking thermal emission and changing the planet's apparent brightness. When the dust settles or gets swept away by atmospheric winds, brightness returns to baseline. Alternatively, the variability might come from a gas torus co-orbiting with the planet. Similar to Jupiter's Io plasma torus, a donut-shaped cloud of charged particles surrounding Jupiter in Io's orbit. Io's intense volcanic activity feeds this torus. If Janssen experiences similarly vigorous outgassing, it could create a surrounding cloud of material that periodically obscures or enhances the planet's thermal signature as viewed from Earth. Both explanations require extreme levels of geological activity. But Janssen is extreme in every measurable way, so neither scenario seems implausible. Scientists have also searched for electromagnetic interactions between Janssen and its host star. The planet orbits so close that it sits deep within the star's magnetic field. Jupiter's moon Io creates a magnetic footprint on Jupiter through electromagnetic coupling. Charged particles from Io's volcanoes interact with Jupiter's magnetic field, generating radio emissions. Similar interactions might occur between Janssen and 55 Cancri. Radio observations in 2011 looked for these signals. Nothing detected. Either the interactions don't occur at detectable strength, or the observation methods weren't sensitive enough. The null result also suggests Janssen might lack a strong intrinsic magnetic field. Earth's magnetic field is generated by convection in its liquid iron core. Janssen's interior temperatures might prevent the kind of convection needed for dynamo action. Or perhaps the magma ocean itself disrupts magnetic field generation. Without a protective magnetosphere, atmospheric loss to stellar wind should be even more severe. Yet the atmosphere persists. That persistence keeps circling back as the central puzzle. Everything about Janssen's environment should doom any atmosphere. The stellar radiation. The lack of magnetic protection. The intense gravitational forces from tidal locking. The evaporation driven by surface temperatures exceeding 3000 Kelvin. Yet there it is, carbon-bearing gases surrounding a world that shouldn't have them. The magma ocean mechanism explains how, but raises its own questions. How deep is the magma ocean? Does it cover the entire planet or just the day side? What's the composition of the molten material? Is it similar to Earth's mantle composition, or something more exotic? How efficiently does convection operate under these extreme conditions? And most intriguingly, does the night side have fundamentally different conditions that might create chemical gradients in the atmosphere? That last question touches on something particularly fascinating about tidally locked worlds. The permanent day and night hemispheres create environments so different they might as well be separate planets. One side continuously blasted by stellar radiation. The other side in eternal darkness. The atmospheric dynamics between these two faces would be extraordinary. If an atmosphere exists, and we now know it does, winds must connect the hemispheres. Heat from the day side gets transported toward the night side through atmospheric circulation. But how efficiently? That depends on wind speeds, atmospheric density, and the atmosphere's chemical makeup. Computer models of tidally locked planets suggest wind patterns unlike anything on Earth. Instead of the Coriolis-driven circulation cells we're familiar with, tidally locked worlds develop what's called a superrotating jet, a continuous high-altitude wind stream that flows eastward around the planet at tremendous speed. This jet would redistribute heat, carrying energy from the scorching day side toward the cooler night side. On Janssen, these winds might reach hundreds or even thousands of meters per second. Hypersonic winds sculpting temperature gradients that would be lethal in either direction. Standing on the day side would be like facing a blast furnace. Standing on the night side would still be hot enough to melt lead, but relatively speaking, comparatively mild. The terminator, the boundary between day and night, becomes the most interesting region. Here, conditions transition from one extreme to another. Temperature gradients drive powerful convection. Rising air from the day side meets descending air from the night side. Turbulence would be constant and violent. If life were ever to exist on such a world, and it can't on Janssen, but theoretically on cooler tidally locked planets, the terminator would be the only survivable zone. Not too hot, not too cold. Though on Janssen, even the Terminator remains far above the boiling point of water. Computer simulations of Janssen's interior reveal mantle dynamics that would reshape our understanding of planetary geology. The extreme temperature difference between hemispheres creates asymmetric convection patterns. Hot magma rises on the day side, forming massive plumes. These aren't small volcanic features, they're continent-sized upwellings of molten rock pushing toward the surface. On the night side, cooler material descends. Though cooler is relative, it's still thousands of degrees. These descending flows complete the convection cell, driving circulation through the planet's mantle. The entire planet becomes a heat engine, powered by the temperature differential its tidal locking creates. The dayside plumes can shift position. In some models, they migrate tens of degrees toward the Terminator. This movement would create varying volcanic activity across the dayside, with hotspots appearing and disappearing over time. If volcanic outgassing is concentrated in these plume regions, atmospheric composition might vary geographically. The atmosphere near the strongest plume would be richer in freshly outgassed volatiles. Regions away from active plumes would have older, more processed atmospheric chemistry. This brings up something fascinating about Janssen's atmosphere. It's not static, it's being constantly renewed. Every second, stellar radiation strips away gases on the dayside. High-energy photons and stellar wind particles collide with atmospheric molecules, giving them enough velocity to escape Janssen's gravity. The atmosphere bleeds into space continuously, yet it persists. The magma ocean replenishes what's lost. Dissolved gases in the molten rock bubble to the surface through volcanic vents. The same process that created Earth's early atmosphere 4 billion years ago continues on Janssen today. It's a dynamic equilibrium, loss balanced by supply. Remove either factor and the atmosphere would either grow indefinitely or disappear completely. This equilibrium is delicate. Small changes in volcanic activity or stellar radiation could tip the balance. If volcanic outgassing slows, atmospheric loss would gradually thin the atmosphere. If stellar activity increases during a flare, temporary atmospheric stripping could occur before volcanic replenishment catches up. The atmosphere's composition reflects this balance. Carbon dioxide and carbon monoxide dominate because they're stable enough to survive in this environment and abundant in volcanic emissions. Other gases present in smaller quantities might include sulfur dioxide, water vapor, and various rock-derived species. But the carbon-bearing molecules dominate the spectral signature web detected. Water deserves special attention. Earth's magma contains dissolved water that outgasses during eruptions. Janssen's magma ocean likely contains water too. But at dayside surface temperatures, water can't exist as liquid. It would immediately vaporize. Even on the night side, temperatures remain too high for liquid water. Any water in Janssen's atmosphere exists as superheated steam. This steam contributes to the greenhouse effect. Water vapor is an excellent absorber of infrared radiation. Even in small quantities, it would trap heat, contributing to the night side surprisingly high temperatures. The night side doesn't cool as much as bare rock calculations would suggest, partly because atmospheric circulation brings heat from the dayside, and partly because greenhouse gases trap what little heat remains. The vertical structure of Janssen's atmosphere adds another layer of complexity. Near the surface, the atmosphere is dense and hot. Pressure increases with depth into the magma ocean until there's no clear boundary between atmosphere and planet, just a gradual transition from gas to liquid to solid as you descend. Higher up, the atmosphere thins. Temperature remains high due to stellar radiation, but pressure drops. At some altitude, the atmosphere becomes thin enough that molecules can escape to space. This exosphere marks the fuzzy edge of Jansen's atmosphere, where the planet ends and space begins. Comparing Jansen to early Earth reveals profound connections. When Earth formed 4.5 billion years ago, the entire surface was molten. Impacts during planetary formation delivered enough energy to melt rock globally. The early Earth was a magma ocean world, probably tidally locked to the moon before tidal forces gradually slowed Earth's rotation. During this period, Earth's atmosphere came from volcanic outgassing. Carbon dioxide, water vapor, nitrogen, and other volcanic gases accumulated. The atmosphere was thick, hot, and utterly hostile to modern life. But it was the starting point for everything that followed. As Earth cooled, the magma ocean solidified. Water vapor condensed into oceans. Chemistry became more complex. Studying Jansen gives us a laboratory for understanding that crucial phase. We can't travel back 4 billion years, but we can observe a world currently in a state Earth once occupied. The processes happening on Jansen right now happened on Earth long ago. Magma ocean dynamics. Atmospheric outgassing. The balance between atmospheric creation and loss. Venus offers another comparison. Modern Venus has a crushing carbon dioxide atmosphere that creates a runaway greenhouse effect. Surface temperatures reach 750 Kelvin. But early Venus, like early Earth, was likely covered by magma oceans. Venus's atmosphere today is a product of billions of years of evolution, outgassing, atmospheric loss, and chemical reactions that eventually created the hellscape we observe now. Jansen represents an arrested state. Its proximity to its star prevents cooling. The magma ocean never solidifies. The planet remains locked in the early phase that Earth and Venus passed through. It's a living fossil of planetary evolution, preserved by extreme conditions that prevent further development. Mars provides a contrasting example. Mars once had a thicker atmosphere, probably sustained by volcanic activity. But Mars is small. Its interior cooled relatively quickly. Volcanic activity slowed and eventually stopped. Without replenishment, atmospheric loss gradually stripped away most of Mars's atmosphere. Solar wind and lack of a protective magnetic field accelerated the process. Jansen's size, 8 Earth masses, means its interior remains hot through radioactive decay and tidal heating. Volcanic activity will continue for billions of years. Unlike Mars, Jansen won't cool enough for atmospheric loss to win. The magma ocean persists, and with it, the atmospheric replenishment mechanism. These comparisons highlight how planetary outcomes depend on multiple factors. Size determines how long internal heat lasts. Distance from the star determines surface temperature and atmospheric loss rates. Rotation state affects heat distribution. Magnetic fields protect atmospheres from stellar wind. Chemical composition influences what gases are available for outgassing. Change any of these variables and you get a different world. Put Jansen farther from its star and it becomes a super-Earth with a solid surface and potentially habitable conditions. Shrink it to Mars size and it cools quickly, losing its atmosphere despite volcanic activity. Remove the magma ocean and the atmosphere disappears within thousands of years. Jansen occupies a precise point in this parameter space where extreme conditions create an unlikely equilibrium. The planet is large enough to stay geologically active, close enough to its star to maintain surface melting, tidally locked in a way that creates extreme hemispheric differences. And it has exactly the right composition to supply carbon-bearing gases through outgassing. Shift any factor slightly and Janssen would be something else entirely. It sits on a knife's edge between multiple possible states, maintained by the exact conditions it experiences. That precarious balance makes it scientifically invaluable. Understanding why Janssen's atmosphere survives teaches us about the boundaries of planetary habitability and the conditions necessary for atmospheres to persist. But there's something else Janssen reveals, something about the diversity of planetary outcomes in the universe. Before exoplanet discoveries began in the 1990s, our only examples were solar system worlds. We assumed other planetary systems would look similar. Rocky planets close to their stars. Gas giants farther out. Ice worlds at the edges. Janssen shatters that assumption. Super-Earths don't exist in our solar system. Tidally locked lava worlds weren't predicted by planetary formation models. The idea that a rocky planet could maintain an atmosphere while orbiting so close to its star contradicted theoretical expectations. Yet here it is. Real. Observed. Challenging us to expand our understanding of what planets can be. Every exoplanet discovery expands the catalog of known worlds, but some discoveries do more. They force us to reconsider fundamental assumptions about how planetary systems work. Janssen belongs to this second category. The 55 Cancri system contains multiple planets. Janssen orbits closest to the star, completing its circuit in less than 18 hours. Farther out are other worlds, Galileo, Brahe, Harriet, each occupying different orbital distances and exhibiting different characteristics. The system also includes a companion red dwarf star, 55 Cancri b, which hosts its own planets. This makes 55 Cancri one of the most populated planetary systems known outside our own. The architecture differs dramatically from our solar system. We have small rocky planets near the Sun, gas giants in the middle regions, and ice worlds at the outer edges. A clear pattern emerged from millions of years of gravitational sorting. 55 Cancri follows different rules. A super-Earth orbits where no planet should survive. Gas giants occupy unexpected positions. The whole arrangement challenges formation models based on solar system observations. Janssen's host star, 55 Cancri a, is a K-type star slightly cooler and smaller than our Sun. It's classified as Copernicus in the system's naming scheme, which honors historical astronomers and telescope pioneers. The star sits 41 light-years away in the constellation Cancer. Close enough that we can study it in detail. Far enough that we'll never visit. The star's composition matters for understanding Janssen. Spectroscopic analysis shows 55 Cancri a is relatively rich in heavy elements, particularly carbon. This chemical signature suggests the protoplanetary disk that formed the system contained higher proportions of carbon compounds than the disk that formed our solar system. That excess carbon might explain some of Janssen's unusual properties, including the diamond planet hypothesis. Several years ago, researchers proposed that Janssen might contain vast quantities of crystallized carbon in its interior. The idea emerged from density calculations and the star's carbon-rich composition. If true, Janssen's mantle could contain diamond layers hundreds of kilometers thick. Pressures and temperatures at those depths would force carbon into its densest crystalline form. The planet would literally be made partially of diamond. The hypothesis captured public imagination. Media reports dubbed it the Diamond Planet. But the reality is more complex and less certain. Recent observations suggest the magma ocean model better explains Janssen's observed properties. A diamond-rich interior remains possible but hasn't been confirmed. The planet's true composition likely lies somewhere between pure diamond and pure silicate rock, with carbon playing a significant but not dominant role. What we know for certain is that Jansen's discovery path was messy. The planet was first detected using radial velocity measurements, which tracked the star's subtle motion caused by orbiting planets. Early analysis suggested a planet with a 2.8-day orbital period. For several years, astronomers accepted this interpretation. Then Jack Wisdom reanalyzed the data in 2005. He argued the 2.8-day signal was an alias, a mathematical artifact created by combining the true orbital period with the observing schedule. He suggested the real period might be different. Other researchers published analyses supporting the 2.8-day planet. The debate continued. In 2010, Rebecca Dawson and Daniel Fabrici solved the puzzle. They demonstrated conclusively that the true orbital period was 0.7365 days, less than 18 hours. The 2.8-day signal was indeed an alias. This correction fundamentally changed our understanding of the planet. It moved Jansen from very close to extraordinarily close. The difference matters enormously when considering surface conditions and atmospheric survival. The transit discovery in 2011 confirmed the corrected orbital period. The MOST Space Telescope monitored 55 Cancri continuously for 2 weeks, capturing multiple transits exactly when Dawson and Fabrici's analysis predicted. Transit observations measure a planet's size by recording how much starlight it blocks. Combined with mass from radial velocity, this gives density. Density reveals composition. Jansen's density indicates it's rocky, not gaseous. But the exact internal structure remains debated. Is there a diamond layer? How thick is the magma ocean? Does a solid core exist beneath the molten mantle? These questions await better data. Temperature measurements added another layer of mystery. Spitzer Space Telescope observations in 2013 mapped Jansen's thermal emission using infrared light. The results showed something unexpected. The hottest point on the planet's day side was offset from the substellar point, the location directly facing the star. Instead of maximum temperature at the center of the day side, the hottest spot was shifted about 30 to 40 degrees eastward. Why? Something must be transporting heat across the surface. On a tidally locked world with no atmosphere, the hottest point should be directly under the star. The offset indicates active heat redistribution. Atmospheric winds could explain it. But at the time, scientists weren't sure Jansen had an atmosphere. Another possibility involved the planet's rotation. Tidal locking isn't always perfect. Some planets maintain slight rotational drift, which could shift the hottest spot. Or perhaps internal convection creates asymmetric heat flow that affects surface temperatures. The puzzle deepened when observations showed temporal variability. Jansen's thermal emission changed between different observing sessions. Sometimes it appeared brighter, sometimes dimmer. The variations were too large to be measurement noise. Something on or around the planet was changing. One explanation involves massive volcanic eruptions. If Jansen experiences supervolcanism, eruptions that dwarf anything on Earth, they could inject enormous dust clouds into the atmosphere. These clouds would temporarily block thermal emission, making the planet appear cooler. As the dust settled or dispersed, brightness would return to normal. Repeated eruptions would create the observed variability. Another hypothesis suggests a gas torus co-orbiting with Jansen. Picture a donut-shaped cloud of material surrounding the planet's orbit. Similar structures exist in our solar system. Jupiter's moon Io produces a plasma torus from its volcanic emissions. If Janssen continuously vents gas from its surface, some might remain in orbit around the star, creating a variable cloud that occasionally obscures the planet. These mysteries motivated the James Webb Space Telescope observations. Webb's unprecedented sensitivity and spectral resolution offered a chance to settle fundamental questions. Does Janssen have a real atmosphere? What is it made of? How does it survive? The observing campaign required meticulous planning. Webb observed the system from multiple complete orbits. Each observation lasted about 8 hours, nearly half of Janssen's orbital period. The telescope captured infrared light from the system both when the planet was visible beside the star and when it passed behind the star during secondary eclipse. Secondary eclipse occurs when the planet moves behind the star from our perspective. During eclipse, we see only starlight. Before and after eclipse, we see the combined light from both star and planet. Subtracting the eclipse measurement from the combined measurement isolates the planet's thermal emission. This technique is called secondary eclipse spectroscopy. The precision required is extraordinary. Janssen's thermal emission is thousands of times fainter than the star. Measuring it means detecting a tiny brightness change against an overwhelming background. Webb's instruments, NIRCam and MIRI, work at different infrared wavelengths. NIRCam covers 4 to 5 microns. MIRI extends from 5 to 12 microns. Together they provide a continuous spectrum showing how much light the planet emits at each wavelength. That spectrum reveals composition. Different molecules absorb and emit light at characteristic wavelengths. Carbon dioxide has a distinctive absorption feature around 4 to 5 microns. Carbon monoxide shows different patterns. Vaporized rock elements like silicon and iron would create yet another spectral signature. When the team analyzed Webb's data, they saw clear evidence for carbon-bearing gases. The spectrum showed reduced brightness between 4 and 5 microns, exactly where carbon dioxide and carbon monoxide absorb light. The signature didn't match vaporized rock. It matched volatile gases. This was the breakthrough. After years of debate, Webb provided definitive evidence that Janssen has a real atmosphere composed of actual gases, not just rock vapor. The atmosphere is likely dominated by carbon dioxide or carbon monoxide, probably both. These gases are continuously supplied by volcanic outgassing from the magma ocean below. The discovery settles one question but raises others. How thick is this atmosphere? How does its pressure compare to Earth's or Venus's? Does composition vary between dayside and nightside? Are there other gases present in smaller quantities? What about clouds or haze? Some answers will come from additional Webb observations. Others require different techniques. Future missions might directly image the planet, separating its light from the stars without relying on eclipses. Spectroscopy at higher resolution could detect trace gases and measure isotope ratios, revealing details about the atmosphere's chemistry and evolution. But the fundamental mystery is solved. Janssen has an atmosphere against all expectations. It survives in conditions that should strip it away within thousands of years. The magma ocean continuously replenishes lost gases, maintaining equilibrium between outgassing and escape. This mechanism allows the atmosphere to persist for billions of years despite hostile conditions. The implications extend far beyond one planet. If atmospheres can survive on worlds as extreme as Janssen, where else might they persist? What about planets slightly farther from their stars, where conditions are less hostile? Could super-Earths in intermediate environments maintain thick atmospheres for geological timescales? What does this mean for habitability across the galaxy? The discovery opens doors to understanding atmospheric evolution across the galaxy. Rocky planets exist in every configuration imaginable. Some orbit close like Janssen. Others circle at comfortable distances. Many fall somewhere between. Each environment tests different survival mechanisms. Janssen proves that extreme proximity doesn't automatically mean atmospheric death. The magma ocean mechanism works. It maintains equilibrium between loss and replenishment. But does this mechanism scale? Could slightly cooler worlds with less volcanic activity still maintain atmospheres through similar processes? What about planets around different types of stars? Red dwarfs are smaller and cooler than our Sun, but they emit powerful stellar flares that could strip atmospheres more efficiently than steady radiation. Do magma ocean planets around red dwarfs survive or succumb? These questions matter because red dwarfs make up roughly 70% of all stars in the galaxy. If their planets can't maintain atmospheres, that dramatically narrows the search for habitable worlds. Conversely, if Janssen's mechanism works around red dwarfs too, billions of additional worlds might retain atmospheres despite hostile conditions. The connection to Earth's past runs deeper than surface similarities. 4 billion years ago, our planet was a hellscape. Continuous asteroid bombardment kept the surface molten. The atmosphere was thick with carbon dioxide, water vapor, and other volcanic gases. No oxygen existed. No ozone layer protected the surface from radiation. Life had not yet emerged, or if it had, it clung to the most extreme refuges imaginable. That early Earth resembled Janssen in many ways. Not in temperature, Earth was cooler. But in the fundamental process of atmosphere formation through volcanic outgassing from a magma-covered world. Studying Janssen lets us observe this process happening now, 41 light-years away, rather than trying to reconstruct it from geological clues billions of years old. The insights apply to Venus too. Our sister planet may have started with oceans and a temperate climate. Runaway greenhouse warming turned it into an inferno with surface temperatures exceeding 860 degrees Fahrenheit. Venus today has a crushing carbon dioxide atmosphere 90 times thicker than Earth's. That atmosphere likely formed through volcanic outgassing, similar to the mechanism sustaining Janssen. Understanding how magma ocean worlds generate and maintain atmospheres helps explain Venus's transformation. It might even reveal whether Venus could have remained habitable if certain conditions had been different. Mars presents a contrasting case. The red planet once had a thicker atmosphere and liquid water on its surface. Rivers carved channels. Lakes filled impact craters. The atmosphere was dense enough to support a water cycle. Then Mars lost most of its atmosphere to space. Without a strong magnetic field to deflect the solar wind, atmospheric gases were gradually stripped away over hundreds of millions of years. Today Mars has only a thin carbon dioxide atmosphere, about 1% the density of Earth's. Janssen's survival mechanism, continuous volcanic replenishment, is precisely what Mars lacked. Once Martian volcanism declined, the atmosphere couldn't be replenished fast enough to compensate for losses. The planet dried out and froze. Comparing these worlds reveals the delicate balance required for atmospheric persistence. Too little volcanic activity means gradual loss. Too much stellar radiation accelerates escape. A magnetic field helps but isn't always necessary if replenishment rates are high enough. Janssen demonstrates that extreme volcanism can compensate for extreme radiation, maintaining atmosphere despite lacking magnetic protection. The search for habitable worlds depends on understanding these boundaries. The habitable zone around a star is traditionally defined as the region where liquid water can exist on a planet's surface. Too close and water boils away. Too far and it freezes. But habitability requires more than temperature. It demands atmospheric stability over geological timescales. A planet in a habitable zone means nothing if it can't hold on to its atmosphere. Jansen teaches us that atmosphere retention is complex. It's not just about distance from the star or planetary mass. Volcanic activity, stellar radiation, magnetic fields, and internal heat all interact. Some planets in the habitable zone might lose their atmospheres. Others outside it might keep theirs through vigorous outgassing. The traditional habitable zone concept may be too simplistic. We need a more nuanced understanding that accounts for atmospheric dynamics, not just surface temperature. Future observations will refine our knowledge of Jansen's atmosphere. Webb can observe the planet again, measuring how its spectrum changes over time. Variability would indicate weather patterns, volcanic events, or atmospheric circulation. Long-term monitoring could reveal seasonal changes if the planet's orbit is slightly elliptical, though current evidence suggests it's nearly circular. Other instruments could contribute different perspectives. Radio telescopes might detect emissions from atmospheric chemistry. Optical telescopes could measure reflected starlight, revealing cloud properties or atmospheric hazes. Each observation adds another piece to the puzzle. The goal is building a complete atmospheric model: temperature structure, pressure profile, chemical composition, circulation patterns. That model would be the first comprehensive picture of a rocky exoplanet atmosphere. Beyond Jansen, dozens of other rocky exoplanets await similar scrutiny. Many orbit closer to their stars than Mercury does to our Sun. Some are larger than Earth but smaller than Neptune, occupying a size range with no solar system equivalent. These super-Earths and mini-Neptunes are common in the galaxy, yet we understand them poorly because we lack local examples. Do they have atmospheres? What are those atmospheres made of? How thick are they? Can they support liquid water despite high temperatures? Jansen provides a template for answering these questions. The techniques developed to study it, secondary eclipse spectroscopy, thermal phase curves, long-term monitoring, apply to other worlds. Each new observation expands our catalog of atmospheric types. Rocky planets with hydrogen atmospheres. Worlds with water vapor envelopes. Planets surrounded by carbon monoxide. The diversity is likely enormous, limited only by the laws of chemistry and physics. The technology enabling these discoveries barely existed a decade ago. Webb launched in late 2021. Its predecessors, Hubble, Spitzer, Kepler, laid groundwork but lacked the sensitivity and spectral resolution for rocky planet atmospheres. Webb's mirror is nearly 3 times wider than Hubble's, collecting much more light. Its infrared instruments operate at wavelengths ideal for thermal emission spectroscopy. And its position at the second Lagrange point, 1 million miles from Earth, provides a stable environment free from atmospheric interference. These advantages combine to make observations like Jansen's possible. Without Webb, we'd still be debating whether rocky exoplanet atmospheres could be detected at all. Now we know they can. The question shifts from whether to how many and what types. Next-generation instruments will push further. Ground-based telescopes with adaptive optics systems that compensate for atmospheric distortion are reaching unprecedented precision. Space missions under development target rocky planets specifically. Some will use star shades, giant structures flying separately from telescopes to block starlight, making planets visible. Others will employ coronagraphs, internal masks that achieve similar blocking. These techniques enable direct imaging rather than relying on transits or eclipses. Direct imaging reveals more detail, including atmospheric composition, cloud patterns, and surface features if resolution permits. The ultimate goal is finding another Earth. A rocky planet in a habitable zone with an atmosphere containing oxygen, water vapor, and other biosignatures. Life as we know it requires liquid water and produces oxygen through photosynthesis. Detecting both in an exoplanet atmosphere would strongly suggest biology. Janssen isn't that world. It's too hot, too hostile, too extreme. But every planet we study teaches us something about planetary diversity and atmospheric resilience. Janssen proves that atmospheres can survive in conditions once thought impossible. That expands the parameter space where we might find habitable worlds. If atmospheres persist around planets as extreme as Janssen, they might exist in many environments we haven't fully considered. The galaxy may be richer in atmospheric diversity than we imagined, with implications for where life might arise and endure. Standing back, the Janssen story reflects humanity's expanding vision. 40 years ago, we didn't know whether planets existed around other stars. The first exoplanet discovery came in 1992, orbiting a pulsar. The first around a Sun-like star came in 1995. Now we know thousands of exoplanets, with more discovered every year. We've progressed from merely finding planets to characterizing their masses, sizes, orbits, and now atmospheres. Each advance reveals the universe in greater detail. Janssen represents the cutting edge of this progression, a world so alien yet so important for understanding how planets work. Its magma oceans, carbon-rich atmosphere, and extreme temperatures challenge our assumptions and expand our knowledge. In 41 years, light from Janssen reaches Earth, carrying information about a world that shouldn't exist by old rules but does by new understanding. That light, captured by our most sophisticated instruments, tells a story of resilience, complexity, and the endless capacity of nature to surprise us. The Janssen discovery arrives at a turning point in our understanding of what planets can be. For centuries, we built theories from 8 local examples. Mercury through Neptune. A handful of moons. 1 asteroid belt. Limited data breeding limited imagination. Then exoplanets shattered those constraints, revealing worlds that defy every category we'd constructed. Hot Jupiters orbiting closer than Mercury. Super-Earths with no solar system equivalent. Planets around binary stars, around pulsars, in configurations our models never predicted. Janssen sits at the extreme end of this spectrum. A world where rock boils, where atmospheres persist through mechanisms we're only beginning to grasp, where every measurement contradicts what textbooks said was possible. It's not just another data point. It's a fundamental challenge to planetary science orthodoxy. The implications ripple outward in unexpected directions. Consider the habitable zone concept. We've spent decades refining estimates of where liquid water can exist around different stellar types. But if atmospheric retention depends on volcanic vigor as much as stellar distance, those calculations need revision. A planet outside the habitable zone might maintain temperate surface conditions through internal heat and thick atmosphere. One inside might lose its air despite comfortable temperatures. Janssen proves the old boundaries were too rigid. Atmospheres survive where theory said they couldn't. Magma oceans sustain themselves for billions of years through tidal heating. Carbon dioxide and carbon monoxide circulate in environments hot enough to vaporize iron. The universe operates by different rules than we assumed, and each discovery reveals another layer of complexity we've missed. The technological achievement deserves recognition too. Webb's instruments detected molecular absorption features in thermal emission from a rocky planet smaller than Neptune, orbiting a Sun-like star 41 light-years away. The planet's contribution to total system brightness is infinitesimal. Yet Webb teased apart that faint signal, measured it across multiple wavelengths, and identified specific chemicals in an alien atmosphere. 20 years ago, this would have seemed impossible. 10 years ago, it was theoretical. Now it's routine. That progress accelerates. Webb will observe more rocky exoplanets, building a catalog of atmospheric types. Ground telescopes with 30-meter mirrors are under construction, capable of even finer measurements. Space missions in planning stages will directly image Earth-sized worlds around nearby stars. Within the next decade or two, we'll have spectroscopic data from dozens of rocky planets across a range of environments. Janssen is the first clear detection, but it won't be the last. Each atmosphere tells a story about planetary evolution. How did this world form? What was its early environment? Has its atmosphere changed over time? Is volcanic activity increasing or declining? These questions connect to the broader narrative of how planetary systems develop from protoplanetary disks into mature configurations. Janssen's carbon-rich atmosphere might reflect the unusual composition of its parent disk. Other planets will show different chemistries, revealing different formation histories. The connection to Earth's past grows stronger as we learn more. Our planet spent hundreds of millions of years as a magma ocean world. That phase determined what atmosphere we started with, which influenced how the surface eventually solidified and cooled. Water vapor condensing into oceans. Carbon dioxide dissolving into seawater. Nitrogen accumulating because it's chemically inert. These processes set the stage for everything that followed, including the emergence of life. We can't observe Earth 4 billion years ago. Those rocks are gone, subducted or eroded beyond recognition. But we can observe Janssen now, watching processes that mirror Earth's infancy. The magma ocean convection. The volcanic outgassing. The atmospheric chemistry under extreme conditions. It's a living laboratory for planetary formation, preserved by circumstances that prevent it from moving to the next evolutionary stage. Venus offers another parallel. The runaway greenhouse effect that created its hellish surface may have started from conditions similar to early Earth. Small differences in initial water content, volcanic activity, or atmospheric composition could determine whether a planet becomes habitable Earth or scorched Venus. Understanding how atmospheres form and persist on magma ocean worlds helps identify which factors matter most. That knowledge applies to every rocky planet in every system. Mars shows the opposite extreme. A world that lost its atmosphere because volcanic replenishment couldn't match escape rates. Janssen demonstrates that vigorous outgassing can maintain atmosphere despite extreme radiation. Mars lacked that vigor. Its smaller size meant faster interior cooling. Volcanism declined. The atmosphere thinned. Today we see the end result, a frozen desert with only wisps of air remaining. These comparisons reveal that atmospheric evolution isn't deterministic. Similar planets can follow divergent paths depending on subtle variations in initial conditions and subsequent history. Some retain thick atmospheres for billions of years. Others lose them within hundreds of millions. The galaxy likely contains examples of every intermediate state, each frozen at a different point in the progression from formation to final configuration. Finding habitable worlds requires understanding these pathways. We need to identify which planets can maintain atmospheres long enough for life to emerge and evolve. That means looking beyond simple temperature calculations. Volcanic activity matters. Stellar radiation matters. Planetary mass and composition matter. Magnetic fields help but aren't always necessary. The interactions between these factors create outcomes we're only beginning to map. Jansen expands that map into territory we previously marked as impossible. Atmospheres in extreme radiation environments. Magma ocean worlds maintaining volatile envelopes through continuous outgassing. Carbon-bearing gases surviving at temperatures that vaporize rock. Each observation adds nuance to our understanding of what's possible, pushing the boundaries of known atmospheric physics. The search continues with renewed purpose. Thousands of exoplanets await detailed characterization. Many are rocky. Many orbit in or near habitable zones. Some may harbor atmospheres with biosignatures, oxygen, methane, combinations of gases that suggest biological activity. Finding those signatures requires the techniques pioneered on worlds like Jansen. Secondary eclipse spectroscopy. Thermal phase curves. Long-term monitoring for variability. Future discoveries will surprise us. They always do. Each planet studied reveals unexpected features, challenges assumptions, forces theoretical revisions. Jansen challenged the assumption that rocky planets this close to their stars can't have atmospheres. What will the next discovery challenge? Perhaps we'll find atmospheric oxygen on a lifeless world, produced through non-biological chemistry. Or detect complex organic molecules in places we thought too extreme for chemistry to occur. Or discover that magnetic fields play different roles than we believed. The universe doesn't care what we think is possible. It operates according to physical laws, and those laws permit configurations we haven't imagined yet. Our job is observation, measurement, analysis. Build instruments sensitive enough to detect faint signals. Develop techniques clever enough to extract information from noise. Construct models flexible enough to accommodate new data without breaking. Jansen succeeds because it exists in a narrow parameter space where multiple extreme conditions align. Large enough to stay geologically active. Close enough to maintain surface melting. Tidally locked to create hemispheric extremes. Compositionally suited to supply carbon gases through outgassing. Change any variable and you get a different outcome. But in this exact configuration, the result is a magma ocean world with a carbon-rich atmosphere surviving against impossible odds. That survival teaches humility. Our theories predicted atmospheric loss would dominate. They were wrong. Nature found a mechanism we'd underestimated: continuous volcanic replenishment maintaining equilibrium with escape processes. The mechanism was there all along, operating on early Earth, on early Venus, on countless worlds across the galaxy. We just needed precise enough observations to confirm it. The James Webb Space Telescope provided those observations. Its infrared capabilities, its spectral resolution, its exquisite sensitivity combined to detect molecular absorption features in a rocky exoplanet atmosphere. The first clear detection of its kind. A milestone in exoplanet science. Proof that we can characterize rocky planet atmospheres despite their faintness and their distance. More milestones await. Direct imaging of Earth-sized worlds. Detection of water vapor on temperate planets. Identification of biosignatures in exoplanet atmospheres. Each achievement builds on previous ones, using techniques refined through observations like Janssen. The progression continues, limited mainly by technology and funding. As instruments improve, so does our ability to study ever more challenging targets. 41 light-years separates us from Janssen. Light traveling at 186,000 miles per second takes 41 years to cross that gulf. The Photons Web detected left Janssen in 1983, carrying information encoded in their wavelengths about a world that defies expectations. Those photons journeyed through interstellar space, arrived at our solar system, and entered Webb's optics to be recorded and analyzed. The information they carried changed our understanding of planetary atmospheres. Not through dramatic revelation, but through precise measurement of subtle spectral features. Science advances through exactly this process. Careful observation, rigorous analysis, gradual accumulation of evidence, occasional surprises that force theoretical revisions. Janssen delivered one of those surprises. A rocky planet with an atmosphere in conditions that shouldn't permit one. The discovery proves that atmospheric science still has fundamental lessons to learn. Our models are incomplete. Our assumptions sometimes wrong. The universe more diverse than our limited sample suggested. That diversity is what makes exoplanet science compelling. Every world is an experiment in planetary physics. Different initial conditions. Different evolutionary paths. Different outcomes. Some produce Earths, temperate, wet, potentially habitable. Others become Venuses, scorched, hostile, shrouded in crushing atmospheres. Still others turn into Mars analogs, cold, dry, stripped of most air. And some become Janssens, extreme, unexpected, challenging everything we thought we knew. The galaxy contains hundreds of billions of stars. Most have planets. Rocky worlds number in the billions. Each one represents a unique combination of formation history, composition, stellar environment, and evolutionary trajectory. We've characterized perhaps a few dozen in detail. The sample is tiny. The lessons preliminary. But each observation adds to our knowledge, building toward comprehensive understanding of how planets work. Janssen's contribution to that understanding is clear. Atmospheres can survive extreme radiation through continuous volcanic replenishment. Magma ocean worlds maintain carbon-rich envelopes despite surface temperatures exceeding 6,000 degrees Fahrenheit. Tidally locked planets redistribute heat through atmospheric circulation even when that atmosphere shouldn't exist according to old theory. These aren't minor details, they're fundamental insights about planetary atmospheric physics. The knowledge applies beyond Janssen. Every ultra-hot rocky planet, every tidally locked world, every planet with active volcanism and strong stellar radiation. The mechanisms we've identified operate wherever similar conditions exist. That means potentially thousands of worlds across the galaxy, each maintaining atmospheres through processes we're only now beginning to understand. Looking forward, the questions multiply faster than answers. How common are magma ocean planets? Do they exist around different stellar types? Can slightly cooler versions maintain atmospheres through similar mechanisms? What about planets with different compositions, more water, less carbon, varying amounts of metals? How do magnetic fields influence atmospheric retention when volcanic activity is vigorous? Do some planets transition from magma ocean states to solid surfaces, and if so, how does that affect their atmospheres? Each question requires observations. More Webb time. Future missions. continued monitoring of known worlds and characterization of newly discovered ones. The work spans decades, involves hundreds of scientists, demands billions in funding. But the payoff is understanding our place in the universe. Learning how common Earth-like worlds are. Discovering whether life exists elsewhere. Finding out if our planet's history is typical or exceptional. Jansen moves us one step closer to those answers. Not through being Earth-like, it's about as far from Earth as a rocky planet can get. But through demonstrating that planets operate under a wider range of conditions than we believed possible. If atmospheres survive at Jansen's orbital distance, they might persist in many environments we'd written off as too hostile. That expands the search space for habitable worlds and increases the odds that we'll eventually find one. The universe is vast. The number of planets staggering. Most will remain forever beyond our ability to study in detail. But the ones we can observe teach us principles that apply to all the others. Physical laws operate the same everywhere. The chemistry of planetary formation follows universal rules. Atmospheric physics doesn't change based on location. So every planet we characterize tells us something about countless others we'll never see. Jansen tells us that nature is more resourceful than our models predicted. That equilibrium can exist between opposing processes even under extreme conditions. That volcanic vigor can maintain atmospheres despite powerful escape mechanisms. These lessons apply to exoplanets we'll discover next year, next decade, next century. They become part of the framework we use to understand all rocky worlds. 41 light-years away, Jansen continues its 18-hour orbit. The magma ocean churns. Volcanic gases bubble to the surface. Stellar radiation strips away atmosphere as fast as outgassing replenishes it. The process has continued for billions of years and will continue for billions more. We've observed it for a few years at most. But those observations revealed something we'd never have predicted from theory alone. A world that shouldn't exist by old rules but does according to new understanding. That's how science progresses, one impossible planet at a time. Right now, 642 light-years away, a star is dying. Not gradually fading over billions of years, but preparing for one of the most violent events the universe can produce. And we're watching it happen in real time. Betelgeuse. The name alone carries weight in astronomy circles. This red supergiant marks the shoulder of Orion, visible to anyone who looks up on a winter night. For thousands of years, it glowed steadily. Then in late 2019, something changed. The star dimmed, dramatically. Astronomers scrambled to their instruments, because they knew what this might mean. A supernova. An explosion so powerful it would briefly outshine every other star in our galaxy combined. Visible during the day, casting shadows at night. A celestial event that happens maybe once per century in a galaxy like ours, and we might be about to witness it. But here's what makes this genuinely unsettling. We have no idea when. Could be tonight. Could be 100,000 years from now. The light we see left Betelgeuse in the 1380s, when the Ming Dynasty was just beginning. If it exploded tomorrow, it actually happened during the Renaissance, and we're only now receiving the news. The star itself is almost incomprehensible in scale. Place it where our Sun sits, and its surface would extend past the orbit of Jupiter. Every second, Betelgeuse burns through mass equivalent to Earth's moon. It's so large that its outer atmosphere is actually cooler than the deeper layers we can detect, creating convection cells the size of our entire solar system. Scientists discovered something else recently. The dimming in 2019 wasn't just a fluke. Betelgeuse had ejected a massive chunk of its own surface into space. A piece of star, flung outward, temporarily blocking our view. The sheer violence required to tear that much material away from a supergiant's gravity suggests internal processes we're only beginning to understand. Stellar physics gives us the framework. Betelgeuse is fusing heavier and heavier elements in its core. Hydrogen is long gone. Helium, exhausted. Now it's burning carbon, oxygen, silicon. Each stage happens faster than the last. Silicon fusion, the final step before catastrophe, takes about 1 day. 1 day between normalcy and detonation. The core contracts under its own gravity. Temperatures spike. Pressures mount. Eventually, even silicon can't hold back the collapse. In less than a second, the core implodes, then rebounds. The shock wave tears through millions of kilometers of stellar material. What took millions of years to build destroys itself in hours. That's the supernova. But the story doesn't end with the explosion. What remains is stranger. The core, compressed beyond anything we experience in everyday physics, becomes either a neutron star or a black hole. In Betelgeuse's case, given its mass, we're likely looking at a black hole. A point in space where gravity is so extreme that not even light escapes. The entire mass of a star, compressed into a region smaller than a city. Meanwhile, the outer layers race outward at roughly 10% the speed of light. This expanding shell carries every element the star forged over its lifetime. Iron, gold, uranium, everything heavier than helium. These materials will eventually seed new star systems, new planets, possibly new life. Every atom in your body heavier than hydrogen was created in a star that died before our sun was born. The supernova remnant becomes a nebula. Glowing debris spreading across light years, enriching the interstellar medium. Within these clouds, gravity begins pulling material together again. The cycle continues. Now consider what this means for us. At 642 light-years, Betelgeuse is close. Not dangerously close, but close enough to matter. When it goes, we'll see effects beyond just a bright light in the sky. The explosion releases more than visible light. Gamma rays, X-rays, ultraviolet radiation, all pour out in the initial burst. Earth's atmosphere will absorb most of this, but satellites might not fare as well. Communication systems could experience disruptions. GPS might lose accuracy. Nothing catastrophic, but noticeable. Then there's the neutrino flux. These ghostly particles barely interact with matter, but a supernova produces them in staggering numbers. Trillions will pass through your body every second for weeks. Detectors worldwide will register the surge, giving astronomers unprecedented data about the explosion's mechanics. The visible brightness is what captures imagination, though. At peak, Betelgeuse will reach apparent magnitude -12, roughly as bright as a half-moon. You'll see it during the day. At night, it'll cast noticeable shadows. For weeks, possibly months, our sky will have two moons, one white, one red. Cultures throughout history have marked supernovae. The 1006 event was recorded on three continents. The 1054 explosion created the Crab Nebula and appeared in Chinese and Middle Eastern texts. Native Americans left pictographs depicting it. These weren't just scientific observations but events that shaped mythology and worldview. What happens to us when Betelgeuse goes? Nothing physically dangerous, but something profound psychologically. We'll have front-row seats to cosmic violence on a scale that makes our largest nuclear weapons look like firecrackers. It'll be a reminder, visible every night, that the universe operates on timescales and energy scales that dwarf human concerns. Astronomers are preparing. Telescopes across every wavelength stand ready. When the light arrives, we'll have perhaps hours of warning from neutrino detectors before the visible light reaches us. Every major observatory will pivot to Orion. This will be the most studied astronomical event in human history. The data will be invaluable. We've never observed a supernova this close with modern instruments. Our models of stellar evolution, nuclear physics, even general relativity, will face their most rigorous test. Whatever we think we know about how massive stars die, Betelgeuse will either confirm it or force us back to the drawing board. There's also the question of what we'll find afterward. The neutron star or black hole left behind will be young, hot, energetic. We might detect pulsar emissions, jets of material shooting from the poles at near light speed. The nebula itself will be a laboratory for studying shock physics, dust formation, and chemical enrichment of space. But I mentioned earlier that the timing is uncertain. Let's dig into why that's so frustrating. Stellar models tell us Betelgeuse is near the end. Its behavior, the dimming events, the mass loss, all point to a star in its final stages. But final stages, for a supergiant, might mean tomorrow or 100,000 years from now. The physics becomes chaotic. Small changes in core conditions produce wildly different outcomes. We're essentially trying to predict the exact moment a Jenga tower falls. We know it's unstable. We can see pieces missing. But that final trigger, the precise instant when structural integrity fails completely, that's incredibly difficult to forecast. The 2019 dimming gave us hope for better predictions. If we could understand what caused it, maybe we could identify pre-supernova signatures. The research that followed revealed the surface ejection, but also showed us how much we still don't know. Betelgeuse is variable on multiple timescales. It pulsates. It sheds mass irregularly. Separating normal variability from end-stage behavior is like diagnosing a patient whose symptoms keep changing. Some astronomers think we're seeing the final centuries. Others argue we might have tens of thousands of years left. The uncertainty stems from how we measure stellar evolution. We can't watch a single star age. We observe millions of stars at different life stages and piece together the sequence. It's like understanding human aging by taking snapshots of random people and arranging them by apparent age. You'll get the general progression right, but predicting any individual's remaining lifespan becomes much harder. Recent observations added another wrinkle. Betelgeuse might have a companion star. If true, the dynamics change completely. Binary interactions can trigger supernovae earlier than expected, or delay them, or create entirely different outcomes. We thought we understood this star, and then realized we might have been looking at a system, not a singleton. The implications stretch beyond academic curiosity. Understanding supernovae helps us understand galactic evolution, element formation, even cosmology. Type Ia supernovae, a different class from what Betelgeuse will produce, serve as distance markers across the universe. They helped us discover that cosmic expansion is accelerating, leading to the concept of dark energy. Getting the physics right matters for our entire picture of how the universe works. And there's something else. Something that connects directly to why this particular star captures our attention beyond the scientific interest. Human timescales collide with cosmic timescales in strange ways. Betelgeuse might explode while you're reading this. Or it might wait until our civilization is dust. From the universe's perspective, there's no difference. A few thousand years either way is a rounding error. But for us, the difference between witnessing this event and having it remain theoretical is everything. We stand at a unique moment. We had the technology to study a nearby supernova in detail, but we lack the ability to predict when it'll happen. Our instruments are ready. Our models are sophisticated. But nature keeps its schedule, indifferent to our preparations. There's a philosophical tension here that's worth examining. We study the universe by observing light that left its source years, centuries, or millennia ago. When we look at Betelgeuse, we're seeing photons that began their journey around 650 years ago, give or take. The star might have already exploded. The shockwave could be racing toward us right now, and we wouldn't know until the light arrives. This isn't speculation. It's the fundamental constraint of information traveling at light speed. We're always looking backward in time. That delay creates an odd psychological state. Astronomers monitoring Betelgeuse know that the supernova they're waiting to observe might have already happened during the Middle Ages. The light carrying that information could arrive next week. Or next century. There's no way to check. No faster-than-light telephone line to call and ask if the star is still there. We wait, instruments ready, knowing that the event we're preparing for might be a historical fact we just haven't learned about yet. Let's shift perspective for a moment. What would it actually look like from Earth? The first indication would come from neutrinos. These ghostly particles barely interact with matter, which means they stream out from the core collapse essentially unimpeded. Neutrino detectors around the world, designed primarily for particle physics research, would register a sudden spike. These facilities are networked specifically for this purpose. When one detector sees an anomalous burst, it alerts the others. If multiple detectors confirm simultaneously, astronomers worldwide get an automated notification. Supernova imminent. Look up. The neutrino warning would give us maybe a few hours head start. Possibly a day. Then the light would arrive. Not gradually. Supernovae brighten dramatically, exponentially. Within hours, Betelgeuse would go from roughly magnitude 0 to potentially magnitude -11 or 12. For context, the full moon sits at magnitude -13. We're talking about a single point of light nearly as bright as the moon, visible in broad daylight. Orion would be unrecognizable. The constellation would have a second sun blazing where the hunter's shoulder used to be. That peak brightness would last weeks, maybe months, then a slow decline over years. But even after fading, Betelgeuse would remain visible to the naked eye for potentially decades. The expanding debris cloud would eventually form a nebula, visible through telescopes for thousands of years. This isn't a brief light show. It's a multi-generational transformation of our night sky. The scientific return would be staggering. Every telescope on Earth and in orbit would immediately swing toward Orion. We'd capture the light curve with unprecedented detail, tracking how brightness changes second by second. Spectroscopy would reveal the composition of ejected material, testing our models of nucleosynthesis. Did the supernova produce the expected ratios of elements? Are there surprises in the chemical signature? X-ray and gamma-ray observations would probe the shock wave physics. Radio telescopes would track the expanding shell as it plows into surrounding material. And then there's the neutrino data itself. These particles carry information about the core collapse that light cannot provide. Light gets trapped, bounced around, delayed by the dense stellar material. Neutrinos escape immediately, carrying direct information about nuclear reactions in the collapsing core. Detecting them in large numbers would let us peer into physics we can't access any other way. The temperature, the density, the exact sequence of nuclear processes, all encoded in the neutrino spectrum and timing. Previous nearby supernovae were observed with far more primitive instruments. Supernova 1987A in the Large Magellanic Cloud, while spectacular, occurred before we had modern detector networks. We caught neutrinos, which was revolutionary, but with limited sensitivity. We got optical observations, but without the resolution and wavelength coverage we have now. Betelgeuse would be the first nearby supernova in the era of space telescopes, gravitational wave detectors, and coordinated global observation networks. The data haul would rewrite textbooks. But there's something else happening alongside the scientific opportunity: cultural impact. Betelgeuse going supernova would be the most dramatic astronomical event in human history, at least in recorded history. The 1006 supernova was brighter, but occurred before the scientific revolution. Ancient observers recorded it with awe but without understanding. The 1054 supernova created the Crab Nebula. Chinese astronomers documented it. Indigenous peoples across the Americas incorporated it into their traditions. But again, no scientific apparatus to study it properly. A supernova in Orion would reach everyone. You can't miss Orion. It's visible from almost everywhere on Earth. Every culture recognizes it. Suddenly, that familiar pattern would change. Children would grow up with a sky that looks different from the one their parents knew. Photographers would capture the light illuminating landscapes. Artists would respond. Writers would find metaphors. The supernova would become part of human culture in ways we can't fully predict. There's precedent for celestial events capturing public imagination, though nothing quite at this scale. Comet Hale-Bopp in 1997 became a cultural phenomenon. People who never looked up started watching the skies. But Hale-Bopp was a visitor, here and gone. Betelgeuse would be a permanent change. The supernova would fade, but the sky would remain altered. We'd live with the consequence, the glowing remnant, for the rest of our species' existence. Now, let's address something often glossed over in popular discussions. Could this actually be dangerous? The short answer is no, but the reasoning matters. Supernovae release tremendous energy, including gamma rays. At close range, within a few dozen light years, a supernova could potentially damage a planet's atmosphere. The gamma rays would interact with atmospheric molecules, creating nitrogen oxides that deplete ozone. Without ozone protection, surface life would face increased ultraviolet radiation from the star. Betelgeuse is too far away for this to be a concern. The inverse square law is brutal. Intensity drops with the square of distance. At 650 light-years, the gamma-ray flux reaching Earth would be negligible. Detectable, certainly. Scientifically valuable, absolutely. But not hazardous. We'd receive more radiation from eating a banana than from Betelgeuse's supernova. This isn't speculation. We can calculate these things precisely. The physics is well understood. Some articles sensationalize this, either through misunderstanding or for clicks. You'll see headlines about killer stars or cosmic threats. It's nonsense. Real astronomers aren't concerned about danger. They're excited about the scientific opportunity. The distinction matters because public misconceptions about astronomy can undermine science communication. We need people to understand that space, while genuinely dangerous in many ways, doesn't threaten us with random nearby supernovae. The galaxy isn't that hostile. What could genuinely affect us is more subtle. The supernova's effect on the solar wind dynamics, perhaps. Earth's magnetosphere protects us from charged particles streaming from the sun. A supernova would add a temporary burst of high-energy particles to the cosmic ray background. Our magnetosphere would handle it, but satellites might experience slightly elevated radiation. Nothing catastrophic. Maybe some temporary communication disruptions. GPS might lose accuracy. ISS would need to monitor exposure levels. Astronauts might need to shelter in more shielded areas during peak flux. Again, manageable. Not apocalyptic. The real challenge would be observation coordination. Every major observatory would want time on every major telescope. Conflicts would arise. Who gets priority? How do you balance spectroscopic observations against photometric monitoring against polarimetry against imaging? Normally, telescope time is allocated months or years in advance through competitive proposals. A supernova would trigger directors' discretionary time at every facility, overriding scheduled observations. Some astronomers would be thrilled. Others, whose carefully planned observations get bumped, less so. There's also the amateur astronomy community to consider. Betelgeuse is bright enough that backyard telescopes could contribute real data. In fact, amateur observations might prove crucial for continuous monitoring. Professional telescopes can't watch one target constantly. They need to split time between multiple objects, multiple projects. Amateurs, coordinating globally, could maintain near-continuous coverage. We saw this work effectively with other transient events. The amateur community has become genuinely valuable for time-domain astronomy. Social media would transform the experience compared to historical supernovae. Real-time updates, images, data, all shared instantly worldwide. Scientists could communicate findings directly to public audiences. Misinformation would also spread rapidly, of course. Distinguishing signal from noise would be challenging. But overall, the transparency would be unprecedented. You'd be able to follow the supernova's evolution as it happens, explained by experts, discussed by millions. Educational impact deserves mention. A visible supernova would provide a teaching moment like no other. Students could observe with their own eyes a phenomenon they'd only read about. Teachers could connect textbook physics to something happening overhead. The abstract becomes concrete kai ban ko the chi te veo no. Bao tung qua ha kasi ze dung kak kuok trian lam. Kak kung thien van se kap not kak bui trin dien qua ho. Su kien nai se trian kam hung cho mot the he kak na thien van hoc. Jong nu chuang trin apollo de trian kam hung cho kak the he na qua hoc va ky su truok day. But we keep circling back to the central frustration. When we have this extraordinary opportunity ahead of us, maybe, or maybe not for 100,000 years. The uncertainty undermines planning. Observatories can't keep resources on standby indefinitely. Research teams can't maintain readiness for decades. Funding agencies want timelines. Yet the universe doesn't provide them. Betelgeuse will explode on its own schedule, indifferent to our preparations or impatience. We've built the instruments. We've developed the theory. We've coordinated the networks. Now we wait. And waiting, in astronomy, often defines the job more than the observations themselves. What we do know is that Betelgeuse isn't behaving like other red supergiants we've studied. Most stars in this phase show relatively predictable brightness variations. Long-period pulsations, yes. But within expected ranges. Betelgeuse keeps surprising us. The great dimming of 2019 to 2020 caught everyone off guard. The star's brightness dropped to around 40% of normal. Some astronomers genuinely wondered if we were watching the prelude to explosion. Spectroscopic analysis eventually revealed the truth. Betelgeuse had ejected material that condensed into dust, temporarily blocking our view. The star itself hadn't actually dimmed that dramatically. We were seeing an obscuration event. But that explanation raises its own questions. Why did Betelgeuse eject that much material at that particular time? Red supergiants lose mass continuously through stellar winds. The rate varies, certainly, but that particular ejection seemed unusually vigorous. Was it a surface convection event? Some models suggest that massive convection cells in red supergiant envelopes can bring hot material to the surface, creating localized bright spots. When those regions rotate out of view, the star appears dimmer. Combine that with dust formation and you get dramatic brightness changes. Except we're not entirely certain that's what happened. Alternative models exist. Maybe the dimming involved magnetic activity. Betelgeuse does have a magnetic field, though measuring it precisely is difficult. Could magnetic loops trap material, then release it suddenly? Solar flares operate on this principle, scaled way down. A stellar version might produce the observed effects. We're speculating, though. The truth is we saw something unprecedented and we're still working out what it meant. This uncertainty pervades supernova prediction. We're trying to forecast an event we've never actually witnessed up close in real time with modern instruments. SN 1987A happened in a large Magellanic Cloud, 168,000 light-years away. Close enough to study extensively, far enough that resolution was limited. Betelgeuse at 550 light-years would give us detail we've never had before. But only if it explodes while we're ready. The waiting game has psychological dimensions worth examining. Astronomers dedicate careers to studying objects that might not do anything interesting during their professional lifetime. You could spend 30 years developing expertise in supernova physics and never witness the one event that would define your field. That's the gamble. Some researchers pivot to other topics, hedging their bets. Others commit fully, accepting that the universe operates on timescales indifferent to human careers. There's nobility in that commitment. Also frustration. Imagine explaining to funding committees why your telescope time should go toward monitoring a star that probably won't explode this year. Or next year. Or the year after that. Competing proposals promise guaranteed results. Yours offers a possibility. Funding agencies generally prefer certainty. Yet Betelgeuse observations continue. Not constantly, but regularly. The star remains on monitoring lists. Photometry gets collected. Spectra get recorded. Data accumulates slowly, building a baseline against which any future changes will be measured. That baseline has value regardless of whether Betelgeuse explodes soon. We're learning about red supergiant behavior in unprecedented detail. The variations, the mass loss, the atmospheric dynamics, all of it contributes to stellar evolution models. When the next red supergiant explodes somewhere else, we'll understand it better because of Betelgeuse. The question of what we'd actually see during the explosion deserves more detailed exploration. The initial brightening would be gradual, probably over hours. Neutrinos would arrive first, traveling essentially at light speed and passing through matter almost without interaction. Neutrino observatories around the world maintain constant vigilance for the characteristic burst signature. They'd detect it before anyone saw anything visually. Minutes to hours later, the shock wave from the core collapse reaches the stellar surface. The star's outer layers begin exploding outward. This is when brightness starts increasing dramatically. Over the course of a day or so, Betelgeuse would brighten from magnitude 0.5 to perhaps magnitude -11 or -12. Roughly the brightness of a half-moon, concentrated in a single point. You could read by it at night. Easily. During the day, it would be visible to the naked eye, a bright star hanging in daylight sky. The color would shift too. Betelgeuse appears reddish now because its surface temperature is relatively cool for a star, around 3,500 Kelvin. During the supernova, the expanding material heats up. The color would shift toward white, maybe even slightly blue. The expanding debris would be glowing from the energy of the explosion itself, not from fusion anymore. Peak brightness would last weeks, maybe a couple months. Then gradual fading over years. But even after fading below naked eye visibility, the supernova remnant would remain a target for telescopes for centuries. The expanding shell of debris, glowing in various wavelengths, would evolve constantly. Radio observations would track the shock wave as it plows through surrounding space. X-ray telescopes would study the hot interior regions. Infrared would pierce any dust that forms. Optical telescopes would monitor the overall structure. Each wavelength reveals different physics. The remnant would become a laboratory for studying extreme conditions we can't replicate on Earth. Nuclear physics, particle acceleration, shock wave dynamics, all happening in real time at scales we can actually resolve. Most supernova remnants we study are ancient, their explosions having occurred thousands of years ago. A fresh one at Betelgeuse's distance would be transformative. Consider the scientific papers that would emerge. Hundreds in the first year alone. Thousands over the following decade. Every subfield of astronomy would find something relevant. Stellar evolution theorists would refine their models of red supergiant death. Galactic chemical evolution researchers would study how the explosion enriches surrounding space with heavy elements. Particle physicists would analyze neutrino data to constrain physics beyond the standard model. Cosmologists would use it to calibrate distance measurements, since Type II supernovae serve as standardizable candles under certain conditions. The interdisciplinary reach would extend beyond astronomy. Geologists would look for isotopic signatures in ice cores or sediment layers, markers of cosmic ray exposure from the supernova. Historians might correlate the event with cultural responses, studying how different societies interpret and record the phenomenon. Artists would create works inspired by it. Musicians might compose pieces. The cultural impact would ripple outward in ways we can't predict. But there's a darker consideration that occasionally surfaces. What if we're wrong about the safety? Not about the distance, that's measured reliably, but about the radiation effects. Current models say we're safe. Models have been wrong before. The ozone layer might be more vulnerable than we think. Or the magnetosphere less protective. Unlikely, yes. Our understanding of these systems is solid. But certainty in science always comes with error bars. The responsible position is acknowledging what we don't know while being clear about what we do. We're confident Earth is safe from catastrophic effects. Confident, not absolutely certain. That distinction matters. Scientists who claim absolute certainty lose credibility when exceptions emerge. Better to be honest about uncertainty while explaining why we consider the risk negligible. Public communication requires that balance. Climate scientists face this challenge constantly. How do you convey high confidence without claiming perfection? How do you acknowledge uncertainty without undermining the message? With Betelgeuse, the stakes are lower because we're not asking anyone to change behavior. No policy decisions hinge on supernova predictions. But the communication challenge remains. Media coverage of Betelgeuse tends toward sensationalism. Headlines scream about stars exploding near Earth, implying danger where none exists. Scientists issue corrections. The cycle repeats. Each brightening fluctuation triggers another round. After a while, public attention drifts. The boy who cried wolf effect takes hold. When the supernova actually happens, will people care? Or will they assume it's another false alarm? Maintaining public interest over uncertain timelines is nearly impossible. The first few times Betelgeuse dims or brightens unusually, media covers it extensively. By the 10th time, it's old news. Editors reject the story. The public assumes nothing real is happening. Then one day, it actually explodes, and everyone's surprised despite decades of warnings. This dynamic frustrates science communicators. How do you keep people informed without exhausting their attention? Some researchers have stopped doing media interviews about Betelgeuse entirely. The questions are always the same. Is it exploding now? When will it explode? What will we see? The answers never satisfy because they involve uncertainty. Journalists want definitive statements. Scientists offer probabilities and caveats. The disconnect is fundamental. Yet when the explosion happens, those same researchers will be flooded with interview requests. Everyone will want expert commentary. The preparation happening now, the monitoring, the theoretical work, the instrument development, all of it will suddenly become urgent and newsworthy. The irony is that the real scientific value lies in the preparation, not the event itself. The supernova will be spectacular, certainly. But the decades of work leading up to it, building our understanding of stellar evolution, developing detection capabilities, training new generations of astronomers, that's where the lasting impact lives. Betelgeuse will eventually teach us something we can't predict. Every major astronomical event does. When gravitational waves were first detected, nobody expected the precision with which we could measure neutron star mergers. The technology worked better than anticipated. The data revealed phenomena theorists hadn't considered. Supernova 1987A taught us about neutrino physics in ways no one foresaw. The neutrino burst arrived hours before the light, exactly as predicted. But the detailed measurements refined our understanding of particle interactions inside collapsing stars. Models improved. New questions emerged. Betelgeuse will do the same, just in different ways. Perhaps we'll discover unexpected asymmetries in the explosion. Maybe the dust production will challenge our models of element formation. The neutrino signal might contain surprises. We won't know until it happens. This uncertainty is what makes the event scientifically valuable. If we could predict everything perfectly, there'd be no point in observing. Science advances through surprises, through data that doesn't quite match expectations. Those mismatches force us to reconsider assumptions, revise theories, build better models. The process is iterative and endless. Consider the stellar evolution models we use. They're sophisticated, incorporating decades of research. But they're still approximations. Real stars are messier than equations suggest. Convection patterns inside Betelgeuse are turbulent and chaotic. Our models smooth them out, treating them statistically. That works for predictions but misses fine details. When Betelgeuse explodes, we'll see whether those details mattered. Did the asymmetric convection create asymmetric explosions? Did rotation play a bigger role than we thought? These questions have answers we can't access until the event occurs. Some researchers are already planning follow-up studies for decades after the supernova. The expanding remnant will be visible for centuries. Its evolution will test our understanding of how supernova remnants interact with surrounding material. Currently, we study old remnants from supernovae that exploded centuries or millennia ago. With Betelgeuse, we'll watch one develop from the beginning. That temporal coverage is rare and valuable. The remnant will sweep up surrounding gas, heating it, compressing it, possibly triggering new star formation. These processes occur in every supernova remnant. But observing them in real time, with modern instruments, will provide unprecedented detail. Computer simulations can be compared directly to observations. Models will improve. Future predictions will become more accurate. There's also the question of what Betelgeuse leaves behind. Supernovae from stars this massive typically produce neutron stars. But some create black holes instead. The boundary between these outcomes isn't perfectly understood. It depends on the star's exact mass, its composition, how much mass it lost before exploding, and details of the collapse process. Current estimates suggest Betelgeuse might be right on that boundary. If it produces a neutron star, we'll have a new pulsar to study. If it forms a black hole, that's equally interesting. Either way, the remnant will teach us about the final moments of massive stellar cores. Neutron stars are extreme physics laboratories. Densities exceed atomic nuclei. Magnetic fields reach unimaginable strengths. Matter behaves in ways we can't reproduce on Earth. Every new neutron star adds to our understanding. Black holes are equally fascinating but harder to study directly. We'd infer its presence through effects on surrounding material. Gas falling toward it would heat up, emitting X-rays. Over time, the black hole might accrete enough material to become visible through those emissions. But that takes years or decades. Immediate detection would rely on gravitational wave observatories. If Betelgeuse's core collapse is asymmetric enough, it might produce detectable gravitational waves. Current detectors probably aren't sensitive enough at that distance. But future observatories might be. LIGO and Virgo are upgrading. New detectors are being built. By the time Betelgeuse explodes, we might have the capability to detect its gravitational wave signature. That would be extraordinary. We've never detected gravitational waves from a supernova. The asymmetry required is substantial. Most supernovae probably don't produce detectable signals. But if Betelgeuse does, it would open an entirely new window into core collapse physics. We'd learn about the exact moment the core fails, how matter falls inward, how the bounce generates the explosion. These are processes hidden inside the star, invisible to traditional telescopes. Gravitational waves carry information directly from the core. They're not blocked by overlying material. This makes them uniquely valuable for studying supernova interiors. Neutrinos serve a similar purpose. They interact so weakly that they escape the collapsing core almost immediately. The neutrino burst from Betelgeuse will arrive before the light, just like with 1987A. But this time, our neutrino detectors are far more sophisticated. IceCube in Antarctica can detect thousands of neutrinos if predictions hold. Super Kamiokande in Japan will see them too. Multiple detectors worldwide will triangulate the signal, pinning down the exact timing and direction. That coordination will happen automatically once the first detector alerts the network. Within seconds, astronomers globally will know Betelgeuse has exploded. They'll point every available telescope at it. The race will be on to capture the earliest moments. Amateur astronomers will contribute significantly. Professional telescopes can't cover the entire sky simultaneously, but thousands of amateur observers can. The first visible light detection might come from someone's backyard telescope. That's how supernovae are often discovered. Automated surveys catch many now, but amateurs still find them regularly. With Betelgeuse, the amateur community will be watching closely. Many have already planned their observation strategies. They know what equipment to use, what filters to apply, how to record data properly. When the moment comes, they'll be ready. This democratization of astronomy is relatively recent. Decades ago, meaningful contributions required access to major observatories. Now, affordable equipment can capture scientifically valuable data. Amateurs discovered comets, tracked asteroids, monitored variable stars. They've become essential parts of the astronomical community. Betelgeuse's supernova will showcase this collaboration beautifully. Professional astronomers will coordinate with amateur networks. Data will flow in from every continent. The global effort will be unprecedented in scale. And it needs to be. The first hours and days are crucial. That's when the shock wave breaks through the star's surface. That's when we see the initial flash, the rapid brightening, the spectrum changing minute by minute. These early moments constrain models of the explosion mechanism. Missing them means losing irreplaceable information. Automated systems will help. Robotic telescopes can respond within seconds of an alert. They'll begin collecting data before humans even know the supernova started. But human judgment matters too. Deciding which observations to prioritize, which instruments to use, how to adapt to unexpected developments. These decisions require expertise and intuition. The combination of automated systems and human oversight will maximize the scientific return. We're not just waiting passively. Preparations continue constantly. Observation plans are refined. Software is updated. Detector calibrations are checked. Communication networks are tested. When Betelgeuse explodes, everything needs to work perfectly. There's no second chance. Some might wonder why we invest so much effort into one star. The answer is that Betelgeuse represents an entire class of objects. What we learn applies to red supergiants everywhere. These stars are crucial for galactic chemical evolution. They produce and distribute heavy elements. Understanding their life cycles and death throes helps us understand galaxies themselves. Every galaxy contains stars like Betelgeuse. Most are too distant to study individually, but Betelgeuse is close enough for detailed observation. It's a proxy for countless others. The investment in studying it pays dividends across multiple fields. Beyond the science, there's something profound about witnessing cosmic events in human timescales. Most astronomical processes unfold over millions or billions of years. We see only snapshots. Stellar evolution happens too slowly to watch. But supernovae are different. They're fast. A human lifetime might encompass the entire visible phase. That connection between cosmic and human time makes supernovae special. We can experience them, not just study them abstractly. When Betelgeuse explodes, people worldwide will look up and see something genuinely new in the sky. That shared experience will be remarkable. Different cultures will interpret it differently. Some will see it as an omen, others as a spectacle. Scientists will see it as data. All perspectives are valid. The night sky belongs to everyone. Throughout history, bright astronomical events have left marks on human culture. Supernovae recorded by ancient astronomers influenced art and mythology. The 1054 supernova that created the Crab Nebula was documented across multiple civilizations. Betelgeuse will be brighter and closer. Its cultural impact could be substantial. Modern astronomers might create detailed records, but they'll also capture something previous generations couldn't: real-time public engagement. Social media will light up instantly. Images will spread globally within minutes. The scientific community will share observations openly, faster than ever before. This transparency changes how discoveries unfold. Previous supernovae occurred before the Internet age. News traveled through traditional channels, slowly. Professional papers took months or years to publish. By contrast, Betelgeuse's explosion will be documented second by second online. Live streams will show telescopes tracking it. Data will be posted immediately. The entire process becomes visible. Some worry this openness might spread misinformation. Fair concern. Spectacular events attract wild speculation. We'll see claims about danger, about cosmic rays, about effects on Earth. Most will be nonsense. The challenge is separating signal from noise. Education becomes critical. Astronomical organizations are dechuan by kak chien dike thon tin som som. Kai siu tan tin zara, thon tin chin zak kan ko san nai lap tuc. En hung jai tik ro ran v en hung gi dang zara, no ko nia la gi, en hung wan noi him now kong tun tai. Su min bok fu dao lam jiam su hom lon vanam lan. Because there will be questions. Lots of them. Can the supernova harm us? No, the distance is far too great. Will it affect our weather? Not measurably. Could radiation reach Earth? Negligible amounts, harmless. These answers need to be ready, accessible, repeated often. The physics is straightforward but counterintuitive. 600 light-years sounds close astronomically. In human terms, it's incomprehensibly distant. Light from the explosion travels for 6 centuries before reaching us. Any dangerous radiation disperses across that vast gulf. By the time it arrives, it's weaker than cosmic rays we experience constantly. Neutrinos will arrive first, actually. They pass through matter easily, so they escape the collapsing core before light does. Detectors worldwide will register a sudden burst of neutrinos. This signal arrives hours before the visible brightening. It's the earliest warning possible. Neutrino detectors are already monitoring constantly. They're designed to catch exactly this scenario. When Betelgeuse collapses, detectors will see the neutrino pulse and send alerts automatically. Astronomers will have precious hours to prepare before the light reaches us. Those hours matter immensely. Telescopes can be pointed, exposure started, spectrographs readied. The very first light from the shock breakout is scientifically valuable. It happens fast, just minutes or hours. Being prepared means capturing data that would otherwise be lost forever. This coordination represents decades of planning. Alert systems connecting neutrino detectors to telescopes. Automated response protocols. International agreements on data sharing. All built specifically for rare transient events like this. Betelgeuse will test whether these systems work as designed. Beyond the immediate explosion, there's the aftermath. The supernova remnant will evolve over years and centuries. Initially, it expands rapidly, plowing into surrounding material. This creates shock waves, heating gas to millions of degrees. The remnant glows in X-rays and radio waves. Betelgeuse has already shed significant mass through stellar winds. That material surrounds the star in shells and clumps. When the supernova ejecta slams into this material, complex interactions occur. Shocks reflect and refract. Instabilities develop. The remnant won't be smooth or symmetrical. Studying these interactions reveals how supernovae inject energy into their surroundings. This feedback affects star formation in galaxies. Supernova shocks compress nearby gas clouds, sometimes triggering new stars to form. Other times, the energy disperses clouds, preventing star formation. Both processes shape galactic evolution. Betelgeuse's remnant will be uniquely observable. Most supernova remnants are ancient and distant. We see them thousands of years after the explosion. Betelgeuse offers the opposite, a remnant we can watch from birth. Imaging it yearly will show expansion, structural changes, emission variations. This time-lapse view is unprecedented. Infrared observations will be particularly revealing. Dust forms in the cooling ejecta within months or years of the explosion. This dust glows in infrared, creating a spectacular expanding shell. The dust composition tells us what elements were synthesized in the star and during the explosion itself. Speaking of elements, the periodic table owes much to stars like Betelgeuse. Hydrogen and helium came from the Big Bang. Almost everything else was forged in stars. Carbon, nitrogen, oxygen, iron, gold, uranium. All created through nuclear fusion or supernova explosions. Red supergiants produce elements through multiple processes. Fusion in the core generates elements up to iron. During the supernova, explosive nucleosynthesis creates heavier elements. The shock wave compresses material, driving reactions that wouldn't occur otherwise. Elements beyond iron, those requiring energy input rather than releasing it, form exclusively in these conditions. When Betelgeuse explodes, roughly 10 solar masses of processed material will be ejected. That's an enormous chemical payload. The ejecta will enrich the interstellar medium, mixing into gas clouds. Future generations of stars will incorporate these elements. Planets forming around those stars will contain atoms forged in Betelgeuse. This is how galaxies become chemically enriched over cosmic time. Early generations of stars contained only hydrogen and helium. They produced heavier elements and distributed them via supernovae. Subsequent stellar generations had more metals, enabling different types of stars and planetary systems. Our solar system contains elements from countless previous supernovae. Betelgeuse will continue this cycle. Somewhere, millions of years hence, a planet might form containing atoms from this star. Perhaps that planet will host life. Perhaps beings there will study astronomy, unaware that their very bodies contain material from a star humans once watched. The interconnectedness is profound. We're not separate from cosmic processes. We're participants. The calcium in our bones, the iron in our blood, all created in stellar furnaces and scattered by supernovae. When we observe Betelgeuse, we're studying our own origins. This perspective shifts how we think about astronomy. It's not just distant objects unrelated to us. It's our history, our context, our extended environment. The universe isn't something we live in passively. It's an active, evolving system, and we're part of it. Betelgeuse's supernova will make this tangible. Watching a star die, knowing it's producing elements essential for life, creates a visceral connection. This isn't abstract physics. It's the mechanism that made our existence possible. Educational opportunities abound. Kai siu tan tin zara, wa quan tam den thien van hoc si tang vot. Kak truong hoc si dua no veo chuan trin jong day. Kak kung thien van si tau ra kak chuang trin dac beat. Kak by jong son so misi lap day kak thin fong. Koen kok nai ko the trian kam hung cho mot the he kak na kwa hok. History shows that astronomical events influence career choices. Many astronomers trace their interest to a specific observation or discovery that captivated them young. Betelgeuse could be that catalyst for thousands of people. The timing is unpredictable, but the impact will be lasting. Some of those inspired individuals might make future discoveries. They might solve problems we haven't identified yet. Science advances through accumulated effort across generations. Betelgeuse's supernova will feed into that ongoing process. There's also artistic inspiration. Throughout history, cosmic events have influenced art, literature, music. The night sky has always been a muse. A bright new star will spark creativity across cultures and disciplines. We'll see paintings, poems, compositions, all responding to this celestial event. Different artistic traditions will interpret it uniquely. Western perspectives might emphasize scientific understanding. Other cultures might focus on spiritual or philosophical dimensions. Indigenous traditions might connect it to existing cosmologies. Each response enriches our collective understanding. Because science doesn't have a monopoly on meaning. Supernovae can be approached from multiple angles. The astrophysics is one layer. The cultural significance is another. The personal, emotional response is yet another. All are legitimate. When Betelgeuse explodes, some people will cry. The night sky they've known their entire lives will change suddenly. A familiar constellation will look different. There's genuine loss in that, even if the star is unimaginably distant. Orion won't be the same. Others will feel excitement, wonder, curiosity. A rare event happening in their lifetime. Something their descendants will ask about. The chance to witness cosmic change directly. Both reactions are valid. The universe doesn't care how we feel about it. But our feelings matter to us. They're part of how we process and integrate experiences. Betelgeuse's supernova will be an experience, not just an observation. Preparation continues. The astronomical community remains vigilant. Betelgeuse could explode tonight. Or it might wait another 100,000 years. Statistically, sooner seems more likely than later, but statistics don't determine individual events. What we do know is that when it happens, we'll be ready. The infrastructure exists. The expertise is available. The coordination is practiced. This will be the most thoroughly documented supernova in history. And then comes the question everyone asks eventually: what happens after? After the initial explosion, after the brightness fades, after the remnant disperses. What's left? At the center, probably a neutron star. Chi loi sup du, kak proton va electron by engian nat voi now, tau ton kak neutron. Ket qua ymot vat the ron koang 20 kilometers, chua koi luong lan han mat troi, doak due tri boi ap sut sui bien neutron. Du la mot trong en hung vat the dai dac not ko the coma kong tiro ton mot lo den. Neutron stars are bizarre. Mot thiat sa fi vat lu sa neutron se non han tai ten tren tre dat. Tron luke bi mat man den muc kak gon nui chi ko the chow vi millimet truok kai sup du. Kak tu truong man not trong vu true. Mot so sa neutron que hang tram lon moi jie. Betelgeuse's neutron star will initially be hot, glowing in X-rays. Over millennia, it will cool and fade. Eventually, it becomes a cold, dark remnant. Still there, still massive, but invisible except through gravitational effects. Unless it becomes a pulsar. Some neutron stars emit beams of radiation from their magnetic poles. As they rotate, these beams sweep through space like lighthouse beams. If a beam is directed toward Earth, we will detect regular pulsations. Hence the name. Whether Betelgeuse's remnant will be a pulsar depends on details we can't predict: the core's rotation rate, the magnetic field strength, the viewing angle. We'll find out when it happens. The supernova remnant itself will expand for tens of thousands of years. Eventually, it merges with the interstellar medium, becoming indistinguishable from the general background. The atoms it scattered will drift through space, perhaps eventually condensing into new stars. Human impact category, minimal. The carbon in those future stars might eventually form planets. On those planets, life might emerge. Intelligent beings might look up at their sky and wonder about the universe. Inside them, atoms that once burned in Betelgeuse. The cosmic recycling program operates on timescales that make human history look like a blink. But here's something most people miss about supernovae. They're not endings. They're transformations. The star doesn't cease to exist, it changes form. Energy, matter, information, all continue. Just differently arranged. Betelgeuse right now contains the future. Elements waiting to be comprehensive. Energy waiting to be released. Stories waiting to be told. When it explodes, none of that disappears. It just moves elsewhere. This connects to something deeper about existence itself. Nothing truly ends. It transforms. The atoms in your body were once inside stars. After you die, they'll become something else. Trees, soil, water, air. Eventually, perhaps, other living things. The boundaries we draw between self and universe are convenient fictions. At the atomic level, we're continuous with everything. Betelgeuse reminds us of this. A star that will die so that new things can live. Not metaphorically. Literally. The supernova creates the raw materials for future complexity. Without stellar death, only hydrogen and helium would exist. No carbon, no oxygen, no iron. No planets, no life, no consciousness. We exist because stars die. That's not poetic language. That's physics. Every element heavier than helium was forged inside stars or during their explosive deaths. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all came from supernovae. We're not just in the universe. We're made of it. Literally composed of stellar corpses. Betelgeuse will add to that treasure. When it exploded, it created elements that don't currently exist anywhere nearby. Those atoms will drift through space for millions of years. Some will be incorporated into new structures. And somewhere, unbelievably in the future, something will exist because Betelgeuse is dead. The scale of this is difficult to internalize. We think in days, years, decades. Maybe centuries if we're historically minded. But stellar evolution operates on timescales where our entire species is a rounding error. Betelgeuse has been a star for roughly 8 million years. It might exist as a neutron star for trillions of years. Our entire civilization could rise, peak, and vanish in the gap between two of its heartbeats. Yet here we are, contemplating it. Tiny creatures on a small planet, understanding something greatly larger and older than ourselves. That's remarkable. We're the universe trying to understand itself. Atoms arranged in such a way that they can contemplate other atoms. Consciousness emerged from matter, then turning around to study the matter it came from. Betelgeuse doesn't know we exist. It's not aware of anything. It's just physics, chemistry, nuclear reactions following inevitable rules. But we're aware of it. We've studied it, predicted its fate, prepared to observe its death. In a sense, we're giving meaning to something that has none inherently. The supernova will happen whether we watch or not. But by watching, we transform it from a physical event into a human experience. We make it mean something. That's what consciousness does. It takes raw existence and converts it into meaning, understanding, story. Some people find this terrifying. The idea that meaning isn't inherent, that we create it ourselves. If the universe doesn't care, if there's no cosmic purpose, what's the point? But consider the alternative. If meaning were predetermined, fixed, universal, we'd be passive recipients. Instead, we're active creators. Every observation, every thought, every response adds to the universe's complexity. Betelgeuse will explode. That's determined by physics. But what it means, how we respond, what we learn, those are up to us. The universe provides raw material. We provide interpretation. And interpretation matters. The way we frame cosmic events shapes how we see ourselves. If we view supernovae as death and destruction, we emphasize loss, endings, fear. If we view them as transformation and creation, we emphasize change, renewal, possibility. Both perspectives describe the same physics, but they lead to different psychological spaces. The scientific perspective offers something valuable here. It doesn't say supernovae are good or bad. It says they're necessary. Without them, we wouldn't exist. They're not tragic or triumphant. They're functional. Part of how the universe operates. There's something freeing in that. Betelgeuse's explosion isn't personal. It's not happening to us or for us. It's just happening. We get to witness it because we exist in the right time and place. That's privilege, not punishment. The countdown continues. Each day, Betelgeuse converts helium to carbon, carbon to oxygen, and oxygen to silicon. Each day, the core shrinks a little. Each day, the outer layers shed more mass. Each day, the inner clock ticks closer to zero. We can't stop it. We can't speed it up. We can only observe and understand. In a universe that often feels chaotic and arbitrary, there's something satisfying about predictable processes. We know what will happen. We just don't know when. That uncertainty is important, though. If we knew the exact date, the supernova would become just another scheduled event. Mark your calendar, set a reminder, watch it happen. But the not knowing keeps us alert. Every clear night could be the night. Every observation could be the last one before everything changes. Amateur astronomers check Betelgeuse regularly. Has it dimmed? Brightened? Changed color? Mostly, it looks the same. But that could change tonight. Or tomorrow. Or next year. The very act of vigilance becomes meaningful. We are observing the universe, maintaining a connection to something far greater than our everyday concerns. When it finally happens, the response will be global. Instant communication means everyone will know within minutes. Social media will explode, though not as dramatically as Betelgeuse. News organizations will scramble to explain what's happening. Scientists will rush to their telescopes. And billions of people will look up, trying to find it in the sky. For a few weeks, astronomy will dominate conversations. People who never think about stars will suddenly care. Children will learn about supernovae in school. Artists will create inspired works. Writers will craft stories. The event will ripple through culture in unpredictable ways. Then, gradually, it will fade from attention. Supernovae will still be visible, but familiarity breeds indifference. Other news will dominate. Life will return to normal. For a year, most people won't think about it often. In 10 years, it will be a historical footnote. For 100 years, just another entry in the astronomical catalog. But the impact won't disappear. Everyone who witnesses it will carry that memory. The night the sky changed. The moment we watched a star die. That becomes part of personal history, woven into identity. And the science continues. Long after public attention fades, researchers will still be analyzing data, refining models, testing theories. The supernova becomes a permanent fixture in astronomical literature. Papers will reference it for centuries. It becomes the standard against which other supernovae are measured. Betelgeuse's death will advance our understanding of stellar evolution. We'll learn things impossible to discover any other way. The data will be scrutinized, debated, reinterpreted. New questions will emerge. Some will be answered. Others will persist for decades. That's how knowledge grows. Not through sudden revelations, but through accumulated observations, tested against predictions, refined through debate. One supernova won't solve everything, but it'll move us forward. That's enough. The universe doesn't reveal itself all at once. It requires patience, persistence, careful attention. Betelgeuse is teaching us even before it explodes. About stellar structure, mass loss, nucleosynthesis. The explosion will be the final exam, testing whether we understood the lesson. We're as ready as we'll ever be. Devices are built. Teams are trained. Protocols are established. When Betelgeuse explodes, humanity will react with coordinated precision. Thousands of people work towards a shared understanding. That coordination itself is remarkable. A global species acting in harmony, focused on pure knowledge. No profit motive drives this. No territorial advantage. Just curiosity. The desire to understand. In a world often fractured by competing interests, astronomy offers rare unity. Everyone benefits from the knowledge. No one loses when we learn. Betelgeuse doesn't care about any of this. It doesn't perform for us. It's just a star, subject to the laws of physics. But we care. We've invested time, resources, and attention. We've built our understanding around stars like this. When it explodes, we'll watch, not because we have to, but because we want to. That wanting matters. It's what makes us human. The drive to understand, even when understanding serves no immediate practical purpose. We study supernovae because they're there, because we can, because the knowledge itself is valuable. And when that light finally arrives, when Betelgeuse's death announcement reaches Earth, we'll be here. Watching. Recording. Understanding. Adding one more piece to the infinite puzzle of existence. The star will die. We'll learn. The universe will continue. And somewhere in that continuation, meaning emerges. Not given. Created. By us. Right now. As we wait for the sky to change. So we stand here, citizens of a moment, watching a star that might already be dead. The light that reaches our eyes tonight left Betelgeuse before Columbus set sail. We are seeing history, not current events. That time lag creates a strange relationship with reality. Somewhere in the vastness between here and there, photons are traveling. Maybe they're the last normal ones, carrying an image of Betelgeuse as it was. Maybe others follow, carrying the flash, the explosion, the transformation. We won't know until they arrive. This is astronomy's fundamental constraint. We're always looking backward. The present is inaccessible. We study the past and call it observation. Betelgeuse could have exploded last week. The information simply hasn't reached us yet. No way to check. No faster channel exists. Light speed is the universe's speed limit, and we're bound by it. That limitation used to frustrate early astronomers. Now we've accepted it. We built our entire field around it. We turned the constraint into methodology. We can't see the present, so we study how the past becomes the present. We measure time through light's journey. When Betelgeuse's supernova light arrives, it'll be carrying a message 6 centuries old. The star made a decision in the 1400s. We're waiting for the announcement. The explosion has happened, or it hasn't. Both possibilities exist simultaneously in our experience until the light resolves the uncertainty. Quantum mechanics talks about superposition. States exist simultaneously until measurement collapses them into a single reality. Betelgeuse is our macroscopic version. Simultaneously exploded and unexploded, depending on your frame of reference. From the star's perspective, it was either one or the other. From our perspective, it's both. That's not mysticism. That's relativity. Information can't travel faster than light, so distant events haven't happened to us yet, regardless of what happened there. Our present doesn't include Betelgeuse's present. They are disconnected, separated by distance and the speed limitations of causality. This creates odd implications. If Betelgeuse exploded yesterday, it's already a supernova. Just not for us. For someone positioned differently, maybe closer, it already happened. For someone farther away, it won't happen for centuries. The event's timing depends on where you're standing. There's no universal now. People struggle with this. We want objective reality, fixed facts, definite answers. The universe doesn't provide them. It offers perspectives, reference frames, relative truths. What's simultaneous for you isn't for someone moving differently. What's now for you is past or future for someone positioned differently. Betelgeuse forces us to confront this. We're waiting for information about something that either has or hasn't occurred, and we genuinely don't know which. Both possibilities are real until light arrives and shatters our uncertainty. The philosophical implications extend beyond astronomy. How we understand time, causality, existence itself, all get challenged by cosmic distances. We think we inhabit a shared present. We don't. We inhabit overlapping light cones, regions of spacetime connected by possible causal relationships. Betelgeuse sits outside our current light cone. Its present is inaccessible to us. Whatever is happening there right now, we cannot know for at least 642 years. By the time we find out, it will be ancient history. The present retreats forever from our observational capabilities. This isn't a limitation. It's structure. The universe is constructed this way. Information travels at the speed of light. There are no exceptions. That creates a fundamental line between knowledge and ignorance. We can know the past. The present is uncertain. The future is inaccessible. Betelgeuse's supernova will teach us this viscerally. We'll watch something that already happened centuries ago. The explosion will be news to us, but it will be old news to the universe. We are always behind, always chasing, never reaching the present moment of distant objects. Some find this depressing. We'll never truly know what's happening now in the broader universe. By the time we see it, it's history. But consider an alternative. If we could see everything at once, if distance didn't create a delay, causality would be broken. Effects could precede causes. Time would lose its meaning. The light speed limit protects causality. It ensures that effects follow causes. It creates an arrow of time, a direction, a structure. Without it, the universe would be chaotic. With it, we have order, predictability, and functioning physics. Betelgeuse demonstrates this beautifully. The star follows rules. It burns fuel, contracts, heats up, and eventually collapses. Each step inevitably leads to the next. The sequence is deterministic. We can predict it without seeing it. This could be because causality is maintained, because the speed of light limits information, because the universe is structured. When the supernova finally becomes visible, it'll confirm what we already predicted. Or it will surprise us, forcing us to revise our model. Either way, we learn. The universe teaches through examples. Betelgeuse is one example among billions. But it is our example, close enough to study, bright enough to see, time to happen when we have the tools to understand it. That timing is arbitrary. We didn't arrange it. Betelgeuse doesn't know we exist. It died millions of years ago, according to stellar physics. We happen to develop intelligence in its final chapter. Purely by chance. But by chance we can exploit it. Humanity's window of technological capability is narrow. We've had serious astronomy for maybe 400 years. We'll probably have it for thousands more, barring catastrophe. Betelgeuse's supernova might occur during this window. Or it might not. The odds favor it happening eventually, but eventually is vague. If it happens next week, we're positioned to study it thoroughly. If it waits 10,000 years, future civilizations will have that opportunity. Either way, someone benefits. Knowledge enters human understanding whenever it comes. Timing influences who learns, not whether the learning happens. This long-term view helps. We're not racing against time. We're participating in an ongoing project that spans generations. Astronomers today prepare the equipment, develop theories, and train students. Those students will train others. When Betelgeuse explodes, whoever survives will carry on the accumulated knowledge. Science is cumulative. Each generation builds on the work of the previous one. Today's observations of Betelgeuse provide information for tomorrow's understanding. The supernova, when it occurs, will be explained through the frameworks we are building now. Our preparation is not wasted if the explosion is delayed. It's an investment in future knowledge. And the preparation itself teaches us. Building instruments, refining models, coordinating observations, all develop skills and understanding applicable beyond Betelgeuse. We don't just wait. We are improving. Every observation, even of an unexploded star, adds to the data. Each refinement of the model increases accuracy. Work continues regardless of when the key event occurs. This patience is characteristic of astronomy. We study processes that take longer than a lifetime. We ask questions that we ourselves may not be able to answer. We contribute to understanding that benefits people we will never meet. It requires a special mindset. Long-term thinking. Delaying gratification. Belief in collective progress. Betelgeuse embodies this perfectly. We're watching. We're waiting. We're preparing. We don't know when it'll happen. We know it will happen. That's enough. The act of watching itself is meaningful. The preparation is valuable. The knowledge we are building is important, whether there is a supernova or not. Because ultimately, this isn't about one star. It's about understanding how stars work. Betelgeuse is a case study, an example, a test subject. What we learn applies to countless other stars. The principles are universal. Physics doesn't change from one star to another. Only the details change. When Betelgeuse explodes, it'll validate or challenge our understanding of those universal principles. Both outcomes advance science. Validation means our models work. Surprise means they need improvement. Both are progress. So we watch. We wait. We prepare. Betelgeuse hangs on Orion's shoulder, burning its last of fuel, approaching its inevitable demise. We can't stop it. We can't predict exactly when. We can only observe and understand. That's enough. That's all. That's the meaning of doing science. Watch the universe do what it does and learn from watching it. The star will die. We will see it. We will understand it better than any supernova before. And then we move on to the next question, the next mystery, the next opportunity to push understanding forward. Because that's what we do. That's what makes us who we are. We look up. We ask. We work to understand. And the universe, indifferent yet generous, provides countless opportunities to learn. Betelgeuse is one opportunity. Just one. But it is ours, and we are ready, and when the light arrives, carrying news of an explosion that happened centuries ago, we will be here, watching, recording, understanding. Another piece added to the endless puzzle. The star will change. We will learn. And somewhere in that learning, meaning arises. Not given. Created. By us. Through our attention, our curiosity, and our patient work to comprehend what we see when we look up at the night sky and see it change. Right now, somewhere in the darkness between stars, invisible predators drift through our galaxy. They have no light, no sound, no warning of their approach. And if one passed close enough to our solar system, we wouldn't see it coming until it was far too late. These are rogue black holes. Stellar corpses torn from their birthplaces, now wandering the Milky Way in complete silence. Scientists estimate there could be hundreds of millions of them out there, and we've barely detected a handful. The rest remain hidden, moving through space like cosmic ghosts, bending light around themselves, swallowing anything that crosses their path. What makes them truly terrifying isn't just their power. It's that we have almost no way to track them until they're already here. And when astronomers finally developed methods to spot these wanderers, what they found was deeply unsettling. Black holes form when massive stars collapse. We've known this for decades. A star 20 times the mass of our sun burns through its fuel, its core implodes, and gravity crushes everything into a point of infinite density. What's left behind is an object so dense that not even light can escape its pull. Most of these black holes stay where they formed, anchored in place by the remnants of their stellar neighborhood. But not all of them. When a massive star explodes as a supernova, the blast isn't always symmetrical. If the explosion throws more material in one direction than another, the newborn black hole gets kicked hard. Astronomers call these natal kicks, and they can launch a black hole across the galaxy at speeds exceeding 600 kilometers per second. That's more than 2 million kilometers per hour. Fast enough to escape the gravitational grip of its birthplace entirely. Once free, these objects become nomads. They don't orbit anything. They don't belong to any star system. They simply drift through the galaxy, following trajectories set by that violent birth moment, invisible and utterly indifferent to whatever lies in their path. Here's where it gets worse. Our galaxy has been forming stars for over 13 billion years. Millions of massive stars have lived and died in that time. Each one that met the right conditions created a black hole. And a significant fraction of those black holes received kicks strong enough to send them wandering. Do the math, and you arrive at a disturbing conclusion. The Milky Way should be filled with these things. Early estimates suggested tens of millions. More recent models push that number higher, potentially into the hundreds of millions. Picture that for a moment. Between 100 million and 400 million rogue black holes, drifting silently through the same space we occupy. Most are stellar mass black holes, between 5 and 50 times the mass of our Sun. Small by cosmic standards, but devastating by any measure that matters to us. And we can't see them. A black hole by definition emits no light. It's a hole in space where light goes to die. The only way we typically detect black holes is by watching how they affect their surroundings. If a black hole is pulling gas from a companion star, that gas heats up as it spirals inward, glowing brilliantly in X-rays before it vanishes beyond the event horizon. Binary systems like this are relatively easy to spot. We've cataloged dozens of them. But a rogue black hole traveling alone through empty space has nothing to feed on. No companion star. No accretion disk. No telltale X-ray signature. It's just a gravitational knot in the fabric of spacetime, moving silently through the void. For decades, astronomers assumed these objects were essentially undetectable. They were out there, sure, but finding them seemed impossible. Then someone realized we'd been thinking about the problem wrong. Even invisible objects reveal themselves through gravity. Einstein showed us this more than a century ago. Mass warps spacetime, and light follows those curves. When light from a distant star passes near a massive object, the object's gravity bends that light like a lens. If the alignment is precise enough, the background star appears to brighten temporarily as its light is magnified and focused toward us. Astronomers call this gravitational microlensing. The technique had been used successfully to find planets, distant stars, even other black holes in binary systems. But using it to hunt lone rogue black holes required a different approach entirely. You'd need to monitor millions of stars continuously, waiting for one to brighten in exactly the right way. The chances of catching such an event are microscopically small. The alignment has to be perfect, the timing has to be right, and you have to be watching that exact star at that exact moment. In 2011, a team of astronomers decided to try anyway. They pointed their telescopes toward the galactic bulge, the dense central region of the Milky Way where stars are packed close together. More stars mean more opportunities for alignment. They monitored the brightness of millions of stars simultaneously, searching for the characteristic signature of a black hole passing in front of them. For years, they found nothing conclusive. Hundreds of microlensing events, yes, but most could be explained by normal stars or brown dwarfs. Then in 2022, they announced something different. An event designated MOA-2011-BLG-191. The light curve was perfect. A star had brightened over several weeks, peaked, then faded back to normal. But the duration and shape of that brightening suggested something unusual. The lensing object wasn't a star. It was too massive and too dark. After ruling out other possibilities, the team concluded they detected a rogue black hole. Somewhere between 2 and 7 solar masses, drifting alone through the galaxy approximately 5,000 light-years from Earth. It had passed directly between us and a background star, briefly magnifying that star's light before continuing on its silent journey. This was the first time anyone had definitively detected an isolated black hole wandering through space. Not orbiting anything. Not feeding on anything. Just moving. And it raised an immediate question. If we found one, how many more are out there that we haven't found? The galaxy is enormous. 300 billion stars spread across 100,000 light-years. Even hundreds of millions of rogue black holes would be sparse in that volume. The chances of one passing close to any particular star are vanishingly small. But close is a relative term in space. A black hole doesn't need to hit something directly to affect it. Gravity works at a distance. If a rogue black hole passed within a few light-years of our solar system, we'd likely never notice. It would tug slightly on the orbits of distant comets in the Oort cloud, maybe nudge a few toward the inner solar system, but nothing catastrophic. Pass within 1 light-year, and the effects become more pronounced. Orbits destabilize. Long-period comets get redirected. The delicate gravitational balance that keeps our solar system stable starts to shift. Get closer than that, and things deteriorate rapidly. A black hole passing within the orbit of Neptune would gravitationally scatter the outer planets. Jupiter's orbit would shift. Saturn's rings might destabilize. The asteroid belt could be stirred into chaos, sending rocks careening through the inner solar system. Earth's orbit would change. Not immediately, not catastrophically in human terms, but enough to alter our climate over centuries. Enough to make our world unrecognizable. And if one passed within the orbit of Mars, we'd have months at best. Maybe weeks. The sun itself would be affected, its outer layers potentially stripped away as the black hole's gravity pulled at stellar material. Earth's orbit would become wildly elliptical or be ejected from the solar system entirely, flung into interstellar space to freeze in the darkness. The worst part isn't the destruction itself. It's the warning time. Or rather, the complete lack of it. Current detection methods only work when a rogue black hole passes directly in front of a background star from our perspective. By the time we detect that microlensing event, we're observing something that happened years or centuries ago, depending on the distance. The light we're seeing left that region of space long before we started watching. The black hole itself is already somewhere else entirely, continuing its journey along a path we can't predict. We have no early warning system. No way to scan ahead and spot an approaching threat. Gravitational wave detectors like LIGO can detect black hole mergers halfway across the universe, but a single black hole drifting through space produces no gravitational waves. It's silent on every wavelength we can measure, visible only through the brief distortion it causes when perfectly aligned with a distant light source. Astronomers are working on better detection methods. Upcoming surveys will monitor more stars more continuously, increasing the chances of catching microlensing events. The Vera Rubin Observatory, scheduled to begin operation soon, will photograph the entire visible sky every few nights, watching for anything that changes. That includes the subtle brightening caused by gravitational lensing. But even with better surveys, we're still looking at a reactive system. We find these objects after they've already passed, not before. And the galaxy is simply too large, too dark, too filled with empty space to monitor comprehensively. The number of rogue black holes out there almost certainly exceeds our ability to track them all. Which brings us to an uncomfortable probability calculation. With hundreds of millions of these objects wandering the Milky Way, and 13 billion years of galactic history behind us, what are the chances one has already passed close to our solar system? Or that one will in the future? The distances involved are staggering enough that the risk to any individual star system remains low over human timescales. But over millions of years, over billions, the odds shift considerably. And we're not just talking about direct hits. Even a distant passage could destabilize the Oort cloud, sending comets plunging toward the inner planets. Some researchers have suggested that periodic comet bombardments in Earth's history might be explained by exactly this mechanism. A rogue black hole passing through the outer solar system every few tens of millions of years, stirring up frozen debris and sending it inward. It's speculative, but it fits certain patterns in the geological record. And it suggests these invisible wanderers have been influencing our corner of space far longer than we've been here to notice. The galaxy's structure offers little comfort when you consider the mechanics. Rogue black holes don't travel in neat, predictable orbits like planets around a star. They follow paths determined by countless gravitational interactions over billions of years. A close encounter with another star system deflects the trajectory. Passage through a dense molecular cloud changes the velocity. The cumulative effect of these interactions creates something closer to a random walk than an orbital pattern. Which means prediction becomes functionally impossible beyond a certain distance. What makes this particularly unsettling is scale. We think of black holes as massive objects, and compared to everyday experience, they are. But in galactic terms, a stellar mass black hole is microscopic. The event horizon of a 10 solar mass black hole measures roughly 60 kilometers across. That's smaller than many cities. Now imagine trying to spot something that size, something that emits no light, against the backdrop of a galaxy 100,000 light-years in diameter. You're looking for a dark marble in an ocean at night. From another continent. The only reason we've detected any at all is because space isn't completely empty. Gas and dust exist between stars, thin beyond anything we'd call a vacuum on Earth, but present nonetheless. When a black hole moves through this tenuous material, it pulls some of it inward. That gas heats up through friction and compression, reaching temperatures where it emits X-rays. Not much. Not the brilliant accretion disks we see around supermassive black holes in galactic centers. Just a faint glow, barely detectable even with our most sensitive instruments. But here's the problem with using that detection method. It only works if the black hole happens to be passing through a region with enough gas to produce a visible signature. Most of interstellar space is far emptier than that. A black hole could pass within a light year of Earth, close enough to potentially affect the orbits of outer solar system objects, and we'd see nothing. No X-rays. No visible light. No radio emissions. Just gravitational effects we wouldn't notice until something started behaving strangely. The math on close approaches is genuinely disturbing. Researchers have calculated that a black hole passing within 50 astronomical units of the Sun, roughly the distance to the Kuiper belt, would disrupt the orbits of trans-Neptunian objects significantly. Within 20 astronomical units, orbital perturbations would extend to the giant planets. Closer than 10, and Earth's orbit itself becomes unstable over timescales ranging from centuries to millennia, depending on the exact trajectory and mass involved. These aren't extinction-level events in the immediate sense. The black hole doesn't need to hit us to cause catastrophic problems. Orbital changes of even a few percent would alter Earth's climate dramatically. Seasons would shift. The length of the year would change. If the orbit became more elliptical, we'd experience temperature swings between perihelion and aphelion far more extreme than current seasonal variations. Glaciation cycles would accelerate or halt entirely. Ocean currents would reorganize. Weather patterns would transform beyond recognition. Life on Earth has survived worse. Mass extinctions punctuate the fossil record, some far more severe than what an orbital disruption might cause. But those events unfolded over thousands or millions of years. Ecosystems had time to migrate, adapt, or collapse gradually. A black hole passage could destabilize things within decades. Too fast for agricultural systems to adjust. Too fast for species to migrate to new climate zones. Too fast for human civilization to reorganize around new realities. The truly nightmarish scenarios involve closer approaches. If a rogue black hole entered the inner solar system, say within Mars's orbit, the effects would be immediate and overwhelming. Earth's orbit wouldn't just shift slightly. It would change fundamentally. We might be ejected from the solar system entirely, flung into interstellar space along a trajectory determined by the exact angle and speed of the encounter. Or we might fall inward, spiraling toward the Sun over a timescale of centuries. Either way, Earth as a habitable planet would end. Ejection means freezing. Without the Sun's heat, surface temperatures would plummet to near absolute zero within years. The atmosphere would condense and freeze, falling as snow that would eventually cover the entire surface in a layer hundreds of meters thick. Oceans would freeze solid to their beds. Any life that survived would exist in deep subsurface environments, perhaps around geothermal vents, living off Earth's internal heat rather than solar energy. Human survival would require either impossible engineering or simply wouldn't happen. Falling inward carries its own horror. The journey toward the Sun would take time, but the end result is incineration. Earth's orbit decaying, bringing us closer to a heat source that already makes the equator brutal during summer. Temperatures would rise steadily. Oceans would boil away, The atmosphere would be stripped by solar wind. Eventually, the planet would be torn apart by tidal forces before ever reaching the solar surface, debris scattered across the inner solar system like a planetary corpse. The galaxy doesn't care about any of this. These events occur with statistical regularity across billions of star systems. Most stars will experience close encounters with rogue objects over their lifetimes. Some will be disrupted. Some will capture new planets or have existing ones stripped away. It's part of the normal evolution of galactic structure. We just happen to be conscious observers existing during a period when our particular star system hasn't experienced such an event recently. Recently, in this context, means within the last few 100 million years. The geological record shows no evidence of sudden orbital disruptions on that timescale. Earth's climate has varied, sometimes dramatically, but always within ranges consistent with predictable astronomical cycles. The Milankovitch cycles that drive ice ages operate over tens of thousands of years and result from subtle variations in Earth's orbital eccentricity and axial tilt. Not the kind of violent perturbations a black hole passage would cause. But absence of evidence isn't evidence of absence over longer timescales. Go back far enough, and the record becomes unclear. The early solar system was chaotic. Planets migrated. Giant impacts occurred. The late heavy bombardment around 4 billion years ago reshaped the inner solar system. Could some of that chaos have been influenced by a passing rogue black hole? Possibly. We have no way to determine that from current evidence. The gravitational signatures would have been erased long ago by subsequent evolution. What we can determine is frequency based on what we observe elsewhere. Studies of stellar velocities in our galactic neighborhood show occasional stars moving at speeds inconsistent with normal orbital patterns. Hypervelocity stars, traveling fast enough to escape the galaxy entirely. Some of these gained their speed through close encounters with the supermassive black hole at the galactic center. Others might have been accelerated by interactions with rogue black holes in the disk. The distribution of these fast-moving stars gives us clues about how often such encounters occur. The numbers suggest a close approach between a rogue black hole and a random star system happens perhaps once every few 100 million years within any given volume of space. That sounds reassuring until you remember we're talking about an entire galaxy containing hundreds of billions of stars. Multiply that out, and you get thousands of these encounters happening somewhere in the Milky Way right now. This moment. As you process these words, a black hole is likely disrupting a solar system dozens or hundreds of light years away. We'll never see it. Never detect it. Never know which star just had its planetary system torn apart. The speed at which these objects move creates additional problems for detection. Stellar velocities in our region of the galaxy average around 200 kilometers per second relative to the local standard of rest. A rogue black hole might be moving faster or slower, depending on its history, but it's in that general range. At those speeds, an object crosses 1 astronomical unit, the distance from Earth to the Sun, in about 2 months. It could traverse the entire solar system in less than a year. Detection, analysis, and response would need to happen within that window. Except we can't detect them reliably in the first place. And even if we could, what response exists? You can't deflect a black hole. You can't destroy it. You can't negotiate with fundamental physics. The only option would be evacuation, and evacuating Earth's population to somewhere safer runs into the obvious problem that there is nowhere safer within reach. Generation ships heading to other star systems would take thousands of years to reach destinations that might themselves be threatened by rogue black holes. Underground bunkers might preserve some fraction of humanity through orbital disruption, depending on severity, but only if Earth remains in a relatively stable orbit around the Sun. Ejection into interstellar space makes that impossible. The planet becomes uninhabitable too quickly for any bunker to matter. This is the situation we exist within. A galaxy filled with invisible threats following unpredictable paths at velocities that leave no time for meaningful response. The odds of a direct impact remain low over human timescales. Low enough that it doesn't make sense to lose sleep over it specifically. But the odds of an encounter somewhere in our cosmic neighborhood, close enough to affect our understanding of how stable planetary systems really are, sit much higher. The question becomes what kind of encounter would actually matter to us. Not just theoretically, but in ways we could measure or experience within human lifetimes. Start with gravitational influence at a distance. A stellar mass black hole passing within a few light years of the solar system wouldn't cause immediate catastrophe, but it would perturb the Oort cloud. That's the spherical shell of icy bodies extending roughly halfway to the nearest star, loosely bound to the Sun's gravity. Disturb that region, and you send comets falling inward toward the inner solar system. Not immediately. The journey takes thousands to millions of years depending on initial position and velocity. But once started, the process continues regardless of whether the black hole remains nearby. Historical impact records on Earth and the Moon show periodic increases in cratering rates. Some researchers have proposed these patterns correlate with the solar system's oscillation through the galactic plane, where stellar density runs higher. More stars means more gravitational perturbations. More perturbations means more comets get nudged loose. The mechanism makes sense even if the specific correlations remain debated. A rogue black hole passing through the Oort cloud would produce similar effects, just concentrated in time rather than spread across millions of years of gradual oscillation. The increased impact rate wouldn't sterilize Earth. Life has survived multiple impact events far worse than anything a perturbed Oort cloud could produce. But it would stress ecosystems, potentially triggering extinctions among larger organisms less able to shelter or adapt quickly. Human civilization, dependent on stable agriculture and infrastructure, would face serious challenges. Not extinction level, but enough to reshape societies and potentially set back technological development by centuries. That scenario assumes the black hole stays several light years away. Move it closer and effects intensify. At 1 light year out, roughly a quarter of the distance to Proxima Centauri, gravitational effects become more direct. The outer planets would experience measurable orbital perturbations. Nothing dramatic over human timescales, but enough to show up in precision tracking data. Jupiter's orbit might shift by fractions of a percent. Saturn's rings could develop new gaps or resonances as orbital periods change slightly. These aren't catastrophic alterations, but they'd be detectable, and they'd tell us something massive had passed nearby. The inner solar system would feel weaker effects at that distance. Earth's orbit wouldn't change noticeably within a single human lifetime. But over centuries, small perturbations accumulate. Climate patterns depend partly on Earth's orbital eccentricity and axial tilt. Alter those parameters even slightly and you change how solar energy distributes across the planet's surface. Ice ages have been triggered by orbital variations smaller than what a passing black hole at 1 light year might induce. Now bring it closer still. Half a light year. A tenth. At these ranges, we're talking about an object whose gravitational influence begins competing with the Sun's hold on the outer planets. Neptune and Uranus could experience significant orbital changes within decades. Their moons might be stripped away entirely, sent tumbling into new orbits around the Sun or ejected into interstellar space. The inner solar system would still remain relatively protected by distance and the sun's stronger local gravity, but relatively does heavy lifting in that sentence. At 1/10 of a light year, maybe 3 months of travel time at typical stellar velocities, detection becomes theoretically possible through gravitational lensing. The black hole's gravity would bend light from background stars, creating a characteristic pattern of brightening and positional shifts as it moves across the sky. Dedicated surveys searching for such events could potentially spot it, given enough luck and the right observational geometry. But that requires the black hole to pass almost directly between us and cataloged background stars, and it requires astronomers to be looking at the right patch of sky at the right time with equipment sensitive enough to catch subtle lensing signatures. The odds aren't favorable. Even if detected, the warning time measured in months doesn't allow for much beyond observation and calculation. We'd watch it approach, model its trajectory, estimate its mass based on lensing strength, and project what effects it might have on planetary orbits. Then we'd wait to see if the models were right. If the black hole passes within the outer solar system itself, within Neptune's orbit, we've moved from theoretical concern to immediate crisis. At those ranges, orbital mechanics become chaotic in the technical sense. Small changes in initial conditions produce wildly different outcomes. Whether Earth remains in a stable orbit or gets perturbed into a more elliptical path, whether the perturbation is mild or severe, whether we end up closer to the Sun or farther away, all of this becomes sensitive to precise details of the black hole's mass, velocity, and trajectory. Run the simulation 1,000 times with slightly different starting parameters and you get 1,000 different results. Some show minimal impact. Others show Earth's orbit elongating enough to create extreme seasonal temperature swings. A few show ejection from the solar system entirely. The disturbing part isn't that ejection scenarios exist. It's that we couldn't predict which outcome would occur until the black hole was already here, moving through the system, its gravity actively reshaping orbital paths in real time. By then it's far too late for any response beyond documentation. Consider what ejection actually means. Earth doesn't crash into the black hole. It doesn't get torn apart by tidal forces unless the approach is extraordinarily close, within a few million kilometers. What happens instead is the planet gets gravitationally kicked, like a billiard ball struck at an angle. The velocity change might be only a few kilometers per second, but that's enough. Earth's orbital velocity around the Sun sits at about 30 kilometers per second. Add or subtract even a small fraction of that and you change whether the orbit remains bound to the Sun. Once unbound, Earth drifts into interstellar space. The Sun shrinks to just another bright star in the sky, eventually indistinguishable from the others except by position. Surface temperatures drop rapidly as solar heating cuts off. Oceans freeze within years. The atmosphere begins condensing as temperatures fall below the freezing points of various gases. Carbon dioxide snow falls first, then nitrogen, then oxygen. Eventually you're left with a ball of ice coated in frozen air, drifting through the void at several dozen kilometers per second relative to the galactic frame. Deep underground, residual heat from radioactive decay in Earth's core continues for billions of years. Hypothetically, life could persist in deep crustal environments or around hydrothermal vents on the ocean floor, sealed beneath kilometers of ice. These ecosystems already exist in darkness, independent of photosynthesis, powered by chemical energy from the planet's interior. They might not even notice the Sun's absence, at least not immediately. Surface life ends completely. Everything dependent on solar energy, which means everything humans need to survive, ceases functioning within months. No agriculture. No renewable energy. No ecosystem services. Survival would require moving underground with nuclear or geothermal power, growing food under artificial light, and maintaining sealed habitats indefinitely. The technical challenges are immense but theoretically solvable. What's not solvable is doing this for billions of people with no preparation time. Even if a fraction of humanity survived in deep bunkers or sealed cities, you've essentially ended human civilization as we understand it. The survivors would live in permanent artificial environments, cut off from any natural world, maintaining themselves through technology that must never fail because there's no outside to escape to. This is assuming the ejection is gentle enough to leave Earth intact as a physical body. A closer approach could generate tidal forces strong enough to cause massive earthquakes, trigger volcanic eruptions, or in extreme cases, literally crack the planet's crust. The threshold for tidal disruption depends on how close the black hole passes and how fast. A stellar mass black hole would need to come within a few 100,000 kilometers to tear Earth apart through tidal forces alone. That's close, closer than the Moon's orbit. It's unlikely but not impossible. What's more likely, if a rogue black hole passes through the inner solar system at all, is significant orbital disruption without physical destruction. Earth survives as a planet but ends up somewhere it wasn't before, in an orbit that no longer supports the climate patterns civilization developed around. Maybe the new orbit is more elliptical, creating extreme seasonal variations. Maybe it's slightly closer to the sun, triggering runaway greenhouse effects. Maybe it's farther out, pushing the planet toward permanent glaciation. Each scenario creates different challenges, some potentially manageable with advanced technology, others not. The fundamental problem remains unchanged. We can't predict these events with useful lead time. We can't prevent them. We can barely detect the objects responsible. And the consequences range from inconvenient to civilization ending depending on variables we can't control. So we exist in a galaxy where these objects drift through the dark, occasionally reshaping solar systems they pass near, and we have no systematic way of knowing where they are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance doesn't mean ignoring the problem. It means acknowledging what we can and can't control, and focusing effort on the things that actually matter within our capability to influence. This brings us to something slightly more optimistic but equally strange. What happens if we reverse the scenario? Instead of losing the sun, what if Earth captured a second one? Binary star systems are common in the galaxy. Roughly half of all stellar systems contain two or more stars orbiting each other. If our solar system encountered a wandering star under precisely the right conditions, gravitational interactions could theoretically bind it into a stable configuration. The newcomer would need exactly the right mass, velocity, and trajectory. Too fast, and it simply passes through. Too slow or too close, and orbital chaos follows. Let's assume the best case. A star roughly half the Sun's mass approaches from a perpendicular angle to the solar system's plane, moving at just the right speed to be captured into a wide elliptical orbit. The two stars settle into a configuration where they orbit their common center of mass every few thousand years, staying far enough apart that planetary orbits remain mostly stable. Even in this ideal scenario, everything changes. First, there's no longer a single point in the sky that defines day and night, seasons, or climate stability. Depending on orbital positions, Earth might receive varying amounts of total radiation throughout the year. When both stars align on the same side, the planet gets hotter. When they oppose each other, one might be visible during what used to be night, eliminating true darkness for months at a time. Ecosystems evolved under predictable light cycles would face immediate stress. Plants time their growth, flowering, and dormancy to seasonal patterns that have remained consistent for millions of years. Disrupting that rhythm doesn't just inconvenience agriculture. It destabilizes the foundation of terrestrial food webs. Animals navigate, hunt, and reproduce based on day length and seasonal cues. Migratory birds use the sun's position for orientation. Nocturnal species depend on darkness. Coral reefs synchronize spawning to lunar cycles and water temperature patterns tied to solar radiation. All of these systems assume one sun following a predictable path. The climate effects cascade through every layer of atmosphere and ocean. Earth's climate system relies on differential heating between equator and poles to drive atmospheric circulation and ocean currents. Those patterns exist because solar radiation arrives at different angles across latitudes and varies predictably through the year. Adding a second star, even one much dimmer than the sun, introduces new heating patterns that don't align with the geography. Jet streams might shift latitude or weaken entirely. Ocean currents that distribute heat globally could alter course or speed. The intertropical convergence zone, which drives tropical weather patterns, might oscillate unpredictably or split into multiple bands. Then there's orbital mechanics. Even if Earth's orbit remains stable initially, long-term gravitational perturbations from the second star would accumulate. Over thousands of years, Earth's orbital eccentricity might increase, creating more extreme seasonal variations. The axial tilt that currently gives us moderate seasons could begin precessing faster or shifting to new angles. Other planets face worse outcomes. Mars, already in a precarious position with thin atmosphere and marginal temperatures, could be pushed into an orbit that makes it even less habitable. Jupiter and Saturn, the solar system's gravitational anchors, would experience altered orbits that ripple through the entire planetary arrangement. The asteroid belt, currently stable in gaps maintained by Jupiter's gravity, could destabilize. Resonances that previously kept asteroids in safe orbits might break down, sending debris inward toward the inner planets. Impact rates could increase significantly over geological timescales. None of this happens overnight. A captured star doesn't immediately scramble planetary orbits. The changes unfold over decades, centuries, millennia. But they're directional. The solar system wouldn't settle into a new stable state identical to the old one. It would transition toward a different equilibrium, one that might not include Earth in the habitable zone. From a human perspective, even the short-term effects present serious challenges. Agriculture depends on predictable growing seasons. Water resources rely on consistent precipitation patterns driven by stable atmospheric circulation. Infrastructure assumes certain temperature ranges and weather extremes. All of that gets recalibrated when the fundamental energy input to the climate system becomes variable. And we're still assuming the best case where the second star approaches gently and settles into a distant orbit. More likely scenarios involve closer approaches that don't result in capture but still perturb planetary orbit significantly during the encounter. A star passing through the outer solar system would gravitationally scatter comets from the Oort cloud, sending them falling inward. Some would miss Earth. Some wouldn't. The impact risk would spike for thousands of years after the encounter as these disturbed objects crossed the inner system. Planetary orbits themselves could shift. Not dramatically, not instantly, but enough to matter. Earth might end up in a slightly wider orbit, reducing solar radiation and triggering gradual cooling. Or a slightly tighter orbit, increasing temperatures and accelerating ice melt. Either direction creates a planet humans didn't evolve on and haven't built civilization around. The probability of capturing a second star remains extremely low. Space is vast, stellar encounters are rare, and the specific conditions needed for stable capture are narrow. But stellar flybys, close enough to disrupt things without capture, occur more frequently on geological timescales. The Sun will experience multiple close encounters with other stars over its remaining lifespan. Most will pass without incident. Some won't. And this assumes we're only dealing with normal stars. What if the intruder is a white dwarf, a stellar remnant much smaller but incredibly dense? Or a neutron star, packing more mass than the Sun into a sphere 20 kilometers across? The gravitational effects scale with mass, not volume. A neutron star passing through the outer solar system would wreak havoc despite being physically tiny. These objects are harder to detect at distance because they emit little light. A white dwarf shines dimly. A neutron star barely radiates in visible wavelengths. By the time we noticed one approaching, it might be too late to do anything beyond calculating the consequences. The galaxy contains billions of stellar remnants drifting through interstellar space. Most are isolated, moving on predictable paths that won't intersect our neighborhood. But on timescales of millions or billions of years, encounters become statistically inevitable. The solar system will interact with other massive objects. The question isn't if, but when and how severely. We can model these scenarios mathematically. We can run simulations showing what happens to planetary orbits under various perturbations. We can calculate impact probabilities and climate shifts. What we can't do is prevent them or predict them far enough in advance to matter. That leaves us in an odd position. We understand the risks. We know the mechanisms. We can describe in detail what would happen under different conditions. But we can't defend against threats operating at stellar scales with energies and masses that make human technology irrelevant. This isn't fatalism. It's recognition that some problems exist outside our ability to solve. You don't build contingency plans for events that would end technological civilization because there's no point. Either the event doesn't happen and the planning was unnecessary, or it does happen and the plans don't help. What matters instead is understanding our place in a dynamic galaxy where stability is temporary and change is guaranteed. The solar system occupies its current configuration because nothing has disturbed it recently. That's not a permanent state. It's a snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. The Sun formed 4.6 billion years ago from a collapsing molecular cloud. It will continue fusing hydrogen for another 5 billion years before exhausting its core fuel and expanding into a red giant. Within that time span, the solar system will experience multiple gravitational encounters with passing stars, clouds of interstellar matter, and possibly rogue planets or stellar remnants. Most encounters will be minor. A slight tug on the Oort cloud. A tiny shift in planetary orbits too small to measure. Occasionally, something more significant occurs. A star passes within a light year, scattering comets inward. A molecular cloud drifts through the system, altering solar radiation through increased dust. A massive object transits nearby, pulling planets into new configurations. These are not hypothetical scenarios invented to frighten people. They're documented processes observed in other stellar systems and predicted by our understanding of galactic dynamics. We exist in a galaxy that doesn't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. Acknowledging this doesn't mean giving up. It means recognizing which problems require solutions and which require acceptance. We can't prevent stellar encounters. We can understand them, model them, and perhaps detect them earlier with better observation networks. That knowledge serves a purpose even if it doesn't change outcomes. Human time operates on scales measured in decades or centuries. Stellar mechanics operate on scales measured in millions of years. That disconnect creates a perceptual problem. We evolved to recognize immediate threats. Predators, storms, drought. Our nervous systems weren't built to process dangers that unfold over timeframes longer than civilizations exist. A star passing within 2 light-years over the next million years doesn't trigger the same response as something happening next week. But the physics doesn't care about our perception. Gravity operates continuously. Orbits shift gradually. What seems stable on human timescales reveals itself as dynamic when viewed across proper intervals. Jupiter's orbit changes. Saturn's rings evolve. The Moon recedes from Earth at about 4 centimeters per year. These aren't static objects frozen in place. They're participants in an ongoing gravitational negotiation that never stops. Now scale that up to galactic levels. The Milky Way contains 200 billion stars, most with their own planetary systems. Add brown dwarfs, rogue planets, stellar remnants, molecular clouds, and regions of concentrated dark matter. Everything moves. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion, where encounters between systems happen regularly across cosmic timescales. Our Sun orbits the galactic center once every 230 million years. During each orbit, it passes through different regions of the galaxy. Spiral arms, interarm regions, areas of higher and lower stellar density. Each environment presents different risks. Spiral arms contain more massive stars, which means more supernovae, more stellar winds, more radiation. They also contain giant molecular clouds that can trigger ice ages by blocking sunlight. Interarm regions are quieter but not empty. Rogue objects drift through these spaces. Stellar remnants. Planets ejected from their original systems. Objects too dim to detect until they're relatively close. The galaxy doesn't maintain clear boundaries between safe and dangerous zones. It's all dangerous given enough time. What varies is the probability and severity of encounters. Right now, the solar system occupies a relatively calm neighborhood. The nearest star, Proxima Centauri, sits 4.2 light-years away. That's far enough that its gravitational influence on our planets is negligible. The next closest stars are also comfortably distant. This configuration is temporary. Stars move at different velocities relative to each other. In about 30,000 years, a red dwarf called Ross 248 will pass within 3.2 light-years of the Sun, becoming our closest neighbor for a time. Then it will continue on its path and something else will take its place. These close passes happen regularly on galactic timescales. Most are harmless. A star passing within 5 light-years exerts minimal gravitational influence on planets orbiting another star. The effects are measurable in simulations but negligible in practice. Closer encounters are rarer but more consequential. A star passing within 1 light-year would perturb the Oort cloud significantly, potentially sending comets into the inner solar system for millions of years afterward. A star passing within half a light-year could affect planetary orbits directly, though the changes would be subtle unless the encounter was extremely close. The problem is detection. We can track nearby stars with current technology, but only the relatively bright ones. Dim red dwarfs, brown dwarfs, and rogue planets are much harder to spot until they're already close. Infrared surveys have improved our ability to find these objects, but gaps remain. Something could be approaching that we won't notice until it's within a few light years. By then, we'd have thousands of years to study it but no ability to change its trajectory. Altering the path of a stellar mass object would require energy expenditures far beyond anything human technology can produce. You can't nudge a star the way you might deflect an asteroid. The mass difference is too large. The energies involved too extreme. Even if we had millions of years to prepare, the engineering challenges would be insurmountable. Which brings us back to the same conclusion. Observation and understanding, yes. Prevention, no. We can map nearby space. We can identify potential threats decades or centuries before they arrive. We can calculate exactly what will happen during an encounter. None of that changes the outcome. It just means we'll know what's coming. There's value in that knowledge even without the ability to act. Understanding allows for preparation of a different kind. Not physical defenses, but intellectual frameworks. If we know a stellar encounter will destabilize the Oort cloud in 50,000 years, that information becomes part of how future generations think about long-term survival. Maybe it influences where deep space probes are sent. Maybe it affects how astronomical databases are maintained. Maybe it does nothing practical but satisfies the human need to understand our environment. That need is real even when it doesn't lead to solutions. We study supernovae knowing we can't prevent them. We model black hole behavior knowing we'll never interact with one. We map the cosmic microwave background knowing it tells us about events we can't influence. Knowledge has value independent of utility. Stellar encounters fall into that category. They're important to understand because they're part of the environment we exist in. They shape planetary evolution. They influence the long-term habitability of solar systems. They determine which configurations of planets remain stable over billions of years. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. A distant encounter might scatter some comets. A close encounter could reshape orbits. An extremely close encounter could eject planets from the solar system entirely. These aren't equally likely. The probability decreases dramatically as encounters get closer. But over billions of years, even low-probability events become near certainties. The Sun will experience multiple close encounters before it exhausts its hydrogen fuel. Some will be minor. At least one might be significant. The galaxy guarantees change over sufficient timescales. What it doesn't guarantee is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, the system reorganizes into a new stable state that might look nothing like the original. This has already happened to countless other systems. We observe planetary systems with highly eccentric orbits, planets too close to their stars, gas giants in locations where they couldn't have formed. These are signatures of past disruptions. Encounters with other stars. Planetary migrations triggered by gravitational interactions. Systems that reorganized after their original configurations became unstable. Our solar system shows signs of its own past reorganization. The NICE model suggests that Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions. They migrated inward and outward after formation, possibly triggered by encounters with planetesimals or resonances between their orbits. This migration would have scattered smaller bodies throughout the solar system, explaining features like the late heavy bombardment 4 billion years ago. If that model is correct, the solar system has already experienced major gravitational reshuffling. What we see now is the result of that reorganization, not the original configuration. Which means change isn't hypothetical. It's already happened. The question is whether it will happen again during the remaining lifespan of the Sun. Probability suggests yes. Timing remains unknown. The galaxy contains too many variables to predict specific encounters far in advance. We can calculate general probabilities. We can identify nearby objects and track their movements. We can model what would happen under different scenarios. What we can't do is point to a specific date and say this is when the next major disruption occurs. That uncertainty is permanent. It's built into the nature of galactic dynamics. Too many objects moving in too many directions with too many possible interactions. Even perfect knowledge of current positions and velocities wouldn't allow precise predictions millions of years ahead because gravitational interactions are chaotic. Small changes in initial conditions produce large differences in outcomes over time. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. The math doesn't allow exact long-term predictions even in principle. We're left with statistical models and probability ranges. Useful for understanding general patterns but useless for predicting specific events. That's not a limitation of current technology. It's a fundamental feature of how gravity works in systems with multiple interacting masses. Chaos isn't something better computers can solve. It's an inherent property of the equations governing motion. Which means we'll never have certainty about future stellar encounters. We'll have better observations, more detailed models, improved probability estimates. We won't have schedules. The galaxy doesn't operate on schedules. It operates on physics, which produces patterns but not predictability. Stars move through space according to gravitational laws that allow probability calculations but resist precise forecasting over timescales measured in millions of years. The Sun's journey through the galaxy has already lasted 4.5 billion years. During that time, it's completed roughly 20 orbits around the galactic center. Each orbit takes between 200 and 250 million years, depending on the Sun's exact distance from the center and the distribution of mass in the galaxy. 20+ complete circuits means 20+ passages through the spiral arms, dozens or hundreds of close encounters with molecular clouds, and countless interactions with the changing gravitational landscape of the Milky Way. The solar system survived all of it. The planets remained in stable orbits. Earth maintained conditions suitable for life across geological timescales. Whatever encounters occurred during those billions of years, none were catastrophic enough to eject planets or sterilize Earth. That's not luck. It's statistics. Most stellar encounters are distant enough to cause minimal disruption. The dangerous ones are rare. Over billions of years, the rare events that do occur tend to fall within a range the system can absorb without complete destruction. But survival of past encounters doesn't guarantee immunity from future ones. Each passage through a spiral arm resets the probability. Each orbit through the galaxy exposes the Sun to new potential interactions. The gravitational environment changes constantly as stars move through their own orbits, clusters form and dissolve, and the galaxy's structure evolves. What protected the solar system during previous orbits might not be sufficient during future ones. The distribution of stars changes. Regions that were once relatively empty can become more crowded as stellar populations shift. The Sun's current path through the galaxy might take it through denser neighborhoods than it experienced in the past. Or it might lead it into quieter regions. There's no way to know without detailed mapping of stellar trajectories across millions of years, which remains beyond current observational capabilities. One factor that does influence encounter probability is the Sun's vertical oscillation through the galactic plane. The Sun doesn't orbit the galactic center in a flat circle. Its path carries it above and below the galactic plane in a wave-like motion, crossing through the plane approximately every 30 to 40 million years. When the Sun passes through the galactic plane, it encounters higher stellar densities than when it's above or below. The plane contains most of the galaxy's visible matter, including stars, gas, and dust. Crossing through it increases the probability of close encounters simply because there are more objects present. Some researchers have suggested this oscillation might correlate with mass extinction events on Earth, proposing that encounters with molecular clouds or increased comet impacts occur more frequently during plane crossings. The evidence remains debated. Extinction patterns don't show clear periodicity matching the oscillation cycle. Even if a correlation exists, it would demonstrate that galactic position influences Earth's history, not that future crossings will necessarily produce similar effects. Each crossing involves different molecular clouds, different stellar configurations, different gravitational contexts. Past patterns don't predict future outcomes with certainty. Beyond stellar encounters, the Sun faces long-term changes in the galaxy's overall structure. The Milky Way is currently on a collision course with the Andromeda Galaxy. The two galaxies will begin interacting in approximately 4 billion years, with a full merger occurring over the following few billion years. During galactic mergers, stellar orbits get disrupted on massive scales. Stars that once followed predictable paths around their galactic centers get scattered into new configurations as the two galaxies' gravitational fields interfere with each other. The Sun will likely survive the merger physically. Galactic mergers don't involve stars actually colliding because the distances between stars are enormous compared to their sizes. Even when two galaxies interpenetrate completely, the probability of any given star hitting another star remains vanishingly small. What changes is orbital structure. The Sun's current orbit around the Milky Way's center will become meaningless as that center merges with Andromeda's center. The combined galaxy, sometimes called Milkomena, will have a different shape, different rotation, different gravitational architecture. The Sun will end up in a new orbit around the merged galaxy's center, potentially far from its current position. That repositioning might place the Sun in denser regions with higher encounter probabilities, or in sparser regions with lower probabilities. The outcome depends on details of the merger that can't be predicted precisely. Simulations show general patterns but can't specify where individual stars end up. Too many variables. Too many gravitational interactions occurring simultaneously. The merger timeline presents an interesting coincidence. 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It will have exhausted most of its hydrogen fuel and begun transitioning toward the red giant phase. The Andromeda merger will commence around the same time the Sun starts expanding. Earth's fate might be sealed by solar evolution before galactic dynamics become the dominant concern. As the Sun expands into a red giant, it will engulf Mercury and Venus. Whether it reaches Earth's orbit remains uncertain and depends on exact mass loss rates during the expansion. Even if Earth's orbit isn't physically consumed, the increased solar radiation will vaporize the oceans and strip away the atmosphere long before the Sun's surface reaches Earth's position. By the time the galactic merger creates new gravitational dynamics, Earth will likely already be uninhabitable. That doesn't mean stellar encounters before then are irrelevant. Between now and the Sun's red giant phase, roughly 5 billion years remain. During that time, the Sun will complete another 20 orbits around the galaxy. 20 more passages through spiral arms. Hundreds more opportunities for close encounters. The probability that at least one significant encounter occurs during those 5 billion years is not negligible. What constitutes a significant encounter? Definitions vary depending on what effects you're measuring. For disrupting the Oort cloud and potentially triggering comet showers, encounters within 1 or 2 light-years matter. For perturbing planetary orbits directly, encounters need to be much closer, probably within a few thousand astronomical units. For ejecting planets entirely, encounters likely need to approach within hundreds of astronomical units. Each category has different probabilities and different consequences. Oort cloud disruptions are relatively common on million-year timescales. Direct planetary perturbations are rare but not impossible. Planetary ejections are extremely rare but have definitely occurred in other systems. The solar system probably won't experience a catastrophic close encounter during the next billion years. Probably. That's the strongest statement physics allows. The galaxy doesn't provide guarantees. Observation programs continue tracking nearby stars, measuring their positions, velocities, and trajectories. As data accumulates, predictions improve for specific stars over limited time periods. Gliese 710 will pass within 10,000 astronomical units in about 1.3 million years. HIP 85605 might come within 16,000 astronomical units in 240,000 years. These predictions carry uncertainty margins that increase with distance into the future. A star projected to pass at 10,000 astronomical units might actually pass at 8,000 or 12,000 depending on factors not fully constrained by current measurements. The difference matters when calculating gravitational effects on the Oort cloud. Small changes in closest approach distance produce large changes in the number of comets perturbed. Even with improving data, predictions beyond a few million years remain probabilistic rather than deterministic. The galaxy contains too many objects with too many possible interactions. The Sun's journey through the galaxy continues. Right now, it's moving toward the constellation Hercules at roughly 250 kilometers per second relative to the local standard of rest. That motion carries it through neighborhoods where stellar densities fluctuate, molecular clouds drift, and gravitational influences shift. Over the next 100 million years, the Sun will move several thousand light-years from its current position. New stars will become neighbors. Current neighbors will drift away. The gravitational landscape surrounding the solar system will transform completely multiple times before the Sun exhausts its hydrogen fuel. Each transformation brings new encounter possibilities. Each possibility carries a probability that can be calculated but not eliminated. The galaxy guarantees that change happens. It doesn't specify when or how severely. Our solar system exists in a dynamic environment where stability is temporary and disruption is eventual. Not immediate. Not predictable in detail. But inevitable given sufficient time. That's the nature of gravitational systems with many interacting bodies moving through space. Chaos emerges from deterministic laws. Probability replaces certainty. Patterns appear but predictions fail beyond certain timescales. The Sun will continue orbiting the galactic center, crossing through spiral arms, oscillating above and below the galactic plane, encountering molecular clouds and passing stars. Most encounters will be distant and inconsequential. Some will perturb the Oort cloud and send comets toward the inner solar system. A few might disturb planetary orbits enough to measure. One might eventually be close enough to fundamentally alter the solar system's architecture. We can't prevent it. We can't predict exactly when it will happen. We can only observe, calculate probabilities, and understand that the galaxy operates on timescales where rare events become commonplace. The question isn't whether the solar system will experience future disruption. The question is whether it will happen during a time frame that matters to us. For the next few million years, probably not. Beyond that, certainty dissolves into probability, and probability suggests that eventually, something significant will occur. The galaxy has 400 billion stars moving through space. The Sun is one of them, following its orbit through a constantly shifting gravitational landscape. Every orbit brings new encounters. Every encounter carries probabilities. Given enough orbits, those probabilities converge toward inevitability. That's not pessimism. That's mathematics applied to gravity operating across billions of years in a galaxy that never stops moving. The galaxy we inhabit operates without regard for our presence. Rogue black holes drift through the darkness between stars, following paths set by violent births millions or billions of years ago. Hundreds of millions of them, perhaps more, scattered across the Milky Way like invisible landmines in a cosmic ocean. We've detected a handful. The rest remain hidden, detectable only through rare gravitational lensing events that require perfect alignment and extraordinary luck. Detection methods improve. Surveys expand. Observation networks grow more sophisticated. None of it changes the fundamental problem. We're looking for objects that emit no light, produce no radiation, and reveal themselves only by bending the light of background stars during brief windows of alignment. Even when we catch these events, we're seeing something that happened years or centuries ago. The black hole itself has already moved on, continuing along a trajectory we can't predict with useful precision. The mathematics of galactic dynamics allows probability calculations but resists exact forecasting. Too many objects moving in too many directions with too many possible interactions. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. Chaos emerges from deterministic laws. Small changes in initial conditions produce wildly different outcomes over time. We can model general patterns but can't predict specific encounters millions of years ahead. That uncertainty is permanent. It's built into how gravity works in systems with multiple interacting masses. Better observations won't fix it. More powerful computers won't solve it. The galaxy doesn't operate on schedules we can map. It operates on physics that produces patterns but not predictability. What matters is understanding our position within this dynamic system. The solar system exists in its current configuration because nothing has disrupted it recently. That's not a permanent state. It's a temporary snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. Change is guaranteed over sufficient time. What isn't guaranteed is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, everything reorganizes into a new stable state that might look nothing like what came before. This has happened to countless other systems. We observed the signatures in eccentric orbits, misplaced planets, and configurations that couldn't have formed naturally. Evidence of past encounters that reshaped entire solar systems. Our own system shows signs of reorganization in its past. the planets might not occupy their original positions. The late heavy bombardment 4 billion years ago suggests major gravitational reshuffling occurred. What we see now could be the result of that ancient chaos, not the initial arrangement. Which means change isn't hypothetical. It's already happened here. The question is whether it will happen again on timescales that matter to anything currently alive. Probability suggests yes, eventually. Timing remains unknown. The Sun will experience multiple close encounters with other stars, molecular clouds, and possibly rogue black holes before it exhausts its hydrogen fuel. Most will be minor. Some might be significant. One could potentially be catastrophic. The galaxy guarantees encounters over billions of years. It doesn't specify which ones will matter or when they'll occur. We can't defend against threats operating at stellar scales. We can't deflect a black hole or alter the trajectory of a passing star. The mass differences are too large. The energies involved too extreme. Even with millions of years to prepare, the engineering challenges would remain insurmountable. You can't nudge a stellar mass object the way you might deflect an asteroid. What we can do is observe, understand, and acknowledge which problems exist outside our ability to solve. Knowledge has value independent of utility. We study phenomena we can't influence because understanding our environment matters even when we can't control it. Rogue black holes are part of that environment. They shape galactic evolution. They influence which planetary configurations remain stable over billions of years. They determine, in ways we're only beginning to understand, which systems survive long enough for complex life to develop. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. The galaxy contains 400 billion stars moving through space, countless stellar remnants, molecular clouds, rogue planets, and objects we haven't cataloged yet. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion where encounters between systems happen regularly across cosmic timescales. Most are harmless. Some aren't. The difference comes down to distance, mass, velocity, and timing. Variables we can measure in nearby objects but can't predict far in advance for the galaxy as a whole. So we exist in a dynamic galaxy where invisible predators drift through the darkness, occasionally reshaping solar systems they pass near. We have no systematic way of knowing where most of them are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance isn't fatalism. It's recognition of what we can and can't control, and focusing effort on things that actually matter within our capability to influence. The galaxy operates according to physical laws that don't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. We're participants in that process, not exempt from it. Understanding that doesn't change outcomes. It just means we'll know what we're looking at when the galaxy reminds us that stability is always temporary. 7 planets orbit a star 40 light-years away. Not scattered randomly like our solar system, but compressed into a space smaller than Mercury's orbit around our Sun. If you stood on one of these worlds and looked up, neighboring planets would appear larger in the sky than our moon. This isn't science fiction. This is TRAPPIST-1. In 2017, NASA announced the discovery of 7 Earth-sized planets around a single star. 3 of them sit in the habitable zone where liquid water could exist. Within weeks, TRAPPIST-1 became the most studied planetary system beyond our own. Scientists redirected telescopes, reprioritized missions, and rewrote research proposals. Because this system isn't just interesting, it's a laboratory for understanding whether life exists elsewhere in the universe. The star itself defies everything we assume about solar systems. TRAPPIST-1 is an ultra-cool dwarf star, barely larger than Jupiter, burning at temperatures that make it glow deep red rather than yellow like our Sun. It produces less energy in a year than our Sun emits in a day. Yet around this dim ember orbit 7 rocky worlds, each locked in gravitational resonance, their orbits synchronized like a cosmic clockwork mechanism that's been running for billions of years. Distance creates problems. 40 light-years means the light we see from TRAPPIST-1 today left that star before the internet existed. Any signal we send would take 40 years to arrive, and we'd wait another 40 for a response. Even our fastest spacecraft would need hundreds of thousands of years to reach it. This isn't a place we'll visit anytime soon. But distance doesn't mean irrelevance. The James Webb Space Telescope changed everything. For the first time in human history, we can analyze the atmospheres of planets orbiting other stars. We're not guessing anymore about what exists on distant worlds. We're measuring it directly. And TRAPPIST-1, with its compact system and frequent planetary transits, offers the best opportunity we have to detect signs of life beyond Earth. Here's what makes this system extraordinary. The planets don't just orbit randomly. They're locked in what astronomers call orbital resonance. For every 8 orbits TRAPPIST-1b completes, planets C, D, E, F, G, and H complete 5, 3, 2, 1, and 1 orbits respectively. This mathematical precision isn't coincidence. It's the signature of a system that has stabilized over billions of years, where gravitational interactions have pulled planets into synchronized motion. Think of it like pushing someone on a swing. Push at random times and nothing happens. Push at exactly the right moment in each cycle and the swing goes higher. The TRAPPIST-1 planets push and pull on each other at precisely the right times, stabilizing their orbits and potentially creating conditions that could support life. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 Earth days. It's too close to the star, receiving 4 times more radiation than Earth gets from the Sun. Surface temperatures likely exceed 400 degrees Fahrenheit. Any water that once existed has long since evaporated. But move outward and conditions change rapidly. TRAPPIST-1e sits in the middle of the habitable zone. It's almost exactly Earth's size, slightly more massive, with a density suggesting a rocky composition similar to our own planet. If water exists anywhere in this system, this is where we'd expect to find it. Scientists have focused enormous attention on this single world because it represents our best chance of finding life around an ultra-cool dwarf star. But there's a problem nobody expected. The first atmospheric measurements came back essentially blank. The James Webb Space Telescope detected no significant atmosphere on TRAPPIST-1b or C. For planets that should theoretically hold on to their atmospheres, this absence is troubling. It suggests something is stripping away these gaseous envelopes faster than planets can retain them. The star itself might be the culprit. Ultra-cool dwarf stars like TRAPPIST-1 are violent in ways our sun isn't. They produce intense stellar flares, bursts of radiation and charged particles that slam into nearby planets. These flares can be thousands of times more powerful than solar flares. When they strike a planet, they don't just heat the surface. They strip away atmospheric particles, molecule by molecule, potentially rendering worlds uninhabitable despite being in the so-called habitable zone. This creates a paradox. Ultra-cool dwarf stars are the most common type of star in the galaxy. They make up roughly 75% of all stars. They also live for trillions of years, far longer than our sun's projected 10 billion-year lifespan. If life needs time to develop, these stars offer more of it than any other stellar type. But if their flares destroy atmospheres, then the most common stars in the galaxy might also be the least likely to host life. Yet dismissing TRAPPIST-1 would be premature. Planets might protect themselves in ways we haven't considered. Strong magnetic fields could deflect stellar wind. Thick atmospheres could regenerate faster than flares strip them away. Oceans could provide a reservoir of gases that replenish atmospheric losses. And some planets in the system, particularly those farther from the star, might avoid the worst of the stellar violence while still receiving enough energy for liquid water. TRAPPIST-1F and G occupy positions at the outer edge of the habitable zone. They receive less radiation than Earth, but not so little that water must freeze. These worlds might be covered in ice with liquid oceans beneath frozen crusts, similar to Jupiter's moon Europa or Saturn's moon Enceladus. Such environments could be remarkably stable, shielded from stellar flares by kilometers of ice while maintaining liquid water in contact with rocky cores where chemical reactions could support life. The density measurements tell us something unexpected. These planets aren't identical copies of Earth. Their densities vary significantly, suggesting different compositions. Some might be water worlds with deep global oceans. Others could be desiccated rocks stripped bare by stellar radiation. A few might have retained thick atmospheres of hydrogen and helium. The system isn't uniform. It's diverse, offering multiple pathways for habitability or multiple ways for planets to fail at supporting life. Tidal forces add another layer of complexity. Because the planets orbit so close to their star and are likely tidally locked, one side permanently faces the star while the other side remains in eternal darkness. This creates extreme temperature gradients. The day side might be scorching hot while the night side freezes. Any atmosphere would constantly circulate, trying to redistribute heat from day to night. This circulation could create permanent storms, winds that never stop, weather patterns unlike anything Earth experiences. But tidal locking isn't necessarily bad for life. The twilight zones, the regions between permanent day and permanent night, could be remarkably stable. Temperatures there might remain moderate, avoiding the extremes of either hemisphere. If liquid water exists, it would likely pool in these twilight regions, creating narrow bands where conditions stay relatively constant. Life, if it exists, might be confined to these transitional zones, thriving in the permanent sunset of a tidally locked world. Scientists debate whether we could ever know for certain if these planets host life. Detecting an atmosphere is one thing. Proving that atmosphere contains biosignatures, gases produced by living organisms, is far more challenging. Oxygen is the classic example. On Earth, oxygen exists in our atmosphere because photosynthetic organisms constantly produce it. Without life, oxygen would quickly react with surface rocks and disappear. Finding oxygen in TRAPPIST-1E's atmosphere would be compelling evidence for life. But oxygen alone isn't enough. Geological processes can produce oxygen without life. We need combinations of gases, chemical signatures that only make sense if biology is present. Oxygen combined with methane, for instance, would be powerful evidence because these gases react with each other and shouldn't coexist unless something continuously produces them. Life produces both. Geology typically doesn't. The James Webb Space Telescope will spend years studying TRAPPIST-1. Each time a planet passes in front of the star, starlight filters through its atmosphere and reaches us carrying information about what gases exist there. By analyzing this light, scientists can identify atmospheric components. But the signals are faint. Detecting them requires hundreds of observations, patient accumulation of data, building up evidence piece by piece until a picture emerges. Recent observations of TRAPPIST-1b have been discouraging. The planet appears to have no substantial atmosphere. This doesn't doom the entire system, but it raises questions about how well any of these planets have retained their atmospheres. If the innermost planet lost its gases, what about the others? Are we searching for life in a system where stellar activity has already stripped away the very atmospheres we need to study? TRAPPIST-1c faces similar scrutiny. Early measurements suggested the possibility of a thick carbon dioxide atmosphere. Subsequent observations found no evidence for it. Either the atmosphere is incredibly thin or composed of gases we haven't detected yet. Or perhaps it simply doesn't exist. Each negative result narrows the possibilities but doesn't eliminate hope. We're still learning how to interpret these observations, still understanding the limitations of our instruments. The system's age compounds these uncertainties. TRAPPIST-1 is roughly 7.6 billion years old, significantly older than our solar system. That's billions of additional years for stellar flares to pummel planets, for atmospheres to erode, for conditions to change. But it's also billions more years for life to emerge, evolve, and potentially leave detectable traces. Age cuts both ways. What happens next depends on what we find. If TRAPPIST-1e has an atmosphere, the focus shifts to characterizing it completely. Scientists will search for water vapor, carbon dioxide, methane, oxygen, and dozens of other compounds. Each detection or non-detection refines our understanding of what kind of world exists there. If we find nothing, attention might shift to the outer planets where conditions could be less hostile despite receiving less stellar energy. Human nature drives us to find patterns, to imagine what these worlds look like, to picture oceans and mountains and alien skies. But we need to resist premature conclusions. TRAPPIST-1 might host life. It might be completely dead. It might fall somewhere in between, with environments capable of supporting life but currently empty through cosmic accident. The only way to know is through methodical observation, collecting evidence without rushing to judgment. The implications extend beyond 7 planets around a dim star. TRAPPIST-1 is common in the galaxy. Not this exact system, but ultra-cool dwarf stars with compact planetary systems. If we determine that TRAPPIST-1 planets can't support life, we're effectively ruling out billions of similar systems. If we find that life can exist there despite the challenges, we're opening up vast regions of the galaxy as potential habitats. Either answer reshapes our understanding of life's prevalence in the universe. Human outlined these possible outcomes. What actually exists at TRAPPIST-1 remains unknown. But each observation brings clarity, each measurement constrains possibilities. We're moving from speculation to data, from wondering to knowing. And the journey has barely started. The challenge isn't just detecting atmospheres. It's understanding what those atmospheres tell us about the planets beneath them. An atmosphere doesn't exist in isolation. It's shaped by volcanic activity, weathering of rocks, biological processes, and the relentless bombardment of stellar radiation. Consider what happens when starlight passes through a planetary atmosphere. Different molecules absorb specific wavelengths of light. Oxygen absorbs certain frequencies. Water vapor absorbs others. Methane has its own signature. By measuring which wavelengths are missing from the light that reaches us, scientists can deduce what gases are present. But this requires the planet to pass directly between us and its star, creating a transit. During those few hours when the geometry aligns, telescopes collect as much data as possible. Then the planet moves on, and we wait weeks or months for the next opportunity. The signal we're measuring is incredibly weak. Imagine trying to detect a single grain of sand added to a beach by measuring the beach's total weight. That's the scale we're working with. The atmosphere of an Earth-sized planet adds roughly 1 part in 10,000 to the total light blocked during a transit. Within that tiny signal, we're searching for even tinier variations caused by specific molecules. It's technically possible, but it requires perfect conditions, flawless calibration, and patience. TRAPPIST-1 doesn't make this easy. The star itself is variable, with surface features that change over time. Star spots, the cooler regions on a star's surface, can mimic or obscure atmospheric signals. When a planet transits across a star spot, the light curve changes in ways that have nothing to do with the planet's atmosphere. Separating these effects requires multiple observations and sophisticated modeling. We're essentially trying to subtract the star's natural variations to isolate the planet's contribution. The James Webb Space Telescope was designed for exactly this kind of work. Its infrared capabilities allow it to detect molecules that are invisible to optical telescopes. Carbon dioxide, for instance, has strong absorption features in the infrared. Water vapor shows up clearly. Methane becomes detectable. But even Webb has limitations. Observing a single planet requires multiple transits. Building up enough signal to confidently detect an atmosphere can take dozens of hours of telescope time. With 7 planets to study and limited observing windows, the process stretches across years. Early results from Webb have been humbling. The instrument works brilliantly, but the planets aren't cooperating. TRAPPIST-1b shows no sign of a thick atmosphere. TRAPPIST-1c remains ambiguous. These aren't instrument failures. They're real results telling us something important about how planets survive around red dwarf stars. Maybe atmospheres around these stars are rare. Maybe they exist but are composed of gases we haven't thought to look for. Or maybe we need more data before drawing conclusions. The habitable zone planets present a different puzzle. TRAPPIST-1e receives roughly the same amount of energy from its star as Earth receives from the Sun. If it has an atmosphere, that atmosphere could support liquid water on the surface. But the planet is tidally locked, with one side permanently facing the star and the other side in eternal darkness. This creates extreme temperature gradients. The day side could be scorching. The night side frozen. Only in the narrow band between them, the terminator region, might temperatures allow liquid water. Unless the atmosphere redistributes heat. A thick atmosphere with strong winds could transport warmth from the day side to the night side, moderating temperatures across the entire planet. Earth's atmosphere does this to some extent. Venus does it far more effectively, with winds so powerful they circle the planet in just 4 days despite the planet's slow rotation. If TRAPPIST-1e has similar atmospheric circulation, the entire surface could be habitable. But if the atmosphere is thin or non-existent, the terminator might be the only refuge. This matters for more than just temperature. Atmospheric circulation affects where water accumulates. On a tidally locked planet with poor heat transport, all the water could freeze on the night side, leaving the day side as a scorched desert. With good circulation, water could remain liquid across much of the surface. The difference between these scenarios determines whether the planet could support life, and whether that life might be detectable from Earth. Detecting life itself requires finding biosignatures, gases that are produced by living organisms and wouldn't persist in the atmosphere without continuous replenishment. Oxygen is the classic example. On Earth, photosynthetic organisms produce vast amounts of oxygen. Without them, oxygen would rapidly combine with rocks and disappear from the atmosphere. Finding oxygen around another planet doesn't guarantee life, but it strongly suggests biological activity. Methane is another candidate. On Earth, methane comes from both biological and geological sources. Bacteria in swamps produce methane. Volcanic activity releases it. Finding methane alone doesn't prove life exists. But finding methane and oxygen together creates a stronger case. These gases react with each other, so their simultaneous presence suggests something is actively producing them. Life is the most obvious explanation. The problem is false positives. Geological processes can produce oxygen under certain conditions. Photochemistry in the upper atmosphere can generate small amounts. Methane can accumulate if volcanic activity is high and chemical reactions are slow. We need multiple lines of evidence, combinations of gases that can't be easily explained by non-biological processes. And we need to understand the planet's geology, its star's activity, and its atmospheric chemistry well enough to rule out alternative explanations. TRAPPIST-1 stellar activity complicates biosignature detection. The star's flares produce ultraviolet radiation that can break apart atmospheric molecules, creating fragments that recombine in unexpected ways. This can generate false biosignatures, gases that look biological but are actually products of stellar radiation. Distinguishing between life and stellar chemistry requires understanding both processes in detail. The search extends beyond just looking for familiar gases. Life on Earth produces thousands of different compounds. Some, like dimethyl sulfide, are produced almost exclusively by marine organisms. Others, like certain chlorinated compounds, come from specific types of bacteria. These trace gases are harder to detect than oxygen or methane, but they're more specific. Finding them would provide stronger evidence for life. But it also requires knowing what to look for and having instruments sensitive enough to detect gases present at parts per billion. Computer models help predict what atmospheres around TRAPPIST-1 planets might look like under different conditions. Scientists simulate planets with various compositions, different amounts of volcanic activity, different ocean coverage, and different types of life. Each simulation produces a predicted spectrum, a pattern of light absorption that would result from that specific combination of conditions. By comparing observed spectra to these models, researchers narrow down which scenarios match reality. These models reveal surprising possibilities. A planet covered entirely by ocean might have an atmosphere dominated by water vapor and nitrogen. A volcanic world could have a thick carbon dioxide atmosphere with sulfur compounds. A planet with extensive forests might show strong oxygen signals alongside organic vapors. Each possibility requires different observational strategies and different interpretations of the data we collect. The outer planets, TRAPPIST-1F and G, orbit in the system's outer habitable zone. They receive less stellar energy, making them colder than the inner worlds. But cold doesn't mean lifeless. Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans beneath icy crusts, maintained by tidal heating. TRAPPIST-1's outer planets might follow similar patterns, with frozen surfaces hiding liquid water oceans below. Life in these oceans wouldn't show up in atmospheric observations, but it could still exist. Detecting subsurface oceans requires different techniques. Scientists look for magnetic fields generated by conductive fluids moving through the planet's interior. They search for evidence of geological activity that might indicate internal heat. They measure how the planet's gravity changes as it orbits, which can reveal whether a liquid layer exists beneath the surface. These observations are harder to make than atmospheric studies, but they're possible with sufficiently powerful telescopes and patient observation. The timeline for answering these questions stretches far into the future. Webb will observe TRAPPIST-1 planets for years, accumulating data transit by transit. Future telescopes, currently in the planning stages, will build on this foundation. The extremely large telescope, under construction in Chile, will have a mirror 39 meters across, dwarfing any existing ground-based telescope. It could directly image planets around nearby stars and study their atmospheres with unprecedented detail. But it won't be operational until the 2030s. Meanwhile, the search continues with existing tools. Ground-based telescopes track the system constantly, measuring changes in stellar activity and refining our understanding of planetary orbits. Space telescopes like Hubble and Spitzer have contributed observations, though neither was optimized for this kind of work. Webb carries the immediate burden, producing results that will shape the next decade of research. What we learn at TRAPPIST-1 will influence how we approach thousands of other planetary systems. If red dwarf planets can maintain atmospheres despite stellar activity, it validates searching for life around the galaxy's most common stars. If they can't, our focus shifts to sun-like stars, which are rarer but potentially more hospitable. Either outcome provides crucial information, but one expands our search space while the other constrains it dramatically. The 7 worlds of TRAPPIST-1 aren't just interesting objects. They're test cases for planetary habitability, laboratories where we can study how planets form, devolve, and maintain conditions suitable for life. Each observation adds another piece to a puzzle that spans astronomy, geology, atmospheric science, and biology. And somewhere in that puzzle lies an answer to whether we're alone. The search for biosignatures at TRAPPIST-1 depends on understanding what counts as proof. Oxygen in an atmosphere sounds like clear evidence of life, but nature produces oxygen through non-biological processes too. Ultraviolet radiation can split water molecules, releasing hydrogen into space and leaving oxygen behind. Photochemistry in carbon dioxide-rich atmospheres can generate small amounts of oxygen. The presence of oxygen alone isn't enough. Scientists need to find combinations of gases that can't coexist without constant replenishment from biological activity. Methane and oxygen together create such a combination. In Earth's atmosphere, these two gases react with each other, destroying both within years. Yet both persist because life constantly produces them. Plants generate oxygen. Bacteria in wetlands and animal digestive systems produce methane. Without this continuous input, both gases would vanish. Finding them together on a distant planet would suggest something actively maintains that chemical imbalance. But even this signature has caveats. Volcanic activity produces methane. Subsurface chemical reactions can release it. The ratio matters. The concentrations matter. The presence of other gases that might explain the pattern matters. A complete biosignature profile requires multiple lines of evidence converging on the same conclusion. No single measurement proves life exists. Only patterns that become progressively harder to explain through geology alone build a convincing case. water vapor presents another layer of complexity. Every habitable planet should have water in its atmosphere, but how much? Too little suggests a dry world with limited liquid water on the surface. Too much might indicate a runaway greenhouse effect, where oceans evaporate and the planet becomes Venus-like. The amount of water vapor, its distribution through the atmosphere, and how it changes with planetary seasons all provide clues about surface conditions. Clouds complicate everything. They block light, making it harder to analyze atmospheric composition beneath them. They reflect starlight, changing how bright the planet appears during transit. They form at different altitudes depending on temperature and pressure, creating layers that absorb different wavelengths. A planet with permanent cloud cover might hide its most interesting features. Scientists develop techniques to peer through clouds, using wavelengths less affected by water droplets or ice crystals, but every cloud layer reduces the quality of data collected. TRAPPIST-1's variability adds another challenge. The star dims and brightens as dark spots rotate across its surface. It produces flares that temporarily increase its brightness. These changes affect how much light reaches each planet and how that light interacts with planetary atmospheres. When the star flares, it pumps extra energy into the upper atmosphere, potentially driving chemical reactions that wouldn't normally occur. To identify biosignatures, scientists must separate signals caused by stellar activity from signals caused by planetary processes. This requires observing the system repeatedly over months and years. A single transit shows what the atmosphere looks like at one moment. Multiple transits reveal patterns. Does the atmospheric composition change with seasons? Does it respond to stellar flares in predictable ways? Does it remain stable over time, suggesting established cycles rather than temporary events? Only long-term monitoring answers these questions. The inner planets, especially TRAPPIST, 1b and c, face the harshest conditions. They orbit so close that stellar radiation strips away their atmospheres over geological timescales. Computer models show that planets this close to active red dwarfs lose massive amounts of atmosphere, potentially evaporating entire oceans worth of water into space. Yet these planets might retain thick atmospheres if they started with enough volatile material. Or they might be airless rocks, stripped bare billions of years ago. Webb's first observations of TRAPPIST, 1b suggested minimal atmosphere, but the data wasn't conclusive. The planet absorbed light consistent with bare rock, but certain atmospheric compositions could produce similar results. Carbon dioxide-rich atmospheres without clouds might appear nearly identical to no atmosphere at all. Distinguishing between these scenarios requires additional observations at different wavelengths, building a complete picture of what light the planet absorbs and reflects. TRAPPIST, 1c showed slightly more promise. Observations hinted at possible atmospheric features, though again, the data remained ambiguous. The challenge with these inner planets isn't just detecting atmospheres. It's determining whether any detected atmosphere is primordial, left over from the planet's formation, or secondary, produced by volcanic outgassing after the primordial atmosphere was lost. A secondary atmosphere would indicate ongoing geological activity, which requires internal heat. Internal heat suggests a molten core, which could generate magnetic fields, which might protect against stellar radiation. The middle planets, TRAPPIST, 1d, e, and f, occupy the sweet spot where temperatures could allow liquid water. Computer models place them in or near the habitable zone, but models depend on assumptions. How reflective is the surface? How much greenhouse warming occurs? What's the atmospheric composition? Small changes in these parameters shift the habitable zone boundary significantly. A planet right at the edge might be habitable or frozen depending on factors we haven't measured yet. TRAPPIST-1e draws particular attention because it receives stellar energy similar to what Earth receives from the Sun. Its size and density closely match Earth's. Its orbital period of 6 days means it's tidally locked, with one side permanently facing the star and the other in eternal darkness. This creates extreme temperature gradients that drive powerful atmospheric circulation. Air heated on the day side rises and flows toward the night side, where it cools and sinks, creating planet-wide wind patterns unlike anything Earth experiences. These winds might actually help maintain habitable conditions. They transport heat from the scorched day side to the frozen night side, moderating temperatures across the planet. Without this heat redistribution, the day side might be too hot for liquid water while the night side freezes solid. But with strong enough winds, a band of moderate temperature could exist between the two extremes, possibly sustaining liquid water in a ring around the terminator, the boundary between day and night. Testing this hypothesis requires measuring how temperature varies across the planet's surface. As TRAPPIST-1e orbits, different parts of its surface face Earth. By observing how much infrared light the planet emits during different parts of its orbit, scientists can map temperature variations. A planet with strong heat redistribution shows less temperature variation than one without. These observations are challenging because the planet is small and the temperature difference is subtle, but Webb's infrared instruments are designed precisely for this work. Tidal locking also affects magnetic fields. Earth's magnetic field comes from its rotating molten core. TRAPPIST-1e doesn't rotate relative to its star, though it does rotate once per orbit relative to the rest of the universe. Whether this slower rotation can sustain a magnetic field remains uncertain. Some models suggest yes, others no. Without a magnetic field, stellar wind and radiation could strip the atmosphere over time. Detecting or ruling out magnetic fields on exoplanets requires observing how stellar wind interacts with the planet, looking for signatures of deflection that would indicate a protective magnetic bubble. The possibility of moons adds another variable. Earth's moon stabilizes our planet's axial tilt, preventing wild climate swings. It drives tides that might have been important for the origin of life. TRAPPIST-1's planets could have moons, though detecting them is nearly impossible with current technology. A large moon would affect the planet's orbit in measurable ways, creating tiny variations in transit timing that repeat with the moon's orbital period. Searching for these signals requires years of precise observations and sophisticated data analysis. Water worlds represent another scenario that might exist at TRAPPIST-1. If a planet formed farther from the star and migrated inward, it might have started as an icy body that melted as it entered warmer regions. The result would be a planet with global oceans potentially hundreds of kilometers deep, with no exposed land. Such planets might be common around red dwarfs, and they present unique habitability questions. Deep oceans with no seafloor contact limit the availability of nutrients. On Earth, life depends on cycles that involve both land and sea. Minerals weather from rocks, wash into oceans, and feed marine ecosystems. A water world lacks this cycle. Life might still exist near hydrothermal vents on the ocean floor, similar to Earth's deep-sea ecosystems, but it would face constraints. Whether complex life could evolve under these conditions remains speculative. High-pressure ice adds another twist. At sufficient depth, water pressure becomes so intense that water molecules form exotic ice structures that remain solid despite warm temperatures. A water world might have a liquid ocean layer sitting atop a thick shell of high-pressure ice, which itself rests on a rocky core. This creates isolated environments. Life in the upper ocean couldn't access nutrients from the core. Life near the core couldn't access energy from the star. Understanding whether such planets exist at TRAPPIST-1 requires measuring their densities precisely and modeling their internal structures. The outermost planet, TRAPPIST-1H, remains the least studied. It orbits every 20 days, making transits rare. Less data means less certainty about its properties. It might be a frozen world, or it might receive enough tidal heating from gravitational interactions with other planets to maintain subsurface liquid. Each observation slowly fills in details, but years of work remain before we understand this distant member of the system. The search for life doesn't stop at finding water or oxygen. Those are starting points, not conclusions. Life leaves traces beyond basic chemistry. On Earth, organisms have transformed the planet's surface in ways detectable from space. Forests change reflectivity. Phytoplankton alter ocean color. Seasonal cycles create patterns. Cities glow at night. Finding life on TRAPPIST-1's planets won't come from a single measurement, but from accumulating evidence that something beyond geology and chemistry is happening. Biosignatures fall into categories. Atmospheric biosignatures involve gases that shouldn't persist without constant replenishment. Oxygen is one example, but it's not the only one. Methane in the presence of oxygen is intriguing because these gases react and destroy each other on geological timescales. Finding both together suggests something continuously produces them. On Earth, that something is life. Microbes produce methane. Plants produce oxygen. Together they create an atmospheric imbalance. Surface biosignatures involve changes visible when observing the planet's surface. Vegetation reflects infrared light differently than bare rock or water. This creates a signature called the red edge, named for the sharp increase in reflectivity at specific wavelengths. Detecting this requires observing the planet as it rotates, watching how light changes as different regions face the observer. Seasonal biosignatures involve patterns that repeat with the planet's orbit. If TRAPPIST-1e has seasons, vegetation might grow and recede, changing the planet's appearance. Monitoring this requires observations spread across multiple orbits, watching for repeated patterns that match environmental cycles. But every biosignature has false positives. Oxygen can come from water molecules breaking apart under ultraviolet light. Methane seeps from geological processes. Surface changes might be dust storms or ice formation. Seasonal patterns could be atmospheric circulation. The challenge is distinguishing biology from everything else. This requires multiple independent measurements. If oxygen appears alongside other gases in unusual ratios, if surface features change in ways consistent with growth rather than weather, if patterns persist across years in stable configurations, the case for life strengthens. No single observation proves anything. The weight of evidence accumulates. Technosignatures represent another approach. Rather than searching for life's chemical traces, we look for technology. Radio signals, laser pulses, atmospheric pollution from industrial processes, structures large enough to see from interstellar distances. This assumes life not only exists but has developed technology. That's a much stronger assumption than looking for microbes, but it has advantages. Technology produces signals far stronger than biology. A radio transmitter can outshine a star at specific frequencies. Industrial pollution creates atmospheric signatures unlike anything natural. The challenge is knowing where to look and what to look for. TRAPPIST-1's proximity makes it an obvious target. The Breakthrough Listen initiative has already scanned these planets for radio signals. So far, nothing. But absence of evidence isn't evidence of absence. Maybe they don't use radio. Maybe they do, but we haven't listened at the right time or frequency. Maybe technology is rare. Maybe it's common, but civilizations don't last long enough to overlap with our listening period. Contamination concerns work both ways. When humans eventually send probes to other star systems, we risk contaminating those worlds with Earth life. Hardy microbes could survive spaceflight. If they reach a habitable planet, they might multiply, potentially destroying or altering native ecosystems before we even know those ecosystems exist. Planetary protection protocols exist to prevent this, but they're designed for solar system exploration. Interstellar missions face different challenges. Travel times span decades or centuries. Sterilization must last that long. We also worry about contaminating our own measurements. If we send a probe that lands on TRAPPIST-1e and later detects organic molecules, how do we know those molecules weren't brought from Earth? Future missions will require extreme care in design, construction, and operation to ensure any discoveries are real. Time introduces profound complications. TRAPPIST-1's life takes 40 years to reach us. When we observe these planets, we see them as they were 4 decades ago. If we detect a biosignature today, it represents life that existed when humanity had just begun studying exoplanets. If we send a signal and receive a reply, nearly a century passes. This delay affects how we plan observations and interpret results. It also raises philosophical questions. What if life existed but went extinct? What if it's about to emerge but hasn't yet? We're looking at a snapshot, not a live feed. Everything we learn is historical. The TRAPPIST-1 system's age matters too. The star is roughly 8 billion years old, nearly twice the Sun's age. Life on Earth appeared within the first billion years after the planet formed. If the same happened at TRAPPIST-1, life there has had billions of years longer to evolve. This cuts both ways. More time means more opportunity for life to arise, adapt, and diversify. But it also means more time for catastrophes. Asteroid impacts, stellar flares, atmospheric loss, any number of events could have wiped life out multiple times. Ancient systems might be graveyards. Or they might host biospheres far more complex than Earth's, with ecosystems that ever find themselves across eons of selection and adaptation. Comparing timelines between systems reveals how contingent everything is. Earth's history includes 5 major mass extinctions, countless minor ones, and several near-total sterilizations. Each reset evolution's progress. If TRAPPIST-1's planets experienced fewer catastrophes, life might be more advanced. If they experienced more, it might be simpler or absent. We have no way to predict this without observing. The Fermi paradox looms over all discussions of life beyond Earth. If planets are common and life arises readily, where is everyone? Why don't we see evidence of civilizations? TRAPPIST-1 offers a test case. If we search thoroughly and find nothing, that tells us something about how rare or fragile complex life is. If we find microbes but no technology, that suggests biological life is common but technological civilizations are rare. If we find both, it challenges our assumptions about how often intelligence emerges. Observation strategies continue evolving. Early work focused on basic planet detection and characterization. Current efforts target atmospheric composition. Future missions will map surfaces, search for seasonal changes, and monitor long-term atmospheric stability. Each generation of instruments reveals new details. Webb's observations will continue for years, building datasets that allow comparison across seasons and orbits. Ground-based telescopes, especially the upcoming extremely large telescopes, will complement space observations. These giant instruments, with mirrors 30 to 40 meters across, can detect faint atmospheric signals Webb might miss. They'll also observe at different wavelengths, providing independent measurements. Direct imaging remains a distant goal. Current instruments can't separate a planet's light from its star's glare except in rare cases involving young, hot planets orbiting far from bright stars. TRAPPIST-1's planets are too close and too cool for this technique. But future technologies might succeed. A space telescope equipped with a star shade, a precisely positioned screen that blocks starlight while allowing planet light through, could image these worlds directly. This would reveal surface features, cloud patterns, and possibly even continents and oceans. Such missions are being designed now but won't launch for decades. When they do, TRAPPIST-1 will be among the first targets. Sample return missions, though far beyond current capability, represent the ultimate goal. A probe that travels to TRAPPIST-1, lands on a planet, collects samples, and returns to Earth would answer questions no remote observation can. It would take centuries with current propulsion technology. Faster systems are theoretical. Breakthrough Starshot proposes using powerful lasers to accelerate tiny probes to 20% of light speed, reducing travel time to 40 years. These probes couldn't slow down or return, but they could transmit data during a brief flyby. Even this ambitious concept faces enormous engineering challenges. Whether it's practical remains uncertain. Regardless of technical hurdles, the scientific motivation is clear. TRAPPIST-1 offers the best near-term opportunity to answer whether life exists beyond Earth. The discovery of this system changed how we think about planetary systems. Before TRAPPIST-1, we knew planets could orbit red dwarfs, but we didn't expect systems this compact or this rich. Its existence suggests similar systems are common. Thousands of red dwarfs lie within 100 light-years. If even a fraction host planet systems like TRAPPIST-1, nearby habitable worlds might number in the hundreds. This changes the scale of the search. We're not looking for rare exceptions but for common outcomes of planet formation. The question shifts from whether habitable planets exist to which ones host life. Cultural impact extends beyond science. TRAPPIST-1 appears in fiction, art, and public imagination as a symbol of possibility. It represents a place we can almost touch, close enough that future generations might visit, real enough that we can study it seriously. Unlike vague discussions of life in the universe, TRAPPIST-1 is specific. It has coordinates. It has planets with names. It has properties we can measure. This concreteness makes the search for life feel tangible rather than abstract. When we ask whether life exists elsewhere, we can point to an actual place and say, we're checking there. The answer matters not just scientifically but philosophically. Finding life would confirm we're not alone. Finding nothing would raise questions about how rare life is and whether intelligence is a cosmic accident. Either way, the search itself transforms us. The process of looking forces us to confront assumptions about life's requirements, challenges our understanding of habitability, and tests the limits of our technology. Every observation teaches us something new, whether or not we find what we're searching for. The data we collect today forms the foundation for discoveries decades from now. Results from Webb's observations won't arrive in a single dramatic announcement. Science rarely works that way. Instead, papers will appear describing atmospheric compositions, temperature structures, and chemical inventories. These technical reports will gradually build a picture of what these worlds are actually like. Some findings will exclude certain possibilities. If a planet shows no water vapor, we'll know its surface is dry. If another shows abundant methane without oxygen, we'll know it's not Earth-like. Negative results matter as much as positive ones. They narrow the search space and guide future observations. Other findings will open new questions. Detecting unexpected molecules might indicate processes we don't understand. Seeing atmospheric patterns that change with time could reveal weather systems or seasonal cycles. Each answer generates new questions, pushing the investigation deeper. The real challenge lies in interpretation. Atmospheric chemistry is complex. The same molecule can form through biological or geological processes. Oxygen, often considered a biosignature, can be produced without life through water vapor dissociation if ultraviolet radiation is strong enough. Methane can emerge from volcanic activity or serpentinization, a chemical reaction between water and certain rocks. Distinguishing between these scenarios requires careful modeling and multiple lines of evidence. Context matters enormously. A small amount of oxygen might be geological noise. Large amounts combined with methane would be harder to explain without life. Phosphine, a molecule that breaks down quickly, would be especially interesting because it needs constant replenishment. On Earth, life produces it. Whether geological processes can generate significant quantities remains debated. Finding it on TRAPPIST-1e would trigger intense scrutiny and follow-up observations. Temperature measurements provide crucial context for interpreting chemistry. If a planet's surface is too hot, water can't remain liquid. If it's too cold, life as we know it can't function. Webb can estimate surface temperatures by measuring thermal emission, the infrared glow objects emit based on their heat. Comparing these temperatures to models tells us weather conditions allow liquid water. Clouds complicate this analysis. They reflect starlight and trap heat, altering surface temperatures in ways that depend on their altitude, composition, and coverage. Thick cloud decks might make a planet's surface warmer than expected, while high thin clouds could cool it. Detecting clouds requires observing how a planet's brightness changes at different wavelengths. Water clouds scatter blue light more than red. Sulfuric acid clouds behave differently. By measuring these spectral signatures, we can infer cloud properties. This matters because clouds affect habitability. Too much cloud cover blocks starlight, reducing photosynthesis. Too little allows harmful radiation to reach the surface. The right amount creates a stable climate. Magnetic fields play a role we can't yet measure directly but must infer. A planet's magnetic field shields its atmosphere from stellar wind, streams of charged particles that erode atmospheres over time. Earth's magnetic field protects our atmosphere. Mars lost most of its atmosphere because it lacks a strong field. Red dwarfs produce powerful flares that accelerate atmospheric loss. Without magnetic protection, even a planet in a habitable zone might lose its atmosphere within hundreds of millions of years. Whether TRAPPIST-1's planets have magnetic fields depends on their internal structure. Planetary magnetic fields are generated by liquid metal cores churning through convection. This requires a planet to be large enough to stay geologically active and have the right composition. TRAPPIST-1e and F might meet these criteria. The others might not. Tidal heating, caused by gravitational squeezing as planets orbit, could keep interiors molten even if they'd otherwise cool. This might generate magnetic fields where they wouldn't normally exist. We won't know until we develop techniques to detect planetary magnetic fields remotely. One proposed method involves measuring how stellar wind particles interact with a planet's magnetosphere, creating radio emissions we could detect. This technology doesn't exist yet but could emerge within decades. Tidal locking introduces unique challenges and opportunities. If these planets always show the same face to their star, they experience permanent day on one side and permanent night on the other. Heat distribution becomes critical. Without efficient atmospheric circulation, the day side could be too hot while the night side freezes solid. Water would evaporate on one side and condense as ice on the other, eventually leaving the planet dry. But if the atmosphere is thick enough, winds could transport heat from day to night, creating a habitable twilight zone between extremes. This band, where temperatures remain moderate, might be the most favorable region for life. Ocean worlds would handle tidal locking differently. Water's high heat capacity allows it to store and transport thermal energy efficiently. Global oceans could circulate heat around the planet, preventing extreme temperature differences. This makes ocean worlds potentially more stable than rocky planets with thin atmospheres. Whether TRAPPIST-1's planets have global oceans depends on their formation history and subsequent evolution. If they formed beyond the snow line and migrated inward, they might have started water-rich. Subsequent atmospheric loss and surface processes would determine how much water remains today. Geological activity offers another piece of the habitability puzzle. Active geology recycles nutrients, releases gases that replenish atmospheres, and creates diverse environments. Volcanism on Earth releases carbon dioxide, which regulates climate over geological timescales. Without volcanism, carbon dioxide gets locked in rocks and the greenhouse effect weakens, eventually making the planet too cold. Plate tectonics, Earth's system of moving crustal plates, drives this recycling. Whether small planets can maintain plate tectonics is uncertain. Earth might be near the lower size limit for this process. TRAPPIST-1's planets, being slightly smaller, might not have plate tectonics. But they could have other forms of geological activity. Stagnant lid tectonics, where a single rigid crust covers a convecting interior, could still drive volcanism. Tidal heating from gravitational interactions with neighboring planets could provide additional energy for geological processes. This might keep smaller planets active longer than they'd otherwise remain. Biosignatures fall into several categories. Gas phase biosignatures are molecules in the atmosphere that life produces. Oxygen, methane, and phosphine are examples. Surface biosignatures are features visible on a planet's surface that indicate life, such as vegetation's distinctive reflectance spectrum. Temporal biosignatures are changes over time that suggest biological cycles, like seasonal variations in atmospheric composition. Each type requires different observation techniques. Gas phase biosignatures are most accessible now because we can study them through transit spectroscopy. Surface biosignatures need direct imaging, which isn't yet possible for these planets. Temporal biosignatures require long-term monitoring, observing the same planet repeatedly over months or years to detect changes. Webb can provide some temporal coverage, but dedicated missions would do better. False positives remain a serious concern. A false positive occurs when we detect something that looks like a biosignature but actually has a non-biological origin. This could mislead us into announcing the discovery of life when none exists. The scientific community would require extraordinary evidence before making such a claim. Multiple independent observations, thorough modeling to rule out non-biological explanations, and peer review by experts would all be necessary. Even then, uncertainty would remain until we could study the planet more directly. False negatives are equally important. A false negative happens when life exists but we fail to detect it. This could occur if life uses biochemistry different from Earth's, producing molecules we don't recognize as biosignatures. It could also happen if life exists but doesn't produce detectable atmospheric signatures, perhaps because it's confined to subsurface oceans or exists in small quantities. We might miss life simply because we're not looking in the right way. The possibility of non-Earth-like life expands the search dramatically. All our biosignature concepts are based on Earth life, which uses carbon-based chemistry, liquid water, and specific metabolic pathways. Life elsewhere might work differently. Silicon-based biochemistry, liquid methane as a solvent, or completely different metabolic processes could exist. We wouldn't recognize these as biosignatures because we don't know what to look for. This limitation means our search is biased toward finding life like ours. We might fly right past evidence of alien life without recognizing it. Addressing this requires creativity and open-mindedness. Some researchers propose looking for disequilibrium rather than specific molecules. Disequilibrium occurs when atmospheric chemistry is out of balance, with reactive gases coexisting when they should react and disappear. On Earth, oxygen and methane shouldn't coexist because they react chemically. They do because life constantly produces both. Detecting similar disequilibria elsewhere might indicate life even if the specific molecules differ from Earth's biosignatures. Artificial intelligence and machine learning are being applied to biosignature detection. These algorithms can analyze vast datasets, identifying patterns humans might miss. They can also model thousands of possible atmospheric compositions, helping distinguish biological from geological signatures. Training these systems requires careful work. They learn from examples, so if we only show them Earth-like biosignatures, they'll only recognize those. Expanding their training to include hypothetical non-Earth biochemistries improves their flexibility. As these tools mature, they'll become essential for processing the enormous amounts of data future telescopes will collect. Human intuition and machine analysis will work together, each compensating for the other's weaknesses. The timeline for answers stretches across decades. Webb's observations will continue for years, gradually building a comprehensive picture of TRAPPIST-1's planets. Follow-up missions will launch in the 2030s and 2040s, each more capable than the last. By mid-century, we might have definitive answers about whether these worlds host life. Or we might find the question is more subtle than we expected, requiring even more sophisticated observations. Either outcome advances our understanding. The search for life around TRAPPIST-1 sits within a broader revolution in how we understand planets and their potential for habitability. 50 years ago, we knew of no planets beyond our solar system. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. This explosion of discovery fundamentally changed our perspective. Planets aren't rare cosmic accidents. They're the natural outcome of star formation, appearing around most stars we examine closely enough. Rocky planets in particular seem common, suggesting the raw materials for life are widespread throughout the galaxy. TRAPPIST-1's system represents something special within this abundance. Most exoplanets we've found orbit much hotter stars than TRAPPIST-1. Hot stars age quickly and emit intense radiation that can strip planetary atmospheres. They also produce more ultraviolet light, which damages biological molecules. TRAPPIST-1's cool, stable nature provides a gentler environment. Its planets won't face the radiation bombardment that plagues worlds around hotter stars. The star will shine for trillions of years, far longer than our sun's remaining lifespan. If life needs time to evolve complexity, TRAPPIST-1 offers nearly unlimited patience. The system's architecture also matters. Having 7 planets packed so closely creates gravitational interactions that could prove beneficial. Tidal forces from neighboring planets might generate internal heating, keeping subsurface oceans liquid even on worlds that receive little starlight. This expands the habitable zone beyond simple calculations based on surface temperature. A planet might look too cold to support life when considering stellar radiation alone, yet maintain liquid water underground through tidal heating. Europa and Enceladus in our solar system demonstrate this principle. Both moons orbit far from the Sun where surface temperatures plunge below -100 degrees Celsius, yet both harbor subsurface oceans kept liquid by tidal flexing. TRAPPIST-1's planets might experience similar conditions, creating multiple environments where life could emerge and persist. Understanding these worlds requires thinking beyond Earth-based assumptions. Our planet's history shapes how we imagine habitability. We picture continents and oceans, a nitrogen-oxygen atmosphere, and a protective magnetic field. But these features aren't universal requirements. Venus-like worlds with crushing atmospheric pressure and sulfuric acid clouds seem hostile, yet life adapted to those conditions would thrive. Ocean worlds with no land whatsoever could support rich biospheres beneath kilometers of water. Planets with thin atmospheres and low gravity might develop life in underground caves where conditions remain stable. The challenge lies in recognizing life's signatures when they emerge from these alien contexts. We're building a library of possibilities, modeling how different planetary conditions produce different atmospheric chemistries. This library will help interpret observations when we finally collect them. If we detect an atmosphere that doesn't match any known geological process but fits a biological model, we'll have found something significant. The strength of that claim depends on how thoroughly we've ruled out alternatives. Geology can mimic biology in frustrating ways. Volcanic outgassing produces many of the same molecules life creates. Lightning can generate complex organic compounds without any biological involvement. Photochemistry driven by stellar ultraviolet light creates chemical reactions that might look like metabolism. Distinguishing true biosignatures from these false positives requires detailed modeling and multiple lines of evidence. No single observation will suffice. We need patterns, consistency across different measurements, and explanations that make sense given what we know about the planet's geology and atmospheric physics. The scientific method demands skepticism. When we think we've found something extraordinary, we must work harder to disprove it than to confirm it. This approach frustrates those who want quick answers, but it protects against embarrassment and ensures that when we do announce a discovery, it stands on solid ground. The search for life around TRAPPIST-1 will proceed with appropriate caution. Future missions will expand our capabilities dramatically. Concepts under development include star shades, massive spacecraft that fly in formation with telescopes, blocking starlight to reveal faint planets more clearly. Interferometry, combining light from multiple telescopes to create a virtual instrument larger than any single telescope could be, will provide unprecedented resolution. Direct imaging missions could photograph TRAPPIST-1's planets as distinct points of light rather than inferring their properties indirectly. Each technological advance brings us closer to definitive answers. Ground-based telescopes continue improving as well. Extremely large telescopes currently under construction will have mirrors 30 meters across, dwarfing today's largest instruments. Adaptive optics systems correct for atmospheric distortion in real time, sharpening images to approach theoretical limits. These facilities will contribute to TRAPPIST-1 studies, particularly for longer-term monitoring and follow-up observations of interesting findings from space telescopes. The combination of space and ground-based observations creates a comprehensive picture. Space telescopes avoid atmospheric interference but have limited lifespans and can't be easily upgraded. Ground-based telescopes can be maintained and improved indefinitely but must contend with Earth's atmosphere. Using both together compensates for each approach's limitations. We're entering an era where planetary characterization becomes routine rather than exceptional. TRAPPIST-1 won't be studied in isolation but as part of a broader sample of potentially habitable worlds. Comparative planetology, examining many similar worlds to understand common patterns and unique variations will reveal which planetary characteristics matter most for habitability. Does magnetic field strength correlate with atmospheric retention? Do planets with active plate tectonics develop more complex biosignatures? Does the presence of a large moon stabilize climate in ways that benefit life? These questions require large samples. TRAPPIST-1 provides 7 data points in a single system, making it invaluable for testing hypotheses about planetary habitability. Public interest in these discoveries remains intense. Each announcement about TRAPPIST-1 generates global attention. This enthusiasm reflects humanity's deep curiosity about our place in the universe. Are we alone? The question resonates across cultures and throughout history. Modern science finally has tools to answer it. The results will reshape philosophy, religion, and our understanding of life's significance. Finding life elsewhere, even simple microbial life, would demonstrate that biology emerges readily when conditions permit. This would suggest the universe teems with life, most of it probably simple, but some fraction potentially complex or even intelligent. Not finding life would also teach us something important. If we examine dozens of seemingly habitable worlds and detect no biosignatures, we'd need to reconsider our assumptions. Perhaps life requires conditions rarer than we thought. Perhaps the transition from chemistry to biology involves improbable steps. Perhaps life emerges commonly but rarely persists long enough to produce detectable signatures. Each null result narrows the range of possibilities, guiding future searches toward more promising targets. The TRAPPIST-1 system will remain a focus of astrobiology for generations. Its proximity, the number of potentially habitable planets, and the relatively easy observing conditions make it an ideal laboratory for testing our methods and assumptions. Whatever we learn there will inform searches around other stars, building a framework for understanding planetary habitability across the galaxy. This knowledge serves practical purposes beyond satisfying curiosity. As we contemplate humanity's long-term future, the question of where else we might live becomes increasingly relevant. Understanding which worlds could support life helps identify potential destinations for future exploration or even colonization. These considerations remain distant, but they motivate current research. We study TRAPPIST-1 not just to find life elsewhere but to understand life's requirements and possibilities. This understanding might one day help us recognize or even create habitable conditions on worlds that initially seem barren. The line between studying exoplanets and studying Earth blurs as we realize the same principles govern both. Atmospheric chemistry, climate dynamics, and the interplay between geology and biology operate by universal physical laws. Insights gained from examining TRAPPIST-1 improve our understanding of our own planet's history and future. Climate science benefits particularly from exoplanet research. Studying worlds with different atmospheric compositions, stellar inputs, and planetary characteristics tests our climate models under extreme conditions. If our models accurately predict TRAPPIST-1's atmospheric behavior, we gain confidence in their predictions for Earth's changing climate. The exchange flows both ways. Our detailed knowledge of Earth's atmosphere and biosphere informs how we interpret observations of distant worlds. 40 light-years now feels simultaneously vast and intimate. Vast because even traveling at unrealistic speeds, reaching TRAPPIST-1 would take centuries. Intimate because we can study its planets in detail, watching their atmospheres change with seasons, measuring their compositions, and searching for signs of life. Technology has collapsed the observational distance even as the physical distance remains unbridgeable with current capabilities. We've become neighbors with TRAPPIST-1 in a way that would astonish astronomers from just decades ago. Their wildest dreams about characterizing distant worlds have become our routine observations. The next generation of instruments will push boundaries we can barely imagine today. What seems impossible now might become straightforward in 20 years. The pace of discovery accelerates as technology and understanding advance together. TRAPPIST-1's secrets will gradually yield to our persistent questioning, revealing whether those distant worlds harbor the universe's most profound mystery or remain silent, waiting for life to arrive from elsewhere. The answer matters less than the journey itself. We stand at a threshold previous generations could only imagine. 7 worlds orbit a dim star close enough to study yet far enough to remain mysterious. Whether they harbor life or stand barren, whether their atmospheres persist or have vanished, whether oceans cover their surfaces or ice locks their water away, each discovery reshapes what we know about planets, habitability, and our own existence. TRAPPIST-1 represents more than coordinates in space. It's a mirror reflecting our assumptions back at us, forcing us to confront what we think we know about life's requirements. Every observation challenges conventional thinking. Every measurement refines theories built on studying a single example, Earth. We're learning that planets don't follow simple rules, that habitability isn't binary, and that nature experiments with configurations we never anticipated. The telescopes currently pointed at this system will continue their work for years. Data accumulates slowly, each transit adding fragments to an incomplete picture. Future instruments will fill gaps, answer questions the current generation of telescopes can't address, and pose new mysteries we haven't yet imagined. The process feels frustratingly slow measured against human lifespans, but it's remarkably fast compared to the billions of years these worlds have existed. What we find at TRAPPIST-1 will influence how we search elsewhere. If red dwarf planets retain atmospheres despite stellar violence, thousands of nearby systems become prime targets. If they don't, our focus shifts to rarer, sun-like stars. Either way, we gain knowledge that directs future efforts and resources. The search expands or contracts based on what these 7 planets reveal about planetary survival around the galaxy's most common stellar type. Somewhere in the accumulated observations, patterns will emerge. Atmospheric compositions that make sense given the planet's histories. Temperature distributions that reveal how energy moves through alien air. Chemical signatures that either suggest biology or don't. The absence of life matters as much as its presence. Both outcomes advance understanding. Both guide the next phase of exploration. We're no longer wondering whether other worlds exist. We're studying specific places, measuring their properties, and determining whether they could host life. This shift from philosophical speculation to empirical investigation represents one of science's great transitions. The question of whether we're alone moves from metaphysics to physics, from belief to data, from wondering to knowing. TRAPPIST-1's planets won't yield their secrets quickly or easily. They'll make us work for every answer, forcing us to build better instruments, develop more sophisticated models, and think more carefully about what constitutes evidence. This struggle drives progress. The harder the question, the more we learn in pursuing it. 40 light-years away, 7 worlds orbit a star that will outlive our sun by trillions of years. They've existed for billions of years already. They'll continue existing long after human civilization has transformed or disappeared. Right now, in this brief window of time, we're looking at them. We're measuring them. We're learning what they are and what they might become. The universe doesn't care whether we find life elsewhere. Planets orbit stars according to gravity's laws regardless of what we discover or conclude. But we care. The question drives us to build telescopes, launch missions, and spend decades analyzing data. It pushes our technology and understanding forward. And eventually, we'll know. Not through revelation or assumption, but through patient observation and careful analysis. TRAPPIST-1 will tell us its story. We just have to listen long enough to hear it. 4.2 light years. That's the distance to our nearest stellar neighbor, Proxima Centauri. In cosmic terms, it's practically next door. In human terms, it's an almost incomprehensible void. And orbiting that dim red star is a world that might harbor the answer to humanity's oldest question: are we alone? On August 24, 2016, scientists announced something extraordinary. They'd found a planet circling Proxima Centauri, tucked right inside the habitable zone where liquid water could exist. The media exploded with headlines about our nearest potentially habitable neighbor. But here's what most of those stories missed: this world might be hiding something far darker than anyone initially realized. Proxima Centauri b sits closer to its star than Mercury does to our Sun. It completes an orbit every 11 days, and despite being in the habitable zone, the conditions there might be so extreme, so utterly hostile, that the very concept of life becomes almost laughable. Let me show you why this discovery changed everything we thought we knew about habitable worlds. The story begins with a star that's been burning for billions of years, yet you'd never see it with your naked eye from Earth. Proxima Centauri is a red dwarf, a stellar ember that glows with barely 1/6 the temperature of our Sun. Its diameter? About 1/7 that of our home star, roughly 1.5 times Jupiter's width. Pack that mass into such a small volume and you get something remarkable: a mean density of 47 grams per cubic centimeter. Compare that to the Sun's density of just 1.4 grams per cubic centimeter. Red dwarfs are the universe's ultimate survivors. While our Sun will burn through its hydrogen fuel in roughly 5 billion years, red dwarfs like Proxima Centauri can keep fusing hydrogen for trillions of years. They're the cosmic equivalent of marathon runners, burning slow and steady while more massive stars sprint through their fuel and die young. But longevity comes with a price. The detection of Proxima Centauri b wasn't accomplished through direct observation. You can't simply point a telescope at the system and snap a photo. The star outshines its planet by a factor of 10 million to 1. Instead, scientists used something called radial velocity measurements. Picture this: as a planet orbits its star, it doesn't just circle around a stationary object. Both planet and star orbit their common center of mass. The star wobbles ever so slightly, pulled by the planet's gravity. That wobble shows up in the star's light. As Proxima Centauri moves toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. These shifts are incredibly tiny, measured in meters per second. The Pale Red Dot Project spent years carefully measuring these subtle changes in Proxima Centauri's light, filtering out the noise, accounting for the star's own variability. When the data finally came together, it revealed an unmistakable signal. A planet with a minimum mass of 1.06 Earth masses, orbiting every 11.2 days at a distance of about 0.05 astronomical units. The excitement was immediate and global. Here was a terrestrial world, roughly Earth's size, orbiting in the habitable zone of the closest star to our own. The implications seemed staggering. If life could exist there, we might actually be able to study it within our lifetimes, or at least within the lifetimes of our children or grandchildren. But let's talk about what reaching Proxima Centauri b would actually require. 4.2 light years translates to about 40 trillion kilometers. Our fastest spacecraft, Voyager 1, currently travels at 17 kilometers per second. Sounds fast until you do the math: 73,000 years to reach Proxima Centauri. That's longer than recorded human history. The New Horizons probe, which gave us those stunning images of Pluto, moves at 58,000 kilometers per hour. Still wouldn't get there for 80,000 years. Even theoretical fusion drives, the kind that might be possible within the next century, would need 36 years to make the journey. The Breakthrough Starshot initiative has proposed something more radical: ultra-lightweight probes with light sails, accelerated by powerful ground-based lasers to 20% the speed of light. At that velocity, the trip would take just over 20 years. 20 years to send a probe. Another 4 years for the signal to return to Earth. A generation-spanning project just to get our first close look at this world. And what would we find when we got there? The planet orbits 20 times closer to Proxima Centauri than Earth orbits the Sun. That tight orbit is necessary because red dwarfs emit far less energy than Sun-like stars. Despite this proximity, Proxima Centauri b receives only about 65% of the solar energy that Earth receives. Its equilibrium temperature, the temperature it would have without an atmosphere, sits at around -39 degrees Celsius. Cold. But potentially not too cold if the planet has the right atmospheric composition. A thick atmosphere with sufficient greenhouse gases could trap enough heat to maintain liquid water on the surface. Scientists have run countless climate models, feeding in different variables, varying amounts of water, carbon dioxide, nitrogen. The results span a remarkable range of possibilities. In some simulations, the planet is completely frozen, a snowball world where ice covers every surface. In others, it hosts a global ocean, dark and deep. Some models produce what researchers call an eyeball Earth, where one region of perpetual daylight stays warm enough for liquid water while the rest of the planet remains frozen. Picture a circular zone of habitability, surrounded by glacial wasteland. These different outcomes depend critically on factors we can't yet measure. How thick is the atmosphere? What's it made of? Is there water at all? The uncertainty in the planet's mass adds another layer of complexity. Radial velocity measurements can only tell us the minimum mass because they depend on how the planet's orbit is tilted relative to our line of sight. If we're looking at the orbit edge-on, we see the full wobble. If we're looking at it more face-on, the wobble appears smaller, and the planet could be more massive than it appears. Current estimates suggest Proxima Centauri b has a minimum mass of 1.06 Earth masses. But if the orbit is tilted at 47 degrees, coplanar with the star's rotation, the true mass would be closer to 1.44 Earth masses. That difference matters. A more massive planet would have stronger gravity, potentially holding onto its atmosphere more effectively. Or it might simply be a larger world with different geological activity. The formation history of this planet remains murky. Proxima Centauri itself might have been captured by the Alpha Centauri system, meaning it could be younger or older than its stellar companions, which are roughly 5 billion years old. If Proxima Centauri b formed in its current orbit, it would have experienced a hellish early environment. During the star's pre-main sequence phase, when it was much brighter and hotter, the habitable zone would have been farther out. For potentially 180 million years, the planet would have been too close to its star for water to exist as a liquid. Any water present would have evaporated into steam, which ultraviolet radiation would then split into hydrogen and oxygen. The hydrogen, being light, would escape to space. The oxygen might remain, but without hydrogen to bond with, there's no way to recreate water. This scenario resembles what scientists believe happened to Venus. Our sister planet likely had oceans early in its history. A runaway greenhouse effect boiled them away, leaving behind the toxic, superheated world we see today. Could Proxima Centauri b have suffered the same fate? The question of water loss leads us deeper into the planet's potential history. Models suggest the planet might have lost at least one Earth ocean's worth of water during its early years. Some estimates push that number much higher. Without water, the prospects for life dim considerably. But water loss isn't the only concern. There's another problem, one that cuts to the heart of whether this world could ever support life as we understand it. It involves the star's behavior, the planet's atmosphere, and a process of destruction that plays out over millions of years. This problem doesn't announce itself with dramatic headlines, but its implications might be even more devastating than simple water loss. Understanding this threat requires us to look more carefully at what happens when a planet orbits so close to its star, experiencing forces that Earth never encounters. The problem starts with tidal locking. When a planet orbits close enough to its star, gravitational forces act like brakes on its rotation. Over time, these forces slow the planet's spin until one side permanently faces the star while the other remains in perpetual darkness. Earth experiences a milder version of this effect with our moon, which always shows us the same face. The tidal force Proxima Centauri exerts on its planet is 939 times stronger than what the Sun exerts on Earth. That's not a force you can resist. Picture standing on Proxima Centauri B's surface. If you're on the day side, the star never moves in the sky. It hangs there, fixed, casting its dim red light across a landscape that never sees sunset. Walk to the other hemisphere and you enter permanent night, where stars will overhead in their familiar patterns but your own sun never rises. Between these extremes lies the terminator, the boundary zone where day meets night, where the star sits perpetually on the horizon. The consequences extend far beyond strange lighting. On the day side, temperatures soar as the star's radiation pummels the same hemisphere without pause. On the night side, temperatures plunge. Without the cycle of day and night to distribute heat, the planet develops extreme temperature gradients. Climate models suggest the day side could be hot enough to boil water while the night side freezes solid. Between these zones, violent winds would rage as air masses rush from hot to cold, trying desperately to equalize the temperature difference. But here's where things get strange. The night side wouldn't just be cold. It could become a graveyard for the atmosphere itself. As air cools, molecules slow down and lose energy. Cool them enough and gases begin to condense. Carbon dioxide, a common atmospheric component, freezes at -78 degrees Celsius. On a tidally locked world with no heat arriving on the night side, CO2 could literally fall out of the sky as snow, accumulating in massive glaciers of dry ice. The atmosphere would gradually migrate from the night side to the day side, thinning until the planet's air pressure drops to near vacuum levels. Unless something intervenes. A thick enough atmosphere could save the planet through heat transport. Air warmed on the day side would rise, flow toward the night side, cool, and sink, creating massive circulation cells that carry heat around the planet. Earth does this with its Hadley cells, the atmospheric circulation pattern that drives our trade winds. Proxima Centauri b would need something similar, but far more powerful. Climate models that simulate this scenario produce what scientists call an eyeball Earth. Picture a planet mostly covered in ice, with one circular region on the day side where temperatures stay above freezing. From space, it would look like an eye staring back at you, a warm pupil of liquid water surrounded by a white iris of ice. The terminator zone, that band between day and night, might offer the most stable conditions. Not too hot, not too cold. If life exists on this world, it might cling to this narrow strip. Yet tidal locking creates another problem that doesn't announce itself immediately. It concerns magnetic fields. Earth's magnetic field arises from our planet's rotation. As Earth spins, the liquid iron in its outer core churns and flows, generating electrical currents. These currents produce the magnetic field that shields us from solar wind and cosmic radiation. It's a dynamo powered by rotation. Proxima Centauri b rotates once every 11 days, synchronous with its orbit. That's slow. Extremely slow compared to Earth's 24-hour day. The question becomes whether such sluggish rotation can maintain a dynamo. Some models suggest it can't. Without rapid rotation, the currents in the planet's core might not achieve the organization needed to generate a strong magnetic field. Other factors complicate this further. Tidal heating from the star's gravitational pull could warm the planet's interior, potentially disrupting the precise conditions needed for a magnetic dynamo to operate. No magnetic field means no shield. And without a shield, the planet faces the full fury of its star. Proxima Centauri isn't a quiet, stable star like our Sun. It's a flare star, and the distinction matters enormously. Our Sun produces flares occasionally, brief eruptions of energy that can disrupt satellites and power grids. These events make headlines when they occur. Proxima Centauri produces similar events not once in a century, but multiple times per day. Some of these flares are among the most powerful ever recorded in our galaxy. On May 1, 2019, astronomers observed Proxima Centauri suddenly brighten. Over just 7 seconds, the star's ultraviolet output increased by a factor of 14,000. Jets of plasma erupted outward, carrying energy equivalent to 100 times the most powerful flares our Sun produces. The event lasted briefly, but its effects would ripple through the entire planetary system. 50 hours of observations using the Atacama Large Millimeter Array detected 463 separate flare events. Not over years. Over 50 hours. The flares ranged in energy from 10 to the 24th power ergs to 10 to the 27th power ergs. Each lasted between 3 and 16 seconds. The planet orbiting this star faces a barrage of high-energy radiation that makes Earth's environment look gentle by comparison. What happens when such radiation hits a planetary atmosphere? The atmosphere doesn't simply absorb it. High-energy ultraviolet photons carry enough energy to break molecular bonds. When UV light strikes a water molecule, it can split it apart into hydrogen and oxygen. The hydrogen, being light, escapes to space. The oxygen might remain, but without hydrogen to combine with, you can't remake water. Over time, the planet's water inventory decreases, molecule by molecule, until the oceans vanish. Nitrogen faces a similar threat. On Earth, nitrogen makes up 78% of our atmosphere. It's an inert background gas that provides atmospheric pressure and moderates temperature. But nitrogen isn't immune to escape. During periods of intense atmospheric loss, escaping hydrogen atoms can collide with heavier nitrogen atoms and drag them along through a process called hydrodynamic escape. Models suggest that several bars of nitrogen, enough to create an Earth-like atmospheric pressure, could be lost in just a few million years. NASA scientists ran a simulation. They placed Earth in Proxima Centauri B's orbit and watched what happened. The model showed Earth's atmosphere being stripped away 10,000 times faster than it loses atmosphere in its actual orbit around the Sun. 10,000 times faster. At that rate, an Earth-like atmosphere wouldn't last 10 million years. The planet would be left bare. The early history of Proxima Centauri B makes this scenario even more likely. During its pre-main sequence phase, before the star settled into stable hydrogen fusion, Proxima Centauri was much brighter and hotter. Its habitable zone lay farther out. If the planet formed in its current orbit, it would have spent approximately 180 million years too close to the star for water to remain liquid. Any water present would have boiled away. The resulting steam would have been broken apart by ultraviolet radiation, and the hydrogen would have escaped to space. This is the runaway greenhouse effect, the same process that transformed Venus from a potentially habitable world into the hellscape we observe today. Venus likely had oceans early in its history. The greenhouse effect boiled them away. The water split into hydrogen and oxygen. The hydrogen escaped. Now Venus has a thick atmosphere of carbon dioxide, surface temperatures hot enough to melt lead, and not a drop of water anywhere. Could Proxima Centauri be our nearest cosmic neighbor and simultaneously a dead world, stripped of its water before life ever had a chance to begin? The evidence points uncomfortably in that direction. Yet some possibilities remain. Perhaps the planet formed farther out and migrated inward after the star stabilized. Perhaps it had such an enormous initial water inventory that some survived despite massive losses. Perhaps a thick hydrogen envelope protected the planet during its early years, a scenario called the habitable evaporated core hypothesis. These scenarios require specific conditions, fortunate circumstances, a series of events that had to unfold in precisely the right order. The odds don't look favorable. But the universe is vast, and improbable things happen. The question becomes whether we can determine what actually occurred without going there, without directly observing this world that remains hidden in its star's glare. Observing this planet presents a challenge unlike almost any other in astronomy. Proxima Centauri outshines Proxima Centauri b by a factor of 10 million. 10 million to 1. The planet's reflected light drowns completely in the star's overwhelming glare. We can't see it directly. We know it exists only because its gravity tugs on Proxima Centauri as it orbits, creating a tiny wobble detectable through precise measurements of the star's spectrum. This wobble shifts the star's light toward the blue when the planet pulls it toward us, and toward the red when it pulls away. From these shifts, we calculate the planet's mass and orbit. But we learn nothing about its surface, its atmosphere, or whether water exists anywhere on it. The James Webb Space Telescope represents our best current hope for breaking through this observational barrier. Webb's infrared capabilities could detect heat signatures from the planet's surface, revealing temperature patterns that would tell us whether an atmosphere exists and how efficiently it transports heat. If the planet is tidally locked, the day side should be significantly warmer than the night side. Measuring this temperature difference would confirm the lock and provide crucial information about atmospheric thickness. A thin atmosphere can't move heat effectively. A thick one creates more uniform temperatures across the surface. The difference between these scenarios means the difference between a lifeless rock and a potentially habitable world. But here's the technical problem. Even Webb can't easily separate the planet's faint infrared glow from the star's light. The angular separation between Proxima Centauri and Proxima Centauri b, as seen from Earth, is incredibly small. Specialized techniques using coronagraphs or star shades, which block the star's light while allowing the planet's light through, might work. These methods have been used successfully on other exoplanets, but Proxima Centauri b presents unique difficulties because of its proximity to its host star. Future ground-based telescopes offer another approach. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter. This enormous light-gathering power, combined with adaptive optics that correct for atmospheric distortion, could achieve the contrast ratio necessary to directly image Proxima Centauri b. Direct imaging would allow spectroscopy, the analysis of light at different wavelengths to identify specific molecules in the planet's atmosphere. Water vapor, carbon dioxide, oxygen, methane. Each leaves a distinct fingerprint in the spectrum. Finding these molecules would transform our understanding of the planet's condition. Spectroscopy could reveal something unexpected. An oxygen-rich atmosphere on Proxima Centauri b wouldn't necessarily indicate life. On Earth, oxygen comes primarily from photosynthesis, making it a potential biosignature. But on a planet that lost its water through atmospheric stripping, oxygen could accumulate as a byproduct of water destruction. UV radiation splits water molecules. Hydrogen escapes. Oxygen, being heavier, remains behind. Over billions of years, this process could create an oxygen-rich atmosphere on a completely dead world. Scientists call this a false positive, a biosignature that doesn't actually indicate biology. Distinguishing between biological and abiological oxygen requires detecting other molecules simultaneously. Methane alongside oxygen suggests life, because these gases react with each other and shouldn't coexist unless something continuously produces them. The atmospheric models paint wildly different possible pictures of this world. If Proxima Centauri b is tidally locked with a thin atmosphere, most scenarios show an eyeball Earth configuration. One side faces the star perpetually. The intense radiation heats this region, potentially keeping a circular area of liquid water surrounded by ice that extends toward the night side. The night side itself remains frozen, possibly covered in thick ice sheets or even frozen nitrogen and carbon dioxide. The terminator, the boundary between day and night, might be the only temperate zone, a narrow ring where temperatures allow liquid water and where life, if it exists, would cluster. But this assumes the planet has water at all. The alternative scenario depicts something far bleaker. If atmospheric escape stripped away the oceans during the planet's early history, Proxima Centauri b might resemble Mars, a cold desert world with a thin atmosphere insufficient to support liquid water at any temperature. Surface pressure matters critically here. Water can't remain liquid below a certain atmospheric pressure regardless of temperature. On Mars, with surface pressure less than 1% of Earth's, liquid water is impossible except in the deepest depressions. If Proxima Centauri b lost most of its atmosphere, it lost the ability to host surface water even if some water ice remains underground. Another possibility involves a thick carbon dioxide atmosphere similar to Venus. If the planet retained significant volatiles but lost its water, carbon dioxide released from volcanic activity over billions of years could build up, creating a dense greenhouse atmosphere. Surface temperatures on such a world would be extreme, potentially reaching several hundred degrees Celsius. The pressure at the surface could be tens or even hundreds of times Earth's atmospheric pressure. This scenario creates a planet within the habitable zone by distance but rendered uninhabitable by its own atmospheric evolution. The magnetic field question adds another layer of uncertainty. Earth's magnetic field, generated by a dynamo in its liquid iron outer core, shields our atmosphere from the solar wind. Proxima Centauri b's rotation rate matters enormously for magnetic field generation. If the planet is tidally locked, rotating once every 11.2 days, this slow rotation might be insufficient to drive a dynamo. Without a magnetic field, the stellar wind hits the atmosphere directly. Charged particles strip away atmospheric molecules through a process called sputtering. The stellar wind at Proxima Centauri b's orbital distance is estimated to be 10 to 1,000 times denser than the solar wind at Earth's orbit. The pressure is roughly 10,000 times greater. This relentless bombardment, sustained over billions of years, would erode any atmosphere that isn't protected by a magnetic field or continuously replenished by volcanic outgassing. But rotation isn't the only factor determining magnetic field strength. Some planets generate fields through alternative mechanisms. Tidal heating, if the planet's orbit is slightly eccentric, could keep the interior molten and convecting even without fast rotation. Jupiter's moon Io demonstrates this principle. Io has intense volcanic activity driven entirely by tidal heating from Jupiter's gravity. If Proxima Centauri b experiences similar tidal forces, its interior might remain hot enough to generate a magnetic field despite slow rotation. This would provide crucial protection for any atmosphere. The uncertainty surrounding all these factors makes prediction nearly impossible. We're dealing with a system where every parameter influences every other parameter. The presence or absence of water affects atmospheric composition, which affects greenhouse heating, which affects temperature distribution, which affects whether water can remain liquid. The magnetic field affects atmospheric retention, which affects pressure, which affects whether liquid water is possible. The planet's formation history affects its initial volatile inventory, which affects everything that follows. We're trying to solve an equation with dozens of unknowns. What we need is direct observation. Not models, not simulations, but actual data from the planet itself. The technology to obtain this data is developing rapidly. Within the next decade, new telescopes and instruments will come online with capabilities specifically designed for characterizing nearby rocky exoplanets. Proxima Centauri b will be among the first targets. These observations won't be easy. Even with the best instruments, extracting a planetary signal from the overwhelming stellar glare requires sophisticated data processing and long observation times. But the payoff justifies the effort. Confirming the presence or absence of an atmosphere, detecting specific molecules, measuring surface temperature. Each piece of data narrows the range of possibilities and brings us closer to understanding what this world actually looks like. There's also the possibility of detecting technosignatures, signs of technology if an advanced civilization exists there. Radio telescopes have searched for artificial signals from Proxima Centauri. So far, they've found nothing. But absence of evidence isn't evidence of absence. A civilization using technologies we haven't imagined wouldn't produce the radio signatures we're looking for. Or perhaps they exist but aren't broadcasting. Or perhaps they existed in the past and are now gone. Or perhaps they never arose at all because the planet's conditions proved too hostile for complex life to develop. The distance to Proxima Centauri, while vast by human standards, is tantalizingly close in cosmic terms. 4.2 light-years. If we could send a probe there, traveling at 20% light speed as proposed by the Breakthrough Starshot initiative, it would arrive in approximately 21 years. The engineering challenges are immense. Accelerating a spacecraft to that velocity requires lasers far more powerful than anything currently built. The probe would need to be incredibly small and light, essentially a computer chip with a light sail. It couldn't carry much scientific equipment. And it couldn't slow down upon arrival, meaning it would have only a brief window to gather data as it flew past at tremendous speed. But imagine what that flyby could reveal. Direct images of the planet's surface. Measurements of its magnetic field. Spectroscopic analysis of its atmosphere from close range. Confirmation of whether oceans exist. Detection of biological or geological activity. 21 years to reach it. 21 more for the data to return to Earth. 42 years total. Long by human timescales, but achievable within a single lifetime. The people who launch such a mission could live to see its results. Until we actually visit Proxima Centauri b, however, all this remains theoretical. The reality check comes when you consider the sheer engineering difficulty of getting there. Even Breakthrough Starshot, the most ambitious proposal currently under serious consideration, faces challenges that make building the James Webb Space Telescope look straightforward. You need a laser array powerful enough to accelerate a grand-scale spacecraft to 60 million meters per second. That's not just powerful. It's apocalyptically powerful. The combined laser output would need to reach something like 50 to 100 gigawatts, focused with extraordinary precision onto a sail measuring only a few meters across. At full power, this laser system would be visible from Proxima Centauri itself. An alien civilization there with telescopes pointed our way would see a bright flash from Earth lasting several minutes as the acceleration phase completed. They'd know something had just been launched toward them. The spacecraft itself couldn't carry much instrumentation. At those velocities, hitting a dust grain delivers energy equivalent to an exploding hand grenade. The craft needs shielding, but shielding adds mass, and mass is the enemy of acceleration. Every gram counts. You're essentially trying to pack scientific instruments, power systems, communication equipment, and shielding into something weighing less than a postage stamp. And there's no slowing down. The craft would scream past Proxima Centauri b at 20% light speed, crossing the entire planetary system in minutes. Whatever data gets collected must be transmitted back to Earth during that brief window, across 4.2 light-years of space, using a transmitter powered by something smaller than your phone. The technical problems multiply the more you examine them. Interstellar space isn't empty. It contains hydrogen atoms, maybe 1 per cubic centimeter. At 20% light speed, those atoms hit with the energy of radiation. The accumulated dose over 4.2 light-years would destroy most electronics unless heavily shielded, which again adds mass. Cosmic rays present another hazard. High-energy particles from distant supernovae and active galactic nuclei constantly bombard the spacecraft. One unlucky hit to a critical component ends the mission. With such a tiny craft, redundancy is nearly impossible. Then there's aiming. At 20% light speed, the spacecraft crosses the distance to the Moon in about 6 seconds. A targeting error of 1 degree means missing Proxima Centauri b by millions of kilometers. Course corrections during flight require propulsion systems, which add mass and complexity. The laser acceleration phase must be extraordinarily precise. Communication presents its own nightmare. The data transmission from the flyby travels back to Earth at light speed, taking 4.2 years to arrive. The signal strength decreases with the square of distance. By the time it reaches Earth, the received power is measured in attawatts. That's 10 to the -18th watts. Detecting it requires enormous receiving antennas and signal processing techniques that filter the spacecraft's transmission from the ocean of cosmic radio noise. Despite all this, breakthrough starshot remains the most plausible method for reaching Proxima Centauri b within a human lifetime. The alternatives are worse. Chemical rockets are hopeless. The tyranny of the rocket equation makes interstellar travel impossible with chemical propulsion. You'd need more fuel than exists in the solar system to reach even a small fraction of light speed. Nuclear propulsion helps, but not enough. Project Daedalus, designed in the 1970s, proposed using fusion rockets to reach Barnard's star. The spacecraft would have massed 50,000 tons, mostly fuel, and required technology we still don't have 50 years later. It could reach 12% light speed, making the trip to Proxima Centauri in about 36 years. But building it requires mining helium, free from Jupiter's atmosphere, and assembling the craft in orbit. The project would cost trillions and take decades of preparation. Antimatter propulsion offers better efficiency but faces the problem that antimatter doesn't exist naturally. Every gram must be manufactured in particle accelerators. Current production rates measure in nanograms per year. Scaling up to the quantities needed for interstellar flight would require energy production far beyond current global capacity. Generation ships avoid the speed problem by accepting the journey will take thousands of years. You build a self-sustaining habitat, launch it on a slow trajectory, and the descendants of the original crew arrive at the destination. This creates biological and social problems that make the engineering look simple. How do you maintain genetic diversity in a population of a few thousand over hundreds of generations? How do you preserve knowledge and purpose across millennia? What happens when the ship arrives and the inhabitants have evolved a completely different culture with no memory of why the journey began? Each propulsion method hits fundamental limits. Physics doesn't provide obvious solutions. We can't manipulate spacetime to create wormholes or warp drives. Those concepts remain firmly in the realm of speculation, requiring exotic matter with negative mass or energy densities that might not exist. So for the foreseeable future, Proxima Centauri b remains out of reach. We can observe it with telescopes. We might eventually send tiny probes. But human visitors? That requires either revolutionary breakthroughs in physics or a commitment to multi-generational projects that our civilization hasn't demonstrated the stability to undertake. Which brings us back to the question of what we're actually observing. Without direct investigation, how certain can we be about conditions at Proxima Centauri b? The answer is we can't be certain at all. We're making educated guesses based on limited data. The planet's mass comes from radial velocity measurements that only give minimum values. Its radius is unknown because it doesn't transit. The atmospheric composition is completely unconstrained. The surface conditions are modeled, not measured. Different research teams using different assumptions produce wildly different conclusions. One study finds the planet could maintain liquid water on its surface. Another concludes it's a desiccated rock stripped of volatiles billions of years ago. A third suggests it's an ocean world with no land masses. A fourth proposes it's completely frozen. They're all working from the same observational data. The divergence comes from different choices about unknown parameters. How much water did the planet start with? How strong is its magnetic field? What's the atmospheric composition? How efficient is heat transport from dayside to nightside? Each assumption cascades through the models, producing dramatically different outcomes. Change one parameter and a habitable world becomes a frozen wasteland. Change another and the frozen wasteland becomes a scorched desert. This isn't sloppy science. It's the reality of studying a world you can't directly observe. You build models based on physics and chemistry, plug in the parameters you know, make reasonable guesses about the parameters you don't know, and see what comes out. Then you try different guesses and see how much the results change. What emerges is a probability distribution rather than a single answer. Proxima Centauri b might be habitable. It might be completely hostile. The observations we have don't definitively exclude either possibility. The situation improves as telescope technology advances. Instruments coming online over the next decade will directly image nearby exoplanets, separating their light from their host stars. Spectroscopy of that light reveals atmospheric composition. The presence of water vapor, oxygen, methane, carbon dioxide, each molecule leaves distinctive absorption lines in the spectrum. But even spectroscopy has limits. Detecting biosignatures requires more than just finding oxygen. Oxygen can be produced by non-biological processes. Ultraviolet radiation splits water molecules, releasing oxygen that accumulates if the planet lacks a mechanism to remove it. A lifeless world stripped of its oceans could have an oxygen-rich atmosphere, mimicking the signature of a living planet. True confirmation requires detecting combinations of gases that wouldn't coexist without life maintaining them. On Earth, oxygen and methane react with each other. They only persist together because biological processes continuously replenish both. Finding that combination on Proxima Centauri b would be compelling evidence for life. The observations won't be easy or quick. Extracting a planetary spectrum from stellar glare requires long integration times and sophisticated data processing. Early attempts will have large error bars. Confirming the presence of specific molecules takes multiple observations with different instruments to rule out false positives. And that's assuming the planet has an atmosphere thick enough to produce detectable spectral features. If stellar activity stripped away most of the atmosphere millions of years ago, there might not be enough gas left to characterize. The timeline stretches across decades. Even if the James Webb Space Telescope begins characterizing Proxima Centauri B's atmosphere tomorrow, confirming habitability or proving its absence requires accumulating enough data to be statistically certain. One observation isn't enough. You need repeated measurements across different wavelengths, different orbital phases, different stellar activity states. Each observation campaign takes months to schedule, execute, and analyze. The scientific process moves deliberately because mistakes are costly. Announce the detection of a biosignature and later discover it was instrumental noise or contamination, and credibility evaporates. The standards for extraordinary claims remain appropriately high. But here's what makes Proxima Centauri B uniquely frustrating compared to other exoplanets. Its proximity should make it easier to study. For light years is nothing in astronomical terms. The planet's light should be readily accessible to our most powerful instruments. Except it's not. Proxima Centauri itself becomes the obstacle. The star's variability creates noise that drowns out the planetary signal. During flare events, extracting anything about the planet becomes nearly impossible. The electromagnetic screaming of the star overwhelms every detector. Between flares, the star's baseline variability still fluctuates enough to complicate measurements. Imagine trying to photograph a firefly next to a strobe light. That's the observational challenge in simplified form. Distance also eliminates certain investigation methods entirely. We're not sending probes to Proxima Centauri B. Not with current technology. Not with near-future technology. Not within any timeframe relevant to current civilization. The Voyager spacecraft, humanity's most distant emissaries, travel at about 17 kilometers per second. At that velocity, reaching Proxima Centauri takes over 73,000 years. Proposals for faster propulsion exist. Nuclear pulse propulsion. Fusion drives. Antimatter rockets. Each faces engineering challenges that remain theoretical. The Breakthrough Starshot initiative proposes light sails accelerated by ground-based lasers to 20% light speed. That reduces transit time to roughly 20 years. But the engineering obstacles are immense. The sail must survive acceleration forces that would vaporize conventional materials. The laser array requires power generation exceeding most nations' total output. And deceleration upon arrival has no proposed solution. A probe traveling at 20% light speed doesn't stop when it reaches the target. It flashes through the system in hours, gathering data at a rate that might fill a few hard drives before disappearing back into interstellar space. So we're left with remote sensing, telescopes, spectroscopy, inference from physics. Which brings us to perhaps the strangest aspect of the entire situation. Everything we know about potentially the most important planet humanity has ever discovered comes from watching a star wobble. The planet itself has never been directly observed. Every specification, every model, every conclusion derives from how Proxima Centauri moves in response to gravitational tugs. The Doppler method measures velocity changes as the star moves toward and away from Earth. Those velocity changes imply a mass. The timing of those changes implies an orbital period. The orbital period implies a distance. The distance combined with stellar luminosity implies a temperature. Every step introduces uncertainty. Every inference rests on assumptions. Consider what happens if one fundamental assumption is wrong. Current models assume Proxima Centauri B is a rocky planet like Earth or Mars. But what if it's not? What if it formed as a mini Neptune with a massive hydrogen envelope? The radial velocity measurements would look identical. A hydrogen-rich world in Proxima Centauri's habitable zone presents completely different prospects for life. The surface, if it exists, would be buried under thousands of kilometers of atmospheric pressure. No liquid water. No rocky substrate for chemistry. Just compression and heat increasing with depth until rock becomes fluid. Or what if the planet formed elsewhere and migrated inward? Planetary migration is common in solar system formation. Worlds don't necessarily stay where they form. Jupiter probably formed farther from the Sun and moved inward before reversing course. If Proxima Centauri be formed in the outer system and drifted toward the star, it could have started with a very different volatile inventory than a planet that formed in place. Migration scenarios affect everything. Water content, atmospheric composition, internal structure. A migrated planet might have captured more water during formation than a locally formed one. Or it might have had its atmosphere stripped during the migration process itself as it passed through regions of intense stellar radiation. The point isn't that any specific alternative is more likely. The point is that multiple scenarios fit the available data. Until direct observation constrains the possibilities, uncertainty dominates. This matters more than it might seem. Public discussion of Proxima Centauri b often treats habitability as a binary question. Either the planet supports life or it doesn't. Reality is messier. Habitability exists on a spectrum. A planet might be marginally habitable. Habitable in the past but not now. Habitable only in specific regions. Habitable but lifeless because life never arose. Each outcome has different implications. Take the scenario where Proxima Centauri b once had liquid water but lost it billions of years ago. That world teaches us about atmospheric escape mechanisms around red dwarfs. It provides data on how stellar radiation interacts with planetary magnetospheres. It constrains models of water loss that apply to thousands of other exoplanets. Scientifically valuable, even if disappointing for those hoping to find life. Now consider the alternative where Proxima Centauri b currently maintains liquid water on its surface despite stellar activity. That would revolutionize our understanding of habitability. It would mean planets can thrive in radiation environments we previously considered sterilizing. The habitable zone concept would need revision. The number of potentially life-bearing worlds in the galaxy increases by orders of magnitude. You see the stakes. This isn't just about one planet. It's about calibrating our expectations for billions of others. Red dwarfs comprise about 75% of all stars in the Milky Way. If their planets can be habitable despite intense stellar activity, the universe becomes far more hospitable to life. If they can't, potentially habitable real estate shrinks dramatically. Proxima Centauri b is the test case. The nearest example. The one we'll characterize first. Whatever we learn there propagates through all subsequent exoplanet research. The waiting is difficult. When the discovery was announced in 2016, excitement peaked immediately. News coverage treated the finding as a potential second Earth. Headlines implied we'd found humanity's future home. Public expectation raced ahead of scientific reality. Then the follow-up studies emerged. The radiation environment looked hostile. Atmospheric stripping seemed likely. Models suggested the planet might be tidally locked, complicating habitability. Enthusiasm cooled. Not because the planet became less interesting scientifically, but because the simple narrative collapsed under detailed scrutiny. What remains is something more complex and ultimately more fascinating than the initial story. Proxima Centauri b might be habitable. The conditions allowing that habitability would differ dramatically from Earth. Life there, if it exists, would face challenges terrestrial organisms never encountered. The evolutionary paths would diverge from anything in our biosphere. Understanding those differences matters more than finding a cosmic twin. Earth-like planets are interesting because they're familiar. Alien worlds are interesting because they expand our conception of what's possible. A habitable planet around Proxima Centauri wouldn't be Earth-like in any meaningful sense. It would be Proxima-like. A product of its specific environment, adapted to its specific challenges, existing under conditions we're still learning to model. That world, if we ever characterize it properly, teaches us what life looks like when it evolves under a red sun. When stellar flares are routine rather than catastrophic. When one hemisphere never sees night and the other never sees day. When the concept of seasons doesn't exist because orbital periods last 11 days. The question isn't whether we find life there. The question is whether we'd recognize it if we did. Recognition requires frameworks. Categories we've already defined. When scientists search for biosignatures in exoplanet atmospheres, they look for specific molecular combinations. Oxygen and methane together. Phosphine in unusual concentrations. Molecules that shouldn't coexist in equilibrium chemistry but do when life mediates the reactions. Those searches assume biochemistry operates similarly everywhere. Carbon-based metabolism. Water as a solvent. Energy gradients life can exploit through familiar pathways. But what if Proxima Centauri b developed something fundamentally different? Not just exotic biochemistry using different solvents or elements, but information processing systems we wouldn't classify as alive using terrestrial definitions. The philosophical problem deepens when you consider detection methods. We search for what we know to search for. Oxygen in an atmosphere stands out because Earth's oxygen comes almost entirely from photosynthesis. But Proxima Centauri b could have oxygen from photolysis, water molecules broken apart by intense UV radiation, leaving oxygen behind without any biological input. That oxygen-rich atmosphere might look like a biosignature when it actually signals the opposite. A dead world that lost its water. Similarly, methane on Earth mostly comes from biological sources. On Proxima Centauri b, geological processes could produce methane through serpentinization, where water reacts with iron-rich rocks. Or atmospheric chemistry under different radiation conditions could generate methane abiotically. The same molecule, completely different origin. This ambiguity isn't just academic. It determines how we interpret observations. When James Webb Space Telescope finally captures a spectrum of Proxima Centauri b's atmosphere, assuming it has one, those spectral lines represent our only data. We build entire narratives around molecular signatures, but the story we tell depends entirely on our assumptions about what those signatures mean. False positives haunt exoplanet research. Venus looked potentially habitable before we understood its atmospheric chemistry. Mars appeared to have seasonal vegetation changes that turned out to be dust storms. Even Earth, if observed from interstellar distances during certain geological epochs, might not show obvious biosignatures. The early Earth had life but no oxygen. An alien civilization searching for habitable worlds might have dismissed our planet as sterile for its first 2 billion years. The inverse problem also exists. False negatives. Life that doesn't produce detectable atmospheric signatures. Subsurface biospheres. Organisms that metabolize in ways that don't leave obvious chemical fingerprints. An ocean world with life confined to hydrothermal vents wouldn't necessarily show biosignatures in atmospheric spectra. We'd categorize it as barren when it actually teems with complex ecosystems. Proxima Centauri b could harbor life we'd never detect remotely. Imagine organisms adapted to survive in cracks within tidally heated rocks. Or microbial communities living in briny underground aquifers, insulated from the radiation-blasted surface. These scenarios are biologically plausible. Earth's deep biosphere extends kilometers underground, comprising a significant fraction of our planet's total biomass. But you'd never know it existed by analyzing atmospheric composition from space. The detection problem becomes even more complicated when you consider non-biological complexity. Could Proxima Centauri b have something that processes information and responds to environmental conditions without being alive in any sense we'd recognize? Autocatalytic chemical networks that maintain themselves far from equilibrium. Mineral systems with emergent organizational properties. Phenomena that blur the boundary between chemistry and biology without crossing it. These aren't idle speculations. They're questions about the limits of our conceptual framework. Life as we know it represents one solution to the problem of maintaining order against entropy. But the universe is large and has been running experiments for billions of years. The probability that Earth's solution is the only viable one seems vanishingly small. This brings us to the spacecraft problem. Even if we can't detect life remotely, we could potentially visit Proxima Centauri b directly. The Breakthrough Starshot initiative proposes launching thousands of tiny spacecraft accelerated by ground-based lasers to 20% light speed. At that velocity, the journey takes just over 20 years. 20 years sounds manageable. A mission launched today could return data within a human lifetime. But the engineering challenges are staggering. The spacecraft would need to survive interstellar space for 2 decades, endure particle impacts at relativistic speeds, and function perfectly upon arrival without any possibility of repair or recalibration. And here's the critical limitation. At 20% light speed, you can't slow down. These wouldn't be orbiters or landers. They'd be flyby probes, screaming past Proxima Centauri b at 60,000 kilometers per second, collecting data during a brief window lasting minutes or possibly seconds. Then continuing into interstellar space forever. The data return would be extraordinary even from a flyby. Direct imaging of the planet's surface. Atmospheric composition measurements. Magnetic field detection. Particle environment characterization. Questions that would take decades to answer with telescopes could be resolved definitively in minutes. But a flyby can't search for life comprehensively. Can't orbit to study different regions. Can't descend to the surface to analyze soil chemistry. Can't drill through ice to sample subsurface oceans. The spacecraft either detects obvious signatures during its brief passage or the question remains unanswered. More sophisticated missions would require deceleration upon arrival. That changes everything. The mass budget explodes. Carrying enough fuel to slow from 20% light speed back to orbital velocities makes the spacecraft too massive to accelerate in the first place. Nuclear pulse propulsion might work, but the engineering becomes fantastically complex. Project Daedalus, designed in the 1970s, proposed a fusion-powered starship that could reach nearby stars within a human lifetime. The spacecraft would mass 54,000 tons, mostly fuel, and use controlled thermonuclear explosions for propulsion. Modern recalculations suggest a modified Daedalus could reach Proxima Centauri in about 36 years. 36 years from launch to arrival. Another 4 years for signals to return to Earth at light speed. A mission launched today would return its first results around 2065. Within the lifetime of people currently alive, barely. The generational question looms. Would civilization maintain interest in a mission spanning 4 decades? Would the scientists who designed it still be alive when data arrives? Would humanity even remember launching it by the time results come back? Historical precedent suggests maybe. Voyager 1 launched in 1977. It's still transmitting data 48 years later. New Horizons launched in 2006, reached Pluto in 2015, and continues exploring the Kuiper Belt. We've demonstrated the ability to maintain missions across decades when the scientific payoff justifies the investment. But those missions explored our own solar system. Proxima Centauri b exists in another star system entirely. The psychological distance matters. It's not ours. It's fundamentally alien territory. The emotional investment differs from exploring planets that orbit our own sun. Yet the scientific justification couldn't be stronger. Every question about exoplanet habitability, atmospheric evolution, and the prevalence of life in the universe comes into sharper focus with data from Proxima Centauri b. It's the calibration point. The ground truth. The one exoplanet close enough to study in detail within foreseeable technological capabilities. The alternative is waiting for better telescopes, larger mirrors, more sensitive instruments, space-based interferometers. Each generation of observatory provides more detailed atmospheric spectra. Eventually we might resolve surface features directly. But remote observation always leaves ambiguities. Always requires inference. Always depends on assumptions about atmospheric chemistry and planetary conditions. Only a spacecraft provides certainty. Direct measurement. Unambiguous data. The difference between believing a planet has water vapor in its atmosphere and actually detecting that vapor with instruments physically present in the planet's vicinity. So we face a choice. Commit resources to an interstellar mission knowing the returns won't arrive for decades. Or continue improving remote observation capabilities, accepting the limitations inherent in analyzing starlight filtered through a distant atmosphere. The decision reveals something about our species. Are we patient enough to plant seeds we won't harvest? Willing to invest in knowledge that benefits future generations more than ourselves? Or do we demand immediate returns, relegating interstellar exploration to Sunday when it's easier? Proxima Centauri b doesn't care about our timeline. It orbits its star every 11 days regardless of whether we're watching. If it has life, that life evolved without waiting for humanity's permission. If it's barren, those empty landscapes exist independent of our curiosity. The planet represents a test. Not of habitability, but of human ambition. Whether we're content to wonder from a distance or willing to close the gap between speculation and knowledge. Whether the nearest potentially habitable world beyond our solar system remains forever a subject of astronomical study or becomes a destination. Right now it's a data point. A planet detected through the wobble it induces in its star's motion. A mass estimate. An orbital period. A position in the habitable zone. Numbers in a database alongside thousands of other exoplanets. But it could become more than that. The first extrasolar world we visit. The place where we discover whether habitable means inhabited. The planet that teaches us what life looks like when it evolves under a red sun's violent gaze. Everything depends on what we choose to do with the knowledge that it's there, waiting, just 4.2 light-years away. So here we are. Standing on Earth, staring outward at a world that sits closer to us than any other star system, yet might as well exist in another universe entirely. Proxima Centauri b occupies this strange position in human consciousness. Close enough to feel relevant. Far enough to remain fundamentally unknowable with current technology. The dark secret wasn't what we expected when the discovery was announced in 2016. Headlines proclaimed a potential second Earth. The reality proved far more nuanced and considerably more hostile. A planet bombarded by radiation that would strip Earth's atmosphere in geologic heartbeats. Flares that erupt not once per century but multiple times daily. Stellar wind pressure 10,000 times what Earth experiences. Tidal forces 900 times stronger than what the Sun exerts on our world. These aren't minor complications. They're fundamental challenges to the very concept of habitability around red dwarf stars. And red dwarfs comprise 3/4 of all stars in the galaxy. If their planets can't maintain atmospheres, can't retain water, can't develop protective magnetic fields, then the universe becomes a much lonelier place than we hoped. But the story doesn't end with hostility. It deepens. Because Proxima Centauri b might have survived anyway. Might have maintained its atmosphere through some combination of factors we haven't fully modeled. Might have enough volcanic outgassing to replenish what stellar activity strips away. Might possess a magnetic field generated through mechanisms we don't yet understand. Might host liquid water in protected regions even while the rest of the surface freezes or burns. The uncertainty isn't a failure of science. It's the current state of knowledge about a world we've never directly observed. Every model depends on assumptions about parameters we can't measure. Change those assumptions and a frozen wasteland becomes a habitable ocean world. Change them again and the ocean world becomes a desiccated rock. What makes this frustrating is that the planet sits right there. 4.2 light-years. The nearest star system. If habitability exists anywhere beyond our solar system that we could potentially verify within a human lifetime, it's there. Yet it might as well be in another galaxy given our current propulsion capabilities. The telescope observations coming online over the next decade will help. James Webb Space Telescope can characterize atmospheric heat transport if the planet has a thick enough atmosphere. Ground-based extremely large telescopes might achieve the contrast ratios needed for direct imaging. Spectroscopy could reveal molecular signatures that indicate water vapor, oxygen, methane, carbon dioxide. But spectroscopy has limits. Finding oxygen doesn't necessarily mean finding life. Oxygen accumulates on dead worlds that lost their water through photolysis. The oxygen remains after hydrogen escapes, creating a false biosignature. Distinguishing between biological and abiological oxygen requires detecting multiple gases simultaneously in combinations that shouldn't coexist without life maintaining them. The observations take time. Years of data collection. Statistical analysis to separate signal from noise. Repeated measurements to rule out instrumental artifacts. The scientific process moves deliberately because mistakes destroy credibility. You don't announce the detection of life on the nearest exoplanet unless you're absolutely certain. Meanwhile, the planet continues its 11-day orbit, indifferent to human curiosity. If life exists there, it evolved under conditions Earth never experienced. Organisms adapted to stellar flares as routine environmental features rather than catastrophic events. Biochemistry operating under intense UV radiation. Ecosystems confined to narrow habitable zones between frozen nightsides and scorched daysides. We wouldn't recognize that life immediately. Our biosignature searches assume Earth-like chemistry. Oxygen from photosynthesis. Methane from biological processes. But Proxima life might use completely different metabolic pathways. Might not produce the molecular signatures we're searching for. Might exist in environments we classify as uninhabitable using terrestrial standards. The spacecraft option remains theoretical. Breakthrough Starshot could launch probes within decades if the engineering challenges get solved. 21 years to reach Proxima Centauri at 20% light speed. Another 4 years for data to return. A mission spanning a generation but achievable within a human lifetime. Yet even that requires revolutionary technology. Laser arrays powerful enough to accelerate gram-scale spacecraft to relativistic velocities. Materials that survive interstellar particle impacts. Communication systems that transmit across light years using power measured in milliwatts. Navigation precise enough to thread a target the size of Earth from 4 trillion kilometers away. And for what? A flyby lasting minutes. No deceleration. No orbit. No landing. Just a brief window to gather data before the probe continues into interstellar space forever. Better than nothing. Better than pure speculation. But still frustratingly incomplete. The more sophisticated missions that could orbit Proxima Centauri B, study it properly, search for life comprehensively, require propulsion systems that don't exist. Fusion drives. Antimatter rockets. Technologies that remain theoretical decades after their initial proposal. The engineering challenges compound. The timeline stretch to centuries. The resources required exceed anything humanity has collectively attempted. So we're left waiting. Watching from afar with increasingly sophisticated instruments. Building models that diverge wildly depending on assumptions. Hoping the next generation of telescopes reveals something definitive. Knowing that even definitive observations leave room for interpretation. Proxima Centauri B represents both promise and limitation. Promise that habitable worlds might exist at stellar distances we could theoretically reach. Limitation that even the closest exoplanet remains functionally inaccessible with current technology. It's the planet that should answer our questions about habitability around red dwarfs, but instead raises more questions than it resolves. The dark secret turns out to be uncertainty itself. We found a world in the habitable zone of the nearest star and discovered we can't determine whether it's actually habitable. Can't confirm whether it has water. Can't verify whether its atmosphere survived stellar bombardment. Can't detect whether life arose there despite the hostile conditions. And perhaps that's appropriate. The universe doesn't owe us easy answers. Doesn't arrange itself for human convenience. Proxima Centauri B exists in the state it exists regardless of whether we understand it. Our ignorance reflects the limitations of our perspective, not any deficiency in the planet itself. The coming decades will narrow the uncertainty. Better instruments. More detailed models. Eventually direct observation through spacecraft if we commit the resources. But even then, even with data from probes that actually visit the system, ambiguities will remain. Life might hide in subsurface oceans we can't sample. Might operate through biochemistry we don't recognize. Might have existed in the past and left traces we can't interpret. The search for life beyond Earth always involved confronting these ambiguities. Proxima Centauri b makes them immediate and tangible because the world sits close enough to feel within reach. It's the exoplanet that should be easiest to characterize and instead proves most frustrating precisely because of its proximity. We know it's there. We know roughly what it is. We just can't determine the details that matter most. So the planet remains what it's always been. A world orbiting a red dwarf star 4.2 light-years away. Potentially habitable. Possibly hostile. Definitely alien. The closest exoplanet to Earth and simultaneously one of the most mysterious. Not because we lack interest or capability, but because the universe maintains its secrets even when they're practically in our cosmic backyard. That's the real lesson. Distance isn't measured only in light years. It's measured in technological capability, observational precision, and the fundamental difficulty of understanding worlds we can't visit. Proxima Centauri b taught us that proximity doesn't equal accessibility. That nearby doesn't mean knowable. That the closest potentially habitable world beyond our solar system remains profoundly alien despite being our nearest neighbor. The dark secret wasn't about the planet. It was about us. About the limits of what we can know from here. About how much remains unknown even when we're looking at the closest possible target. About how the universe resists easy categorization no matter how sophisticated our instruments become. Proxima Centauri b will reveal its secrets eventually. Through better telescopes or visiting spacecraft or some technology we haven't invented yet. But it will reveal them on its own timeline, not ours. And when those secrets finally emerge, they'll probably raise more questions than they answer. Because that's how exploration works. Each answer opens new uncertainties. Each discovery reveals deeper mysteries. The planet spins through its 11-day orbit, lit by the dim red glow of its ancient star, maintaining whatever secrets it holds. Waiting for us to develop the capability to truly see it. Or perhaps indifferent to whether we ever do. Either way, it's there. The closest alien world. Still hiding its dark secret. Still waiting. There's a lake on Titan where you could walk across the surface without getting wet. Not because it's shallow, but because the liquid itself is lighter than your body. Step in and you'd float, surrounded by methane and ethane, under a sky thick with orange haze, while nitrogen rain falls upward in the low gravity. This isn't science fiction speculation. This is Saturn's largest moon, and it's the only other world in our solar system with stable liquid on its surface. For decades, scientists searched for life by following water. Mars rovers hunt for ancient riverbeds. Europa missions target subsurface oceans. The logic seemed airtight. Life needs liquid. Water is the universal solvent. Find water, find life. Then we got a closer look at Titan, and that certainty started cracking. Because Titan doesn't play by Earth's rules. Its lakes are liquid methane. Its ice is made of water harder than granite. Its atmosphere is denser than ours, and its surface temperature sits at -290 degrees Fahrenheit. Everything we thought we knew about where life could exist suddenly needed revision. The Cassini mission changed everything when it arrived at Saturn in 2004. Scientists expected Titan's thick atmosphere to hide a relatively boring surface. They were wrong. Radar imaging pierced through the haze and revealed something nobody predicted. Lakes. Hundreds of them. Concentrated near the poles, filling impact craters and ancient riverbeds. Some larger than the Great Lakes. But these weren't water. Spectroscopic analysis confirmed what seemed impossible. Liquid methane and ethane, stable on the surface, fed by a complete hydrological cycle. Titan has weather. It has seasons. It has coastlines that shift with evaporation and rainfall. It's Earth's hydrocarbon twin, running on completely different chemistry. The numbers don't make intuitive sense at first. Titan's surface pressure is about 1.5 times Earth's at sea level. That's manageable. But the temperature makes everything strange. At -290 Fahrenheit, methane behaves like water does here. It evaporates from lakes, forms clouds, falls as rain, carves river channels, and pulls back into seas. Water ice on Titan is effectively bedrock. It doesn't melt. It doesn't flow. The entire landscape is frozen water with liquid methane rivers cutting through it. Imagine continents made of ice, oceans made of gasoline, and rain that would fuel your car. This inversion creates chemistry Earth never experiences. On our planet, water dissolves salts and minerals, creating the ionic soup where biochemistry happens. On Titan, liquid methane dissolves completely different compounds. Long-chain hydrocarbons. Nitrogen-bearing molecules. Organic compounds that would be solid or gaseous here but remain liquid there. The result is a chemical laboratory running experiments Earth's environment would never allow. And that's where things get interesting for astrobiology. Traditional definitions of life hit a wall with Titan. We define life by its need for liquid water, its carbon-based chemistry, its energy metabolism. But those definitions assume Earth conditions. They assume water's unique properties as a solvent. They assume temperatures where proteins remain stable and cell membranes maintain structure. Titan violates every assumption. So either life there is impossible, or our definitions are too narrow. Scientists are increasingly betting on the latter. The concept gaining traction is called polyextremophile life. Not organisms that tolerate one extreme condition, but entities that function in an environment completely alien to Earth biology. These wouldn't be bacteria that survive cold. They'd be structures that require cold to maintain stability. They wouldn't use water as a solvent. They'd be built around methane's properties. Their metabolism wouldn't generate heat. It might consume hydrogen or acetylene, releasing methane as waste. Everything would be inverted from what we know. Cornell researcher Jonathan Lunine proposed a theoretical cell membrane that could function in liquid methane. On Earth, cell membranes are phospholipid bilayers. They work because water is polar. Head groups love water. Tail groups hate it. The result is a stable barrier that controls what enters and exits a cell. But methane isn't polar. It's nonpolar. So a methane-based membrane would need completely different chemistry. Lunine's team modeled something called an azotosome, built from nitrogen-containing compounds that self-assemble in liquid methane. Computer simulations show they'd be stable, flexible, and capable of selective permeability. They could work. But membranes are just the start. Metabolism is the harder problem. Life needs energy. On Earth, that energy comes from breaking chemical bonds or capturing photons. Both processes depend on specific temperature ranges where reactions proceed fast enough to be useful but slow enough to control. Titan's temperature is so low that most chemical reactions we rely on would effectively stop. So how could metabolism function? The answer might lie in Titan's atmosphere. Cassini detected something strange. Hydrogen gas near the surface is depleting faster than it should. Acetylene, a high-energy hydrocarbon, is also disappearing. The numbers don't add up unless something is consuming them. One hypothesis: organisms on Titan's surface are breathing hydrogen, metabolizing acetylene, and releasing methane. It's the inverse of our respiration. We breathe oxygen and release carbon dioxide. They'd breathe hydrogen and release methane. The energy yield would be tiny compared to Earth biochemistry. But in a cold, slow world, maybe tiny is enough. This metabolic model solves another puzzle. Titan's atmosphere shouldn't exist. Methane breaks down under solar ultraviolet radiation. Without a constant source, it should vanish in about 10 million years. Yet Titan's atmosphere is 5% methane, stable over geological time. Something is replenishing it. Volcanic outgassing from the interior is one explanation. But biology is another. If organisms are converting hydrogen and acetylene into methane, they'd be maintaining the atmosphere that makes their lakes possible. They'd be planetary-scale ecosystem engineers, like Earth's cyanobacteria that oxygenated our atmosphere billions of years ago. The implications stretch beyond Titan. If life can emerge in liquid methane at -290 Fahrenheit, then habitable zones around stars need redefinition. We've been searching for planets in the Goldilocks zone where liquid water exists. But methane-based life could thrive on worlds far colder, far from their stars, in conditions we've been ignoring. The number of potentially habitable worlds in the galaxy would multiply dramatically. Titan isn't just interesting because it might host life. It's interesting because it represents an entire class of worlds we haven't seriously considered. But before we get ahead of ourselves, we need to address the elephant in the room. Nobody has detected life on Titan. The hydrogen and acetylene depletion could have non-biological explanations. The chemistry might be abiotic. We're extrapolating from incomplete data, building hypotheses on top of models. This is responsible science, exploring possibilities, but it's not confirmation. Proving life exists on Titan would require either direct detection of organisms or finding chemical signatures that can't be explained any other way. Neither has happened yet. The challenge is partly technical. Titan is 890 million miles from Earth. Light takes over an hour to travel that distance. Sending a mission there requires years of transit time and landing on a surface we still barely understand. The Huygens probe, which descended to Titan's surface in 2005, lasted 90 minutes before its batteries died. It sent back images of a rocky shoreline and detected methane vapor near the surface. But it didn't carry instruments designed to search for life. We weren't ready to ask that question yet. Now we are. NASA's Dragonfly mission, scheduled to launch in 2027 and arrive in 2034, will change the game. It's a nuclear-powered rotorcraft that will fly between dozens of locations on Titan's surface, sampling different environments and analyzing chemistry. It's designed to look for prebiotic chemistry, the organic building blocks that might precede life. But if life already exists there, Dragonfly has a chance of finding it. The mission will land near Titan's equator, in a region called Shangri-La, where sand dunes made of hydrocarbon particles stretch for hundreds of kilometers. What Dragonfly finds could reshape biology. If it detects only abiotic chemistry, that's still valuable. We'll learn about organic synthesis in exotic environments. But if it finds evidence of metabolic processes, or structures that suggest cellular organization, or chemical patterns that defy non-biological explanation, then we'll know life isn't unique to Earth's conditions. We'll know biochemistry can take radically different forms. And we'll know that searching for life in the universe needs to cast a much wider net. The search won't be straightforward. Even if organisms exist on Titan, they might not be easy to recognize. They won't have DNA. They won't have proteins as we know them. Their chemistry will be so foreign that our instruments might not know what to look for. Scientists are developing new biosignature frameworks specifically for non-water-based life. These focus on patterns rather than specific molecules. Does the chemistry show disequilibrium? Are there compounds that shouldn't coexist unless something is actively producing them? Is there complexity that seems organized rather than random? These questions guide not just Titan exploration but our entire approach to astrobiology. Because Titan is teaching us something fundamental. Life might not be rare in the universe. But familiar life might be. We've been searching for ourselves, for carbon and water organisms that look like Earth biology. Maybe that's the wrong approach. Maybe the universe is full of life, just not life we'd immediately recognize. Titan is the test case. It's the place where we'll learn whether biology is flexible enough to work in conditions that seem hostile to everything we understand. The story of Titan's lakes is really about expanding what we think is possible. Before Cassini, liquid lakes on another world seemed like science fiction. Now they're mapped and studied. Before astrobiology embraced exotic chemistry, life seemed confined to narrow conditions. Now we're modeling organisms that breathe hydrogen. The pattern keeps repeating. Our assumptions get challenged. The universe turns out stranger than we imagined. And the definition of habitable keeps stretching. That's why Europa matters even more than Titan in some ways. It's not trying to rewrite the rules. It's playing by them. Water, salt, energy, heat. The ingredients list reads like Earth's early oceans, just buried under ice instead of exposed to air. If life can start in those conditions, then every icy moon in the outer solar system becomes a candidate. And there are dozens of them. Europa orbits Jupiter every 3.5 days, locked in a gravitational dance with Io and Ganymede that stretches and compresses its interior like a stress ball. That flexing generates heat. Not from sunlight, which barely reaches Jupiter's orbit, but from tidal forces. The moon's icy shell cracks and refreezes constantly, creating a surface that looks like shattered glass held together by frozen seams. Those cracks matter because they might connect the surface to the ocean below. If water from the deep ocean occasionally rises through fractures and gets exposed at the surface, then a spacecraft could sample it without drilling through kilometers of ice. The Hubble Space Telescope detected water vapor plumes erupting from Europa's surface in 2012. Follow-up observations confirmed them. These aren't geysers in the traditional sense. They're intermittent, sporadic jets of material that shoot up to 200 kilometers above the surface before falling back down. Scientists think they originate from pressurized pockets of water beneath the ice, forced upward when stress fractures open temporarily. If a spacecraft could fly through one of those plumes and analyze the particles, it would essentially be sampling the ocean without landing. That's exactly what NASA's Europa Clipper mission plans to do. Launching in 2024, it won't orbit Europa directly because Jupiter's radiation environment is lethal to electronics. Instead, it will orbit Jupiter and make dozens of close flybys of Europa, sweeping through different regions and altitudes. Its instruments will measure the ice shell's thickness using radar, analyze the surface composition with spectrometers, and sample any plume material it encounters. The goal isn't to find life directly. It's to determine whether the conditions for life exist. But here's the tension. Europa might be habitable, but accessibility is the problem. The ice shell is estimated to be 15 to 25 kilometers thick. Drilling through that with current technology would take decades, and we don't even know if it's safe to try. The ocean below is under immense pressure. Breaking through could trigger unpredictable responses. And even if we reach the water, contamination becomes a serious concern. How do we search for alien life without introducing Earth life in the process? Enceladus doesn't have that problem. Saturn's tiny moon, barely 500 kilometers across, has plumes that are active, consistent, and accessible. The Cassini spacecraft flew through them multiple times, analyzing water vapor, salts, organic molecules, and even molecular hydrogen. That last one is critical. Hydrogen suggests hydrothermal activity on the ocean floor, reactions between water and rock that release energy. On Earth, entire ecosystems thrive around hydrothermal vents in total darkness, sustained by chemical energy instead of sunlight. If Enceladus has the same setup, it could support life. The difference between Europa and Enceladus comes down to scale and certainty. Europa is larger, has more water, and probably more stable conditions over geological time. But it's harder to study. Enceladus is smaller, might have a thinner ice shell, and actively advertises its ocean by spraying it into space. A mission to Enceladus could analyze fresh ocean material without landing, without drilling, without waiting decades for results. That's why the next generation of missions is split. NASA is focusing on Europa because it represents the best chance of a large, stable biosphere. But other space agencies and private missions are eyeing Enceladus because it's the low-hanging fruit. If life exists in either place, finding it at Enceladus would be faster and cheaper. The question is whether faster and cheaper is worth the trade-off if Europa turns out to be the richer environment. Then there's Ganymede, Jupiter's largest moon and the only moon in the solar system with its own magnetic field. It also has a subsurface ocean, possibly sandwiched between layers of ice in a structure scientists call an ice-water-ice sandwich. That's strange. Most icy moons have a single ocean layer beneath the crust. Ganymede might have multiple layers at different depths, each with different pressures, temperatures, and chemistries. If life emerged in one layer, could it spread to others? Could different layers host different kinds of organisms, each adapted to local conditions? We don't know. The European Space Agency's JUICE mission, which launched in 2023 and will arrive at Jupiter in 2031, will spend years studying Ganymede. It will map the subsurface structure, measure the ocean's depth and salinity, and search for active geology. Unlike Europa Clipper, JUICE will eventually enter orbit around Ganymede, giving it extended close-up access. If Ganymede's ocean is layered, that raises entirely new questions about how habitable environments can be structured. What unites all these moons is water and energy. Where those two exist together, life becomes possible. Not guaranteed, but possible. And the outer solar system has more liquid water than Earth does. Most of it is hidden under ice, locked away in oceans we've never seen. But it's there, and it's been there for billions of years. Long enough for chemistry to get interesting. Long enough for evolution to do its work, if the conditions are right. That's the shift happening in astrobiology right now. For decades, scientists focused on Mars because it was nearby, because it once had surface water, because it seemed like the obvious place to look. Mars still matters. But the icy moons are taking over as the primary targets for life detection because they have what Mars lost, active water systems that exist today, not billions of years ago. Mars is a fossil record. Europa and Enceladus are living environments. The challenge is patience. These missions take years to design, years to build, and years to reach their destinations. Europa Clipper won't arrive until 2030. Dragonfly won't land on Titan until 2034. JUICE won't finish its Ganymede observations until the late 2030s. We're talking about timelines that span decades. The scientists who propose these missions might retire before the data comes back. That's the reality of outer solar system exploration. It's generational work. But the payoff is proportional. If we find life on Europa, it won't just be a discovery. It will be proof that life can begin independently in multiple places. That would mean life isn't a fluke. It's a natural outcome when conditions align. And if it happened twice in one solar system, it's happening everywhere. The galaxy suddenly becomes a much more populated place, even if most of that life is microbial, hidden, and nothing like us. That's the argument some scientists are making now. Life might be common, but complex life might be rare. Intelligence might be rarer still. So the search isn't really about finding aliens we can talk to. It's about understanding whether biology is universal or exceptional. Whether life is chemistry's inevitable destination or a fragile accident that happened once and barely survived. The icy moons will answer part of that question. If their oceans are sterile, that tells us something. It means water and energy aren't enough. It means life requires additional factors we haven't identified, conditions that Earth had but these moons lack. That would narrow the search. We'd know habitable zones are smaller than we thought, that liquid water alone doesn't guarantee biology. But if we find life, even simple life, even just metabolic signatures or organic structures that suggest cellular organization, then the equation changes. Habitable becomes a much broader category. We'd start looking at moons around Uranus and Neptune. We'd reconsider rogue planets drifting through interstellar space, worlds with no star but enough internal heat to melt subsurface ice. We'd expand the search beyond solar systems entirely, into molecular clouds where organic chemistry runs wild without needing planets at all. The icy moons are teaching us to stop thinking of habitable as a single set of conditions. It's a spectrum. Earth-like is one point on that spectrum, but it's not the only one. Titan represents another point, where cold hydrocarbon chemistry might support life nothing like ours. Europa represents a third, where water exists but sunlight doesn't. Each environment selects for different biochemistries, different survival strategies, different forms. That's why the next 20 years matter so much. We're not just exploring distant moons. We're testing whether life is resilient enough to exist in places that seem impossible. Whether biology can adapt to darkness, cold, pressure, and isolation. Whether the spark that started on Earth can ignite elsewhere under completely different rules. The missions launching now will answer those questions. And once we have those answers, we'll know whether we're alone or surrounded by life we've simply been too Earth-focused to recognize. The timeline matters because space exploration doesn't move at human speed. It moves at orbital mechanics speed, budget cycle speed, engineering validation speed. You can't rush a spacecraft to Jupiter. The laws of physics don't care about your funding deadline. But while we wait for those flagship missions to arrive, something else is happening. Ground-based telescopes are getting better at analyzing atmospheres. Webb is already looking at exoplanet spectra with unprecedented detail. And closer to home, we're refining our detection methods. Learning what biosignatures actually look like when you can't land and sample directly. That's the real challenge with ocean worlds. Access. You can't just drill through kilometers of ice. Not yet. The technology exists in theory, but deploying it on Europa or Enceladus requires autonomous systems we're still developing. Systems that can melt through ice, navigate obstacles, communicate back through solid barriers, and operate for months without human intervention. NASA's been testing ice-penetrating robots in Antarctica. Harsh environment, thick ice, isolated conditions. About as close to Europa as you can get on Earth. and the results are mixed. Drilling works. Navigation works. Power management is the problem. You need enough energy to melt ice, run instruments, and transmit data. Solar panels don't help under the ice. Nuclear power is the only option, and miniaturizing that while keeping it safe enough to launch is where the engineering gets complicated. So we're caught in this strange position. We know where life might be. We have strong evidence that liquid water exists right now on multiple moons. But physically reaching those oceans is still a decade away, maybe two. That gap between knowing and confirming is where the frustration lives. Some scientists argue we should focus on Enceladus first. The plumes make it easier. You don't need to land or drill. Just fly through the eruptive jets and collect samples directly. Cassini did it accidentally. A dedicated mission could do it intentionally, with instruments designed specifically to detect biological molecules. If anything's alive in that ocean, pieces of it are being ejected into space constantly. That's sampling without the engineering nightmare of penetration. But plume analysis has limits. You're collecting fragments, not context. You might find organic molecules, but are they biological or geological? You might detect chemical disequilibrium, but is that metabolism or just weird chemistry? Without direct observation, without being able to see how these molecules are organized or whether they're part of larger structures, interpretation becomes guesswork. That's why Europa Clipper is carrying multiple instrument types. Cameras to map the surface. Spectrometers to analyze composition. Ice-penetrating radar to probe the subsurface. Magnetometers to confirm the ocean's conductivity. No single measurement proves life. But patterns across multiple datasets can build a case strong enough to justify the next mission, the one that actually lands. And that landing mission is already being designed. Europa Lander is still in concept phase, but the basic plan is clear. Touch down on a geologically active region. Deploy sensors to listen for subsurface activity. Use a drill or melt probe to access material just below the surface, where radiation hasn't destroyed organic molecules. Run chemical tests on site. Look for amino acids, lipids, metabolic byproducts. Anything that suggests biological processes rather than sterile chemistry. The landing site selection will be critical. Too smooth and you're probably on old ice, far removed from recent ocean contact. Too rough and landing becomes impossible. The ideal target is somewhere recent resurfacing has occurred. Cracks, ridges, areas where tidal flexing has pushed fresh material upward. Those are the places where ocean chemistry meets the surface, where contamination from space radiation is minimal. Radiation is the other problem no one talks about enough. Jupiter's magnetic field accelerates charged particles to extreme energies. Europa's surface gets bombarded constantly. Organic molecules don't survive that. They break apart, rearrange into non-biological forms. Which means surface sampling alone won't work. You need to dig, even if it's just a meter or two, to reach material that's been shielded. That complicates the mission profile. Now you're not just landing, you're drilling in a place where your equipment might freeze, where communication delays mean full autonomy, where one mechanical failure ends the mission. The engineering margins are razor thin. Which is why Europa lander keeps getting delayed. It's not lack of interest. It's physics. While engineers solve those problems, astrobiologists are asking harder questions. What does alien life even look like? We assume cells, membranes, metabolism. But that's Earth bias. Life here evolved in specific conditions with specific chemistry. Carbon-based, water-dependent, DNA-encoded. Those aren't universal requirements. They're just what worked here. Titan suggests alternatives are possible. Liquid methane isn't water. It doesn't have water's properties. But chemistry still happens. Molecules still interact. Energy still flows through systems. Whether that produces something we'd recognize as life is the open question. But the fact that we're asking it means our definition of life is expanding. Some researchers propose we should stop looking for Earth-style biology and start looking for thermodynamic signatures instead. Life, at its core, is a system that maintains disequilibrium. It takes in energy, uses it to build structure, and exports entropy. That's true whether you're a bacterium, a tree, or a hypothetical methane-based organism on Titan. The chemistry changes, but the thermodynamics don't. If that's the framework, then detection becomes different. You're not searching for DNA or proteins. You're searching for organized complexity. Patterns that persist against entropy. Chemical gradients that shouldn't exist unless something is actively maintaining them. That's harder to measure from orbit, but it's also harder to misinterpret. This shift in thinking is changing mission design. Future landers won't just carry microscopes and chromatographs. They'll carry calorimeters to measure heat flow, sensors to detect chemical cycling, instruments that can recognize complexity without assuming specific molecular structures. We're preparing for life that doesn't look like us. Which brings up the philosophical side. If we find microbial life on Europa, how do we treat it? Do we have ethical obligations to extraterrestrial microbes? The Outer Space Treaty says we can't contaminate other worlds, but it's vague on what contamination means. Bringing Earth bacteria to Europa would be catastrophic for any native ecosystem. But is accidentally killing alien microbes during sampling any different than what we do in Earth's deep oceans every time we take a core sample? These aren't abstract questions. They'll become policy decisions the moment we confirm life exists elsewhere. Some scientists argue for extreme caution. Observe from orbit, never land, preserve these environments in their natural state. Others argue that's impractical. We can't understand life without direct study. Sterilization protocols exist for a reason. Use them properly and contamination risk drops to near zero. The debate will intensify as missions get closer to launch. Right now it's academic. But when Europa lander is sitting on a launch pad, fully fueled, and someone raises concerns about planetary protection, the conversation becomes real. Do you scrub the mission? Redesign the protocols? Accept calculated risk? There's no consensus yet. What's clear is that finding life on an icy moon would be simultaneously the greatest discovery in human history and the beginning of much harder questions. Not just scientific questions, but ethical ones. Legal ones. Questions about how we interact with biology that exists beyond our planet, that evolved independently, that has no concept of humanity and no stake in our survival. That's the weight these missions carry. They're not just exploring. They're potentially introducing us to a second genesis, a separate origin of life that followed different rules and produced different results. Even if it's just bacteria. Even if it's chemically simple. The implications reshape everything we thought we knew about biology's place in the universe. And if multiple moons harbor life, if Europa has one form and Enceladus has another and Titan has a third, then we're not looking at rare accidents. We're looking at inevitability. Life becomes something the universe does regularly, under wildly different conditions, using whatever chemistry is available. That's a different cosmos than the one we grew up in. The icy moons are forcing us to confront that possibility before we're ready. Before we have the technology to fully investigate. Before we've agreed on what finding life even means. We're in this strange transition period where we know enough to ask the right questions but lack the tools to answer them definitively. So we build the tools. Design the missions. Train the next generation of scientists who'll interpret data we haven't collected yet. That's where we are now. Poised between knowing these worlds exist and understanding what they contain. The gap is closing, but slowly. And every year that passes without confirmation is another year of uncertainty, another year where life beyond Earth remains theoretical rather than observed. The timeline matters here. Europa Clipper launches in October 2024. JUICE, the European Space Agency's Jupiter mission, launched in April 2023. Both arrive at Jupiter in the 2030s. They'll spend years mapping, measuring, taking data we don't have yet. But neither lands. Neither drills. They're reconnaissance, not contact. The actual moment when we touch Europa's ice and sample its ocean, that's still decades away, potentially 2040s or 2050s, depending on funding, technology development, and political will. Which means most of the scientists designing these missions won't see the final results. They're building instruments for questions that'll be answered by people who haven't finished grad school yet. That's normal in planetary science. Voyager launched in 1977 based on calculations done in the 1960s. The researchers who planned those trajectories were working with slide rules. Now we're analyzing data from those same spacecraft 47 years later. Long timelines are standard. But they create a strange disconnect. Public excitement peaks during launches, during flybys, during press conferences with new images. Then it fades. The actual science happens in the gaps. Years of orbital mechanics. incremental data collection, slow refinement of models that nobody outside the field pays attention to. Europa Clipper will make 49 close flybys of Europa over 4 years. Each flyby generates gigabytes of data. Radar soundings, ice-penetrating measurements, magnetic field readings, surface composition maps. That data gets analyzed, peer-reviewed, published in papers with titles like High-Resolution Subsurface Characterization of Europa's Chaos Terrain Using Multi-Frequency Sounding. Not exactly viral content. But that's where the discoveries happen. Not in dramatic announcements, but in cumulative understanding built dataset by dataset. Someone notices an anomaly in the magnetic readings. Someone else correlates it with a surface feature. A third researcher runs simulations and realizes it matches what you'd expect from a subsurface current. Suddenly you've constrained the ocean's salinity and temperature in one specific region. That's progress. Unglamorous, incremental, but real. The challenge is maintaining momentum across decades. Keeping missions funded when results are slow. Convincing politicians that orbital surveys matter even when they don't produce headlines. NASA's good at this. They've kept missions running for years past their planned lifetimes because the science justifies it. Cassini was supposed to study Saturn for 4 years. It lasted 13. The Opportunity rover was designed for 90 days on Mars. It operated for 15 years. Once a mission is active and producing data, shutting it down becomes harder to justify. But getting to that point requires sustained investment through the unglamorous phases. Europa Clipper costs $4.25 billion. That's over 2 decades of development, construction, launch, and operations. For context, that's roughly what the U.S. spends on military operations every 3 days. It's less than the budget for a single aircraft carrier. In terms of national spending, it's a rounding error. But it still requires congressional approval, annual budget fights, competing priorities. Every year without a major discovery is a year someone argues the money could go elsewhere. The counterargument is simple. This is a one-time cost for potentially permanent knowledge. If Europa has life, we learn that once and it changes biology forever. If it doesn't, we learn that too, and it narrows where else to look. Either outcome justifies the investment. But that logic doesn't always win budget battles. Which is why mission designers build in public engagement. Pretty pictures from JunoCam. Visualizations of what Europa's ocean might look like. Educational outreach explaining why this matters. It's not just science communication. It's survival strategy. Missions with public support get continued funding. Missions that fade from public consciousness get cut. So there's this weird tension. The actual science is slow, technical, incremental. But the presentation has to be exciting, accessible, urgent. Researchers have to be both rigorous scientists and effective communicators. Not everyone's good at both. Some of the best planetary scientists are terrible at explaining their work to non-specialists. Some of the best science communicators oversimplify to the point of inaccuracy. Finding people who can do both is rare and valuable. NASA knows this. They fund media specialists, visualization teams, outreach programs specifically to keep missions in public awareness. It works. Curiosity rover has a Twitter account with millions of followers. People care about a robot on Mars because someone made them care. The same strategy applies to Europa. Make people invested in the search for life on an ice-covered moon 48 light minutes from Earth. Make them check for updates. Make them explain to their kids why this matters. That cultural investment translates to political support when budget renewals come up. But it only works if the underlying science is solid. You can't sustain interest in a mission that's not producing results. Which brings us back to the question: what if Europa Clipper finds nothing? What if the ocean's sterile? What if years of flybys show no biosignatures, no organic chemistry, no signs that life ever existed there? That's a possible outcome. Not the one anyone wants, but scientifically valid. It would tell us something important. That liquid water and energy sources aren't enough. That you need additional factors we haven't identified yet. Maybe the ocean's too young. Maybe the chemistry's wrong. Maybe life requires conditions that only Earth provides. That would be disappointing but not catastrophic. Science advances through negative results as much as positive ones. Ruling out possibilities narrows the search space. If Europa's dead, we focus on Enceladus. If that's sterile too, we rethink our assumptions about where life can form. The worst outcome isn't finding nothing. It's ambiguity. Detecting organic molecules that could be biological or geological. Finding chemical gradients that might indicate life or might just be mineral dissolution. Seeing surface features consistent with biology but not definitive. That's the scenario that drives scientists crazy. Spending billions, traveling for years, collecting massive data sets, and ending up with maybe. No clear answer. Just more questions. It's possible. Maybe even likely. Biology's messy. It doesn't announce itself clearly unless you're looking at something obviously alive. Microbes don't leave business cards. They leave chemical traces that could have multiple explanations. Distinguishing between biotic and abiotic processes in an alien environment with limited data is hard. Sometimes impossible without direct sampling, which we can't do from orbit. So we might end up in limbo. Strong suggestions but no confirmation. Enough evidence to justify a lander mission but not enough to declare victory. That's actually the scenario most researchers expect. Not a clear yes or no, but a probably, pending further investigation. That's how science usually works. You don't get revelation. You get provisional conclusions that get refined as new data arrives. The public doesn't like that. They want definitive answers. Life exists or it doesn't. tell us which. But reality's more complicated. We might spend the next 50 years saying Europa probably has life, without being able to prove it conclusively. Living in that uncertainty requires patience. Something modern culture isn't great at. We want answers now. We want streaming video from Europa's ocean floor showing alien fish swimming past the camera. That's not happening. What we get is spectroscopy data suggesting complex organic molecules. Magnetic field variations consistent with conductive fluids. Plume composition showing water-soluble compounds that might support metabolism. All circumstantial. All suggestive. None definitive. And we sit with that. Publish papers. Debate interpretations. Design better instruments for the next mission. That's the actual process. Not dramatic. Not cinematic. Just methodical accumulation of evidence toward increasingly confident conclusions that might take decades to reach. The icy moons force us to accept this pace. They're not going anywhere. Europa's been there for 4 billion years. It'll wait another 50 while we figure out how to study it properly. The urgency is artificial. We want answers because we're curious, but the universe doesn't care about our timeline. It operates on geological scales. Orbital periods measured in days. Ocean circulation measured in centuries. Evolutionary processes measured in millions of years. Our 70-year human lifespans are nothing against that backdrop. Which makes this whole endeavor slightly absurd. Temporary biological creatures trying to understand permanent planetary processes. Using instruments that'll fail in a decade to study worlds that have existed since the solar system formed. It's audacious when you think about it. But that's what exploration is. Temporary beings pushing against the limits of temporary understanding. Each generation builds on what the previous one learned. Each mission answers some questions and creates new ones. The researchers working on Europa Clipper won't see the lander mission. The people designing the lander won't see the submarine mission. The submarine designers won't see the deep drilling mission. But each step makes the next possible. That's how you explore an alien ocean from 500 million kilometers away. Slowly. Carefully. One impossible step at a time. Which brings us to the uncomfortable truth nobody wants to discuss. The probability calculation. What are the actual odds we find life on Europa? Not, is it there, but, will we detect it if it is? Those are different questions. Completely different. Life could exist in Europa's ocean and we might never know. The ocean's huge. 100 kilometers deep in places. Volume exceeding all Earth's oceans combined. And we're sampling tiny fractions. A few plume passes. Some surface spectroscopy. Maybe eventually a lander analyzing 1 square meter of ice. That's like trying to find whales by analyzing a single drop of seawater from the Atlantic. Possible? Technically? Likely? No. Europa's ocean could be teeming with microbial life, and our instruments might sample a barren region. Or life might cluster around specific hydrothermal vents we never get close to. Or organisms might be seasonal, dormant during our observation window. Or they might exist in forms our instruments aren't designed to detect. False negatives are a massive problem in astrobiology. You can't prove something doesn't exist just because you didn't find it. You only sampled one location at one time with one set of instruments looking for one type of biosignature. Negative results tell you almost nothing. Which means even if Europa Clipper finds nothing conclusive, the question remains open. The mission could be scientifically successful and still leave us uncertain. That's not failure. That's just reality. But here's where it gets interesting. Absence of evidence starts mattering after enough missions. One negative result means little. 5 missions over 30 years finding nothing. That shifts probabilities. Not to zero, but lower. The Bayesian calculation changes with each data point. Right now, before we've really looked, the prior probability is genuinely uncertain. Some researchers estimate 50-50 odds. Others think it's more like 10%. Nobody knows. Too many variables. But as missions accumulate data, the probability distribution narrows. Either life's signature becomes increasingly apparent or increasingly unlikely given what we're seeing. The frustrating part is how long this takes. Decades of missions. Billions in funding. All to narrow the probability range from maybe to probably or probably not. That's slow. Expensive. Uncertain. And absolutely necessary. Because finding life elsewhere, even microbial life in an alien ocean, changes everything. Not technologically. Not immediately practically, but philosophically. It answers whether biology is a cosmic inevitability or a singular accident. If Europa has life, and Enceladus has life, and maybe Titan has life, then life's everywhere. Any world with liquid water and chemical energy probably develops biology eventually. The universe is living. We're not alone. Not even close. That shifts how we see ourselves. Earth stops being special. Life stops being precious and rare. It's just chemistry that happens when conditions permit. Common. Expected. Ordinary. Some people find that comforting. Others find it diminishing. Either way, it's transformative. But what if we look and find nothing? What if Europa's ocean is sterile? What if all the icy moons are dead? That's equally important. Maybe more so. Because it suggests life's harder than we think. That liquid water and energy aren't enough. That something else is required. Some additional ingredient or condition we haven't identified. And Earth has it, but these ocean worlds don't. That makes Earth remarkable again. Not for having water or chemistry, but for crossing some threshold these other worlds couldn't reach. And we don't know what that threshold is. Both answers matter. Life everywhere changes our cosmic perspective. Life nowhere changes it differently. We learn something fundamental either way, which is why these missions matter despite the uncertainty, despite the slow pace, despite the ambiguous results we'll probably get. This isn't about satisfying curiosity, though that's part of it. It's about understanding the universe's capacity for biology. Whether life is chemistry's inevitable consequence or a profoundly improbable accident that happened exactly once. We can't answer that from Earth. We have to look elsewhere. And the icy moons are the closest, most accessible elsewhere we've got. So we build the missions, design the instruments, wait years for the data, interpret ambiguous results, propose follow-up missions, wait again. It's tedious. It's expensive. It's uncertain. And it's the only way forward. Now here's something nobody talks about. The contamination problem going both directions. We worry constantly about forward contamination, bringing Earth microbes to Europa and ruining the pristine alien environment. Every spacecraft gets sterilized, components baked, procedures documented, all to avoid accidentally seeding Europa with terrestrial biology. That's responsible, necessary, but it assumes Europa's biology, if it exists, is vulnerable to Earth organisms, that our microbes could survive there, outcompete native life, establish themselves. Maybe, maybe not. Europa's ocean is extreme by Earth standards. High pressure, low temperature, strange chemistry. Earth organisms aren't adapted to that. They'd probably die quickly. The environment might be naturally hostile to anything from our biosphere. But we don't know. So we sterilize anyway. Better safe than sorry. But here's the reverse question nobody asks. What if Europa's biology is dangerous to Earth? What if we bring samples back and they contain organisms that thrive here, that outcompete terrestrial microbes, that lack natural predators or environmental constraints? Invasive species are devastating on Earth when introduced from other continents. Imagine invasive species from another world, with completely different biochemistry, no natural checks, no evolutionary relationships with anything here. That could be catastrophic, or completely harmless. We don't know because we've never encountered alien biology. Sample return missions have to account for this. Containment protocols, quarantine procedures, analysis in isolation before exposure to Earth's environment. It's complicated, expensive, possibly excessive if Europa's organisms can't survive here, but possibly essential if they can. The irony is we might discover life on Europa and still never bring samples to Earth because the contamination risk is too high. We'd study it remotely. Send instruments instead of returning material. Keep the biospheres separate. That's frustrating from a research perspective. You want the samples. You want to analyze them properly in fully equipped laboratories. But you can't risk contaminating Earth's biosphere or Europa's. So you're stuck doing science at arm's length. Forever. Unless we develop methods to completely neutralize biological material while preserving its chemical and structural information, then you could safely return samples. But that technology doesn't exist yet, and might not be possible. The universe is full of these practical barriers. Not just technical challenges, but fundamental constraints that can't be engineered around. Another constraint nobody mentions: political continuity. These missions take decades. Decades of funding. Consistent support across multiple administrations. Different political parties. Changing budget priorities. Europa Clipper survived because it had bipartisan support. But that's rare. Most long-term projects get cancelled halfway through when priorities shift. New administration comes in, wants different flagship missions, cuts funding for the previous administration's pet projects. Science doesn't work on 4-year election cycles. It works on 20-year development timelines. Those don't align well. Which means we need international collaboration. Spreading the cost and commitment across multiple space agencies so no single election can kill the program. ESA, NASA, JAXA working together. That's how you sustain multi-decade efforts. But international collaboration is slow. Complicated. Requires diplomatic negotiation. Technology sharing agreements. Export control compliance. It's a mess. Yet it's necessary. No single country wants to fund a $10 billion program alone, especially when the payoff is uncertain and decades away. So we partner. Compromise. Negotiate. And slowly build missions that might survive long enough to reach their targets. Assuming nothing breaks. Assuming budgets hold. Assuming political will persists. Those are big assumptions. Most proposed missions never happen. They get studied, designed, prototyped, then canceled when funding dries up, or priorities change, or technical problems emerge that push costs too high. The graveyard of canceled missions is vast. Europa Orbiter, Titan Mare Explorer, Enceladus Life Finder. All studied seriously. All canceled before construction began. Europa Clipper is rare because it survived that process. Made it through design reviews. Secured funding. Actually launched. That's exceptional. And even now, there's no guarantee future missions will follow. Clipper could be the only Europa mission in our lifetime. The lander might never happen. The submarine definitely won't happen anytime soon. We might get one shot at this. One spacecraft. One dataset. And that's all. Which means interpreting that data becomes absolutely critical. Extracting every possible bit of information. Because we might not get another chance. The pressure on researchers is intense. They've waited careers for this mission. It has to work. The instruments have to function. The data has to be interpretable. Because if something fails, if results are ambiguous, there might not be a follow-up mission to clarify things. You get one chance to answer whether life exists beyond Earth. And the answer might be insufficient data. That's what keeps researchers awake at night. Not technical failure, though that's bad enough. But ambiguous success. Data that suggests something interesting but doesn't confirm anything. Living in that uncertainty for the rest of your career. Knowing the answer might exist in an ocean you can see but can't reach. That's the real challenge of exploring Europa. Not the engineering, though that's hard. Not the distance, though that's vast. But the fundamental limitation that you're trying to answer the biggest question in biology with indirect measurements of a world you can't fully access. And you might only get one attempt. Yet here's what makes Europa Clipper historically significant regardless of what it finds. It establishes the methodology, creates the template for how you study ocean worlds remotely. Every instrument, every measurement technique, every data analysis approach becomes a blueprint. Future missions to Enceladus, Titan, Ganymede, they'll build on this foundation. We're learning how to read these worlds. Developing the language needed to interpret what subsurface oceans tell us through their ice shelves. That knowledge persists even if this specific mission doesn't find life. The techniques remain useful. The calibration data becomes reference material. Understanding how ice responds to tidal heating, how salts concentrate in fractures, how plumes form and dissipate, all of that applies broadly. You're not just studying Europa. You're studying the physics of ocean worlds as a class. Which means even negative results have value. Knowing that Europa's ocean doesn't show biosignatures tells you something about where life can and can't emerge. Constrains the parameters. Narrows the search space for future efforts. Science progresses through elimination as much as discovery. And there's another angle nobody discusses much. The cultural impact of searching. The fact that humanity allocated resources, launched a spacecraft, spent years trying to answer whether we're alone. That matters philosophically even before we have results. It demonstrates what our species considers worth pursuing. Shows that curiosity about our place in the universe ranks high enough to justify significant investment. That's not trivial. In a world focused on immediate returns, quarterly earnings, election cycles, committing to a multi-decade search for extraterrestrial life represents something different. Long-term thinking. valuing knowledge for its own sake. That cultural statement matters. It influences how future generations think about science funding, about exploration, about what questions deserve sustained effort. Europa Clipper becomes part of that narrative, a marker of what early 21st century humanity chose to prioritize. Decades from now, regardless of what it finds, people will look back at this mission as a moment when we seriously attempted to answer the life question. That attempt matters. The audacity of it, the technical sophistication required, the international cooperation involved. All of that represents something worth doing, even if the answer turns out to be, we still don't know. Because the pursuit itself drives innovation. Problem solving at this level creates spillover benefits. Radiation-hardened electronics developed for Clipper get used in other applications. Power systems designed for distant operation become templates for future spacecraft. Instruments built to detect faint biosignatures find uses in Earth science, medical diagnostics, materials analysis. The engineering doesn't vanish if the science proves inconclusive. It propagates, gets refined, applied elsewhere. NASA's Technology Transfer Office exists specifically to move space-developed innovations into commercial markets. So taxpayer investment in missions like Europa Clipper generates returns beyond the immediate science. Though that's not why we do it. We do it because the question is fundamental. Does life arise wherever conditions permit? Or is Earth a cosmic fluke? That question shapes how we understand our existence, informs philosophy, theology, ethics, changes what it means to be alive if we discover we're not unique, or confirms our isolation if we search thoroughly and find nothing. Either answer matters profoundly. And you can't get that answer without looking, without building spacecraft, without making measurements. So we build Europa Clipper, launch it toward Jupiter, wait years for data, knowing the answer might not be clear, might require follow-up missions, might remain ambiguous for decades. We do it anyway. Because some questions are worth asking even when answers aren't guaranteed. Even when the timeline extends beyond single careers. Beyond political cycles. Into time frames that test institutional patience. The commitment itself becomes the statement. We care enough to try, to invest resources, to sustain focus across years. That says something about humanity worth acknowledging. Now let's address what happens if Clipper does find something. If measurements suggest biological activity, what then? The discovery process would be slow, deliberate. Multiple independent confirmations required before announcing anything. You don't claim extraterrestrial life based on single data points. You need patterns, consistency, elimination of alternative explanations. That takes time. Months of analysis. Years potentially. researchers would be cautious to the point of paranoia. Extraordinary claims require extraordinary evidence. The standard for claiming life detection is deliberately high, so initial findings would be tentative, suggestive rather than conclusive. Papers would use careful language, consistent with biological processes, difficult to explain through known abiotic mechanisms. Nothing definitive until the evidence becomes overwhelming. And even then, debate would continue. Scientists arguing over interpretation. Alternative hypotheses proposed. Demands for additional data. That's healthy. That's how science works. Skepticism until proof becomes undeniable. But assuming evidence accumulates. Multiple lines of data pointing the same direction. Consensus gradually forming that biological explanation is most likely. What happens then? First, immediate calls for follow-up missions. Sample return if possible. More sophisticated instruments. Direct access to the ocean. Funding would materialize. Political support would surge. Nothing motivates space agencies like the possibility of confirming life beyond Earth. Budgets that seemed impossible suddenly become feasible. Timelines that were decades long get compressed. National prestige enters the equation. Countries want to be part of the discovery. International collaboration intensifies. Everyone wants involvement in the biggest scientific finding in human history. Because that's what it would be. Confirmation of extraterrestrial life rewrites biology. Establishes that Genesis isn't unique. That the universe creates life wherever chemistry permits. The implications cascade through every field. Philosophy grapples with what it means. Theology adjusts frameworks. Ethics considers how we treat non-Earth life. Law debates who owns extraterrestrial organisms. Policy determines contamination protocols. It's not just science. It's civilization-level adjustment. And it starts with measurements from a spacecraft orbiting Jupiter. Data transmitted across hundreds of millions of miles. Interpreted by researchers who've dedicated careers to this question. That's the scenario Europa Clipper could enable. Not guaranteed. Maybe not even likely. But possible. And possibility is enough. Enough to justify the mission. The investment. The decades of work. Because if there's even a small chance of answering whether we're alone, you take it. You build the spacecraft. Launch it. Wait for data. Accept that results might be ambiguous. That follow-up might be needed. That certainty might take generations. You do it anyway. Because some questions define what it means to be human. Our need to understand our place in the universe. To know if life is rare or common. Special or inevitable. Those questions don't have dollar values. can't be justified through economic analysis. They're justified by being fundamental, by mattering in ways that transcend normal metrics. Europa Clipper represents that kind of question, pursued seriously, with sophisticated tools, real commitment. And now we wait. Years of flight time, then years of data collection, followed by years of analysis. The answer, if it comes, won't arrive quickly, won't be simple, might not even be definitive. But we'll know more than we do now. Understand ocean worlds better. Have methods for detecting biosignatures. Possess data to guide future missions. That's progress. Incremental. Frustrating. Necessary. The only way forward when you're trying to explore worlds you can't physically reach. When you're searching for life that might not exist, or might exist but remain undetectable with current methods. You build what you can, measure what's possible, interpret carefully, and prepare for the likelihood that this is just the beginning. That Europa Clipper is the first chapter in a much longer story, one that might not conclude in our lifetimes, but one worth starting, worth pursuing, worth the investment of resources and decades of effort. Because ultimately, the question of whether life exists beyond Earth isn't just scientific curiosity. It's existential inquiry. Who are we? Where do we fit? Is intelligence common or rare? Those questions shape everything. And Europa, with its vast subsurface ocean, represents our best near-term chance at answers. So we send Clipper. We wait. We analyze. We accept uncertainty. And we continue the search. Because that's what drives us forward. Not certainty of success, but the possibility of discovery. The chance that somewhere beneath those ice sheets, in the dark cold ocean, something lives. Something that proves we're not alone. That life finds a way. That the universe is richer and stranger than we imagined. And if we're wrong, if Europa is sterile, then we search elsewhere. Enceladus, Titan, exoplanet oceans. The search continues. Because now we know how to look, what to measure, how to interpret. Europa Clipper taught us that. Made us better at reading worlds we can't touch. And that knowledge compounds, gets refined, applied to the next target, then the next. Until eventually, maybe decades from now, maybe centuries, we find what we're looking for. Or confirm we're alone. Either way, we'll know. And knowing matters. That's what Europa Clipper is really about. Not just one mission, but the beginning of systematic search. The moment humanity decided to seriously pursue the life question. using the best tools we have, accepting the limitations, pushing forward anyway, because some answers are worth waiting for. So we're left in this strange position, waiting. Years of flight time ahead, then years of data collection, followed by years of analysis where researchers argue over interpretation and demand additional measurements before committing to conclusions. The answer won't arrive as a headline, won't be a single dramatic announcement. It'll emerge gradually through accumulated evidence, refined models, eliminated alternatives. Messy, uncertain, requiring patience nobody wants to exercise. But that's exploration at this scale. You don't get instant gratification. You get slow revelation. Data points that individually mean little but collectively suggest something profound. And maybe that's appropriate. Maybe the biggest question in biology shouldn't have a quick answer. Maybe it should require decades of effort, billions in investment, international collaboration, technical innovation we haven't achieved yet. Because if the answer comes easy, it probably isn't the right answer. Europa's ocean has existed for 4 billion years. It's not going anywhere. The question of whether life exists there has waited this long. It can wait longer while we develop proper methods to investigate. The urgency is ours, not the universe's. We want to know before we die. Want to see the answer in our lifetimes. But cosmic processes don't care about human lifespans. They operate on geological timescales, evolutionary timescales. Timelines measured in millions of years while we measure in decades. So we do what we can. Build missions that might outlast us. Collect data future researchers will analyze. Contribute to understanding that compounds across generations. That's the actual nature of this search. Not individual achievement but collective progress. Each mission adds pieces. Each dataset refines models. Each generation pushes a little further than the last. Europa Clipper is one piece. Important, but not final. It'll answer some questions and create others. Suggest follow-up investigations. Provide data that becomes more valuable over time as we develop better interpretation methods. Maybe it finds biosignatures. Maybe it doesn't. Either way, it establishes the framework. Shows what's possible with current technology. Identifies what improvements are needed. And then we build the next mission. Better instruments. Different approach. Closer access. The process continues until we have definitive answers or exhaust feasible investigation methods. That could take 50 years. Could take a century. Could take longer than human civilization persists in its current form. But the question remains worth asking, worth pursuing, worth the investment even knowing answers might not arrive in our lifetimes. Because this is what separates us from every other species on Earth. This capacity to ask questions whose answers we might never see. To pursue knowledge that benefits future generations more than ourselves. To invest in understanding purely because understanding matters. Europa's ocean holds secrets 4 billion years old. Secrets about whether life is inevitable or exceptional. Whether biology is chemistry's natural outcome or a fragile accident that happened once. We're trying to read those secrets from hundreds of millions of miles away, using instruments that can't touch what they're studying, interpreting signals that could mean multiple things. It's audacious, maybe impossible, definitely worthwhile. The search for life beyond Earth isn't just science. It's philosophy. It's existential inquiry about our place in the universe. Whether we're alone or surrounded by biology we haven't recognized yet. And we won't know until we look. Really look. With sophisticated instruments, sustained effort, decades of patience. That's what Europa Clipper represents. Not just a spacecraft. Not just a mission, but humanity's commitment to answering the biggest question we can ask. Are we alone? The answer is out there. Beneath ice sheets on distant moons. In subsurface oceans we can't access. In chemistry we don't fully understand. And we're going to find it. Not today. Not tomorrow. But eventually. Because that's what we do. We explore. We question. We search. Even when answers take decades. Even when results are ambiguous. Even when success isn't guaranteed. We send spacecraft to frozen moons. We measure magnetic fields and analyze plume chemistry. We build instruments that might detect life completely unlike ours. And we wait. Years. Decades. However long it takes. Because some questions are worth answering regardless of how long they take. Some knowledge is worth pursuing even when you might not live to see it confirmed. Europa's ocean is still there. Still hidden. Still holding whatever secrets it contains. And somewhere between now and whenever those secrets are revealed, we'll keep searching. Keep measuring. Keep pushing the boundaries of what's possible. That's the real story of Europa Clipper. Not what it finds, but what it represents. Humanity reaching toward understanding. Refusing to accept ignorance about our place in the universe. The data will come back. Slowly. Over years. We'll analyze it, debate it, build new missions based on what we learn. And eventually, maybe not in our lifetimes but in someone's, we'll know. We'll have the answer. Until then, we wait. And we search. Because that's what drives us forward. Not certainty, but possibility. The chance that beneath those ice sheets, in the dark cold ocean, something lives. Beneath a frozen shell thicker than Mount Everest is tall, an ocean larger than all of Earth's seas combined sits in complete darkness. You're probably picturing some distant exoplanet, maybe something thousands of light years away. Wrong. This ocean exists right here in our solar system, orbiting Jupiter every 3.5 days. Europa holds more liquid water than our entire planet, and NASA just launched a $5 billion mission to find out if anything is swimming in it. The numbers don't make sense at first. Europa is slightly smaller than our moon, yet somehow contains double the water volume of Earth. Where did it all come from? More importantly, how does it stay liquid when surface temperatures drop to -220 degrees Celsius? The answer involves one of the most violent gravitational relationships in the solar system, and it's the same force that might be creating the conditions for life to exist right now, roughly 390 million miles from the Sun. Jupiter's gravity doesn't just pull on Europa. It squeezes the Moon like a stress ball, over and over, every orbit. The result is tidal heating, a process so intense that it generates enough warmth to maintain a liquid ocean beneath an ice shell that would otherwise be frozen solid. But here's what makes this truly remarkable. The same gravitational torture that keeps the water liquid also cracks the ice above it, creating a dynamic surface that might be exchanging material between the frozen exterior and the hidden ocean below. Scientists discovered something strange when the Galileo spacecraft flew past Europa in the late 1990s. Jupiter's powerful magnetic field, which normally behaves in predictable ways, was getting disrupted near the Moon. Not scattered randomly, but in a pattern that suggested something conductive existed beneath the surface. The only substance that made sense was salt water, lots of it, creating its own induced magnetic field through interaction with Jupiter's magnetosphere. This wasn't speculation based on models. It was a direct measurement of something happening right then. The surface told its own story. Europa's ice shows almost no impact craters, which seems impossible for an object that's been orbiting Jupiter for billions of years. The solar system is full of debris, rocks, and ice chunks that should have been pounding this moon relentlessly. Yet Europa's surface is remarkably smooth, the smoothest solid object we've ever found. The only explanation that fits is resurfacing, ice that gets recycled and renewed, erasing old scars. Something beneath that crust is mobile enough to erase geological history. Look closer at Europa's surface and you'll see something that resembles pack ice on Earth's Arctic Ocean, except the pieces are the size of cities. These ice rafts have rotated, shifted, and refrozen in new positions. Some regions show what scientists call chaos terrain, areas where the surface has completely broken apart and reassembled into jumbled landscapes. The ice isn't just sitting there. It's moving, breaking, reforming. Underneath all that activity, an ocean is pushing upward. Then there are the streaks. Long linear features, reddish-brown in color, crisscross Europa's pale surface like veins. For years, scientists debated what these could be. Radiation damage, mineral deposits. The answer turned out to be salt, specifically magnesium sulfate, left behind when briny water from below erupted onto the surface and evaporated. The ocean isn't just sitting quietly in the dark. It's interacting with the ice shell above it, possibly in ways that could bring nutrients down and waste products up, exactly the kind of exchange that life would need. Water alone doesn't make a habitable world. You need the right chemistry, the right energy sources, the right conditions maintained over geological timescales. Europa's ocean started out wrong for life, too acidic, loaded with sulfates and carbon dioxide. But something changed. Over 4.5 billion years, chemical reactions transformed that harsh environment into something that resembles Earth's oceans. The water became chloride-rich, with dissolved magnesium, sodium, potassium, and chlorine floating in concentrations similar to our seas. The ocean evolved. In 2024, the James Webb Space Telescope detected carbon dioxide on Europa's surface, specifically in a region called Terra Regio. This wasn't just any carbon dioxide. Analysis showed it came from below, from the subsurface ocean, deposited recently in geological terms. Carbon is fundamental to life as we know it. Finding it concentrated in an area where the ice has clearly been disrupted, where material from the ocean appears to have reached the surface, isn't proof of life. But it's exactly what you'd want to see if you were looking for habitable conditions. Then came the ammonia discovery. Scientists re-examining old Galileo data found faint signals of ammonia-bearing compounds near fractures in the ice. Ammonia matters for two reasons. First, it's a nitrogen-bearing molecule, and nitrogen is essential for amino acids, DNA, proteins, all the molecular machinery that biology runs on. Second, ammonia acts as antifreeze, lowering water's freezing point. In Europa's environment, where temperatures hover around freezing even in the ocean, ammonia could create pockets of liquid water that would otherwise freeze solid. Life, if it exists, might be clustering around these ammonia-rich zones. The energy question looms over everything. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly through food chains built on photosynthetic organisms. Europa receives 25 times less sunlight than Earth, and none of that reaches the ocean anyway. So where would the energy come from? Tidal heating provides warmth, but life needs chemical energy, electrons moving from one molecule to another, reactions that release usable power. One possibility involves the same process that supports life at hydrothermal vents on Earth's ocean floor. Hot water, heated by geological activity, erupts from cracks in the seafloor, carrying dissolved minerals and chemicals. When this hot, chemically rich water meets cold ocean water, reactions occur spontaneously. Microbes harvest the energy from these reactions, building entire ecosystems in complete darkness. Europa might have similar vents if its seafloor remains geologically active. That's where the debate gets contentious. Recent calculations from Washington University in St. Louis suggest Europa's seafloor might be cold and geologically quiet. The tidal heating that keeps the ocean liquid might not penetrate deep enough to warm the rocky core below. Without volcanic activity, without fracturing and faulting that exposes fresh rock to water, the chemical reactions that microbes could feed on become much harder to sustain. Europa's core likely cooled billions of years ago, and unlike Earth's interior, which still churns with heat from radioactive decay, Europa might not have enough internal energy to power active geology at the seafloor. But other researchers aren't convinced the story ends there. Even without volcanic hydrothermal vents, chemical energy could come from different sources. Radiation from Jupiter constantly bombards Europa's surface, breaking apart water molecules and creating hydrogen peroxide, oxygen, and other oxidants. These chemicals could work their way down through the ice, eventually reaching the ocean. Meanwhile, the seafloor, even if cold, still contains minerals that can react with water through a process called serpentinization. Mix oxidants from above with reduced minerals from below, and you've got potential energy for life. There's another pathway that nobody predicted until recently. The ice shell itself might be producing nutrients. Jupiter's radiation doesn't just create oxidants, it also generates complex organic molecules from simpler compounds on the surface. Normally, these would just accumulate in the ice, chemically isolated from the ocean. But a process called crustal delamination could change that. As denser, salt-rich ice forms near the surface, it could sink through the lighter ice below, carrying those surface nutrients down into the ocean like a conveyor belt. The ice shell wouldn't just be a barrier. It would be a chemical factory and delivery system. The plume question adds another layer of mystery. In 2012, the Hubble Space Telescope captured what appeared to be water vapor erupting from Europa's south polar region, shooting 200 kilometers into space, more than 20 times the height of Mount Everest. If real, these plumes would be a gift to future missions. Instead of drilling through miles of ice, a spacecraft could simply fly through a plume and collect samples of ocean water directly. But proving the plumes exist has been surprisingly difficult. Hubble saw the plume signature once, maybe twice. The Galileo spacecraft might have flown through one in 1997, though that interpretation came decades after the fact from reanalysis of magnetic field data. The James Webb Space Telescope looked for plumes in 2023 and found nothing. Other observations using radio telescopes searched for the molecules that should be present in plumes and came up empty. Either the plumes are rare, episodic events that only happen under specific conditions, or they're much weaker than initially thought, or some of those early detections were misinterpretations of noisy data. The uncertainty doesn't diminish Europa's potential. Plumes or no plumes, the ocean exists. The chemistry appears favorable. The energy sources, while debated, seem sufficient for at least microbial life. What Europa needs now is not more speculation from a distance, but direct investigation up close. That's exactly what NASA launched on October 14, 2024. Europa Clipper is the largest spacecraft NASA has ever built for a planetary mission. With its solar arrays deployed, it stretches over 100 feet, roughly the length of a basketball court. Those enormous solar panels are necessary because Jupiter sits 5 times farther from the Sun than Earth, meaning sunlight there is 25 times weaker. Clipper will spend 6 years traveling 1.8 billion miles, using gravity assists from Mars and Earth to slingshot itself toward Jupiter, arriving in April 2030. The mission design is clever out of necessity. Jupiter's radiation environment is brutal, intense enough to fry electronics in a matter of hours if a spacecraft stayed near Europa continuously. Instead, Clipper will orbit Jupiter itself, swooping past Europa for close flybys, then retreating to safer distances. Over 4 years, it will complete 49 of these flybys, each one bringing it within 16 miles of the surface in some cases. During each pass, the 9 instruments on board will have just minutes to gather data before radiation levels become dangerous again. Those instruments represent the cutting edge of planetary science. Radar will peer through the ice, measuring its thickness and looking for water pockets within the shell. Magnetometers will map Europa's induced magnetic field in far greater detail than Galileo could, potentially revealing the ocean's depth and salinity. Spectrometers will analyze the surface composition, identifying organic molecules, salts, and other chemicals that might have come from below. Cameras will image the surface at resolutions high enough to see features the size of a car. One instrument stands out for its potential to make history. The Surface Dust Analyzer will collect ice grains and dust particles as Clipper flies through the space just above Europa's surface. By analyzing the composition and trajectories of these particles, scientists can determine where they came from and what they're made of. If plumes exist, SUDA will fly right through them, collecting samples of ocean water without the spacecraft ever touching the surface. Laboratory tests have shown something remarkable about instruments like SUDA. Scientists fired ice grains containing tiny amounts of bacterial cell material at a prototype mass spectrometer under conditions simulating a Europa flyby. Even when only 1% of a grain consisted of biological material, the instrument detected it. Clipper carries similar technology. If microbial life exists in Europa's ocean, and if that life gets ejected into space through plumes or surface fractures, and if SUDA happens to sample those particles, the instrument could detect alien biology directly. Nobody on the mission is publicly betting on that outcome. The odds of all those conditions aligning seem astronomical. But the fact that it's even possible, That we've built a spacecraft capable of detecting extraterrestrial life if it's there, represents a profound shift in space exploration. For perspective, we've never attempted anything quite like this before. Every previous mission to detect extraterrestrial life required landing, drilling, or direct sampling. Clipper could find it simply by flying through the right patch of space at the right moment. The margin for error is razor thin, but the payoff would rewrite biology textbooks. Understanding what makes this possible requires examining Europa's surface in detail. When Voyager 1 flew past in 1979, it sent back images that baffled scientists. Europa looked nothing like a typical moon. No impact craters pockmarked the surface. No mountains broke the horizon. Instead, the images showed a smooth, cracked sphere crisscrossed by dark reddish-brown streaks and linear fractures stretching hundreds of miles. Those features told a story. The lack of craters meant the surface was young, geologically speaking, probably only 40 to 90 million years old. On cosmic timescales, that's yesterday. Something was constantly resurfacing Europa, erasing ancient impact scars. The cracks suggested movement, tectonic activity driven not by internal heat alone but by the flexing of the ice shell as Jupiter's gravity squeezed and released the Moon every 3–5 days. The reddish-brown material coating those fractures became a mystery that took decades to solve. Early theories proposed sulfur compounds ejected from volcanic Io and deposited on Europa's surface. But spectroscopic analysis told a different story. The material appeared to be salts, magnesium sulfate primarily, mixed with other minerals. These weren't deposits from space. They came from below. When Europa's ice shell cracks under tidal stress, liquid water from the ocean can seep upward through the fractures. As it reaches the surface, the extreme cold and vacuum of space cause it to evaporate instantly, leaving behind dissolved salts and minerals. Those deposits form the reddish streaks we see. The color comes from radiation damage. Jupiter's intense magnetic field accelerates charged particles to enormous speeds, and when those particles slam into the surface, they break chemical bonds and create new compounds that absorb light differently. This process matters because it means Europa's surface isn't isolated from the ocean below. There's exchange happening, material moving between the deep ocean and the exposed surface. James Webb Space Telescope observations confirmed this in 2023 when astronomers detected carbon dioxide concentrated in a region called Terra Regio, an area of chaos terrain where the surface appears jumbled and disrupted. The carbon dioxide didn't come from space. Isotopic analysis showed it originated in the subsurface ocean and reached the surface recently, geologically speaking, probably within the last few hundred years. Terra Regio itself reveals how dynamic Europa's surface can be. Chaos terrain forms when warm ice or liquid water rises from below, melting or disrupting the overlying ice shell. The result looks chaotic because it is: blocks of ice tilted at odd angles, fractured and refrozen in new configurations, surface material replaced by fresher ice from deeper layers. These regions offer windows into Europa's interior composition. Then there's the question of plumes. In 2012, Hubble observations suggested water vapor erupting from Europa's south polar region, shooting 125 miles into space before falling back to the surface. The detection was tentative, based on ultraviolet spectroscopy showing what appeared to be hydrogen and oxygen atoms where none should be. Follow-up observations in 2016 provided additional evidence. Researchers analyzing old Galileo data discovered that when the spacecraft flew past Europa in 1997, it might have passed directly through a plume without anyone realizing it at the time. But plumes remain controversial. Later observations with more sensitive instruments found nothing. The James Webb Space Telescope examined Europa thoroughly and detected no active plumes. Radio telescope arrays saw no molecular emissions. Either the earlier detections were misinterpreted, or plumes on Europa are sporadic, erupting only occasionally under specific conditions. Models suggest that if plumes exist, they're most likely when Europa reaches the farthest point in its orbit from Jupiter. At that moment, tidal forces stretch the Moon maximally, potentially opening cracks wide enough for pressurized water to escape. The plumes wouldn't be steady geysers like those on Saturn's moon Enceladus. They'd be brief, localized eruptions that might occur every few orbits or less frequently still. This uncertainty actually increases Clipper's importance. The spacecraft will fly past Europa 49 times over 4 years, sampling different locations under different orbital conditions. If plumes exist, Clipper has excellent odds of encountering one. If they don't exist, or if they're too weak to detect remotely, Clipper will still gather material from Europa's exosphere, the thin envelope of gas and dust particles surrounding the Moon. Every object in space loses material to its surroundings. Solar radiation and Jupiter's magnetospheric particles constantly bombard Europa's surface, breaking molecular bonds and ejecting atoms and molecules into space. Some of that material escapes entirely. Some falls back. And some lingers in a thin cloud around the Moon. SUDA will sample that cloud, collecting particles that originated on the surface or potentially from the ocean itself if exchange processes are active. Recent discoveries add weight to the idea that Europa's surface and ocean communicate regularly. Analysis of old Galileo spectrometer data revealed ammonia-bearing compounds near surface fractures. Ammonia is significant for 2 reasons. First, it's a nitrogen compound, and nitrogen is essential for life as we know it, playing key roles in amino acids, DNA, and proteins. Second, ammonia lowers water's freezing point. An ocean containing dissolved ammonia could remain liquid at temperatures several degrees below 0 Celsius, potentially staying fluid even in regions where pure water would freeze. The ammonia detection came from reanalyzing data that had sat in archives for decades. Scientists applied modern processing techniques to old near-infrared observations and found faint spectral signatures that earlier analysis had missed. The compounds appeared concentrated near fractures and pits, exactly where you'd expect material from below to reach the surface. This pattern keeps repeating. Every time researchers look more carefully at Europa, they find more evidence of an active world. The surface isn't a static ice shell sitting atop a stagnant ocean. It's a dynamic interface where processes from below continuously reshape what we see from above. Cracks form and heal. Chaos terrain disrupts and refreezes. Salts and minerals migrate upward. Carbon dioxide deposits in specific locations. Ammonia appears near fractures. All of this paints Europa as a world where the ocean isn't sealed away forever beneath impenetrable ice. It's accessible, at least in principle. Material from the ocean reaches the surface through various processes. That's what makes Clipper's mission feasible without landing or drilling. The Moon itself brings samples to the surface. But here's what nobody can answer yet: how much exchange actually occurs? Is it constant and widespread, or rare and localized? Do these processes deliver enough material from the deep ocean to the surface that Clipper can sample it? Or does radiation and weathering destroy organic molecules before they can be detected? These questions matter because they determine what Clipper will find. If exchange is robust and frequent, the spacecraft should detect clear chemical signatures from the ocean, potentially including organic compounds or even biosignatures. If exchange is minimal or if surface conditions destroy delicate molecules quickly, Clipper might see only heavily altered material that doesn't reflect the ocean's true composition. The mission design acknowledges this uncertainty. Clipper's instruments are built to detect a wide range of compounds at very low concentrations. The radar can peer through several miles of ice, potentially detecting liquid water pockets trapped within the shell. Magnetometers will map the induced magnetic field with unprecedented precision, revealing ocean depth and conductivity. Cameras will image the surface at resolutions allowing scientists to identify the freshest terrain, where material from below reached the surface most recently. That last capability could prove crucial. If Clipper can identify very young surface features, areas that formed within the last few years or decades, those locations offer the best chance of finding pristine ocean material before radiation has had time to alter it significantly. Timing matters in ways that aren't immediately obvious. Europa's orbit creates predictable patterns. Every 3-5 days, the Moon completes one trip around Jupiter. That orbital period determines when tides peak, when ice flexes most dramatically, and potentially when material from below has the best chance of reaching the surface. Clipper's mission design accounts for this. The spacecraft won't arrive at random moments. Its flybys will be timed to capture Europa at different points in its orbital cycle, sampling conditions when tidal forces are strongest and when they're weakest. This approach should reveal whether surface activity varies with orbital position. But there's a complication. Europa's surface doesn't respond instantly to tidal forces. Ice has memory. When stress builds, cracks don't necessarily open immediately. They might propagate hours or days later. When tidal forces relax, fractures don't seal up right away. Material could continue rising through a crack long after the peak stress has passed. This delayed response makes prediction difficult. Scientists can calculate exactly when tidal forces reach maximum strength. They can't say with certainty when a particular crack will open or when water might breach the surface. Clipper will have to sample the Moon repeatedly, building statistical understanding of how surface activity correlates with orbital mechanics. The spacecraft's trajectory creates its own set of constraints. Radiation near Jupiter is intense. Europa orbits deep within Jupiter's magnetosphere, where trapped charged particles create a radiation environment that would destroy unshielded electronics within hours. Clipper can't orbit Europa directly because sustained exposure would kill the spacecraft. Instead, it orbits Jupiter on a highly elliptical path designed to bring it close to Europa periodically while spending most of its time farther out where radiation is less severe. Each close approach lasts only hours. The spacecraft swoops in, gathers data frantically, then retreats to a safer distance. Those brief encounters must be choreographed precisely. Different instruments need different viewing geometries. Cameras want sunlight illuminating the surface at specific angles to reveal topography. Spectrometers need different lighting to identify surface composition. The radar works best when looking straight down through the ice. Mission planners spent years designing a sequence of flybys that balances these competing needs. Some passes prioritize imaging. Others focus on spectroscopy or radar. A few are optimized for sampling material above the surface, flying through regions where plumes might be active. The word "might" appears frequently in mission documentation. Plumes remain one of Europa's biggest mysteries. Hubble spotted what appeared to be water vapor erupting from the surface in 2012. Additional observations in 2014 and 2016 found similar features. These weren't continuous geysers like those on Saturn's moon Enceladus. They appeared intermittently, visible during some observations but absent during others. More recent observations haven't confirmed the plume detections. James Webb Space Telescope looked for plumes in 2023 and found nothing. That doesn't mean the earlier detections were wrong. It means plumes, if they exist, are sporadic and localized. This uncertainty shaped Clipper's design. The spacecraft carries instruments specifically built to detect and analyze plume material. But it doesn't depend on plumes existing. If Europa is actively venting ocean water into space, Clipper will sample it. If plumes are rare or absent, the mission can still accomplish its goals through remote sensing. That flexibility is critical because nobody knows what Clipper will actually encounter. Models predict certain features. Observations suggest others. But Europa has surprised scientists before. Every time new data arrives, it reveals something unexpected. Take chaos terrain. These are regions where the surface appears to have broken apart and refrozen in a jumbled mess. The first chaos terrain identified decades ago looked like enormous ice flows had drifted apart, rotated, and then frozen back together. Scientists proposed that liquid water or warm ice had risen from below, disrupting the solid surface. Higher resolution images complicated that picture. Some chaos regions show features that don't match simple flooding models. Others have characteristics suggesting multiple episodes of disruption. The process creating chaos terrain isn't straightforward melting and refreezing. Something more complex is happening. Carbon dioxide detections added another layer. Terra Regio, one of the largest chaos regions, shows concentrated carbon dioxide deposits. The carbon appears recently placed, geologically speaking. It hasn't been sitting on the surface for millions of years getting degraded by radiation. Something delivered it relatively recently. If that carbon came from the ocean, it means chaos terrain represents active exchange zones. These find ancient scars from billions of years ago. They're places where the ocean still communicates with the surface. That makes them prime targets for Clipper. But here's the challenge. Terra Regio covers an area larger than California. Concentrated carbon dioxide means higher levels than surrounding terrain, not a single rich deposit. The spacecraft will fly over this region multiple times, but each pass covers only a narrow swath. Finding the exact spots with the strongest signals requires careful targeting. Clipper's cameras can image at resolutions down to 50 centimeters per pixel during the closest approaches. That's detailed enough to see individual ice blocks and small-scale surface textures. But at that resolution, each image covers only a tiny fraction of Europa's surface. Taking pictures of everything at maximum resolution would require thousands of years. The mission strategy involves multiple resolution tiers. Wide area imaging identifies interesting regions. Moderate resolution imaging characterizes those regions in more detail. High resolution imaging targets the most promising specific features. This hierarchical approach maximizes the science return from limited flyby time. Similar logic applies to spectroscopy. Clipper carries two spectrometers, one working in visible and near-infrared wavelengths, another in thermal infrared. These instruments can identify surface composition, but they need time to gather enough light for clear signatures. The spacecraft can't point both spectrometers at every interesting feature during every flyby. Prioritization becomes necessary. Mission planners have already identified dozens of high-priority targets based on existing data. As Clipper begins returning its own observations, that target list will evolve. Early flybys will reveal new features that demand closer inspection during later passes. This iterative process mirrors how Galileo explored the Jupiter system in the 1990s. That mission's early observations raised questions that later observations addressed. Unexpected findings forced mission planners to revise strategies mid-mission. Clipper will likely follow a similar pattern. One advantage Clipper has is processing power. Galileo's computers had less capability than a modern smartphone. Data had to be compressed heavily before transmission to Earth, losing detail. Clipper's systems can do more onboard processing, making smarter decisions about what data to prioritize for transmission. That matters because communication bandwidth is limited. Europa sits over 600 million kilometers from Earth at Jupiter's closest approach. Radio signals take 33 to 52 minutes to travel one way, depending on planetary positions. The spacecraft can transmit data at rates up to 14 kilobits per second under optimal conditions, far slower than your internet connection. A single high-resolution image from Clipper's cameras might contain hundreds of megabits of data. Transmitting one image could take hours. The spacecraft will generate far more data during each flyby than it can possibly send home in the weeks between encounters. Onboard systems must decide what to transmit first. Engineers program priorities into Clipper's software. Certain measurements take precedence. Data from instruments that can't repeat an observation get transmitted before data from instruments that will have another chance. But the system also allows ground controllers to request specific data sets when something particularly interesting appears. This semi-autonomous approach represents decades of lessons learned from planetary missions. Early spacecraft were essentially remote-controlled robots. Every command came from Earth. Later missions gained more autonomy, able to execute pre-planned sequences without constant ground contact. Clipper sits somewhere between, capable of independent operation but still taking direction from mission control. That balance will be tested during the mission's most critical moments. When Clipper makes its closest approaches to Europa, sometimes skimming just 25 kilometers above the surface, communication delays mean ground controllers can't respond to unexpected situations in real time. The spacecraft must handle problems itself. Radiation poses the biggest threat during these close passes. Europa orbits within Jupiter's intense radiation belts. The spacecraft's electronics sit inside a vault with thick aluminum walls, but radiation still penetrates. Over time, cumulative exposure will degrade systems. Some components will fail eventually. The question is whether they'll last long enough to complete the mission. Engineers designed Clipper's radiation vault using techniques borrowed from nuclear reactor shielding. The walls use interlocking aluminum plates that scatter incoming particles, reducing their energy before they reach sensitive electronics. But aluminum alone can't stop everything. High-energy protons still penetrate. Some will strike memory chips, flipping bits from 0 to 1 or back again. Most bit flips won't matter. They'll occur in unused memory locations or get corrected by error-checking systems. Others will cause software glitches that the spacecraft can recover from by rebooting. A few might prove catastrophic. Mission planners accept this risk because there's no alternative. Clipper must operate in Jupiter's radiation environment to study Europa. The spacecraft carries redundant systems for critical functions. If one computer fails, another takes over. If a sensor stops working, others can partially compensate. This redundancy adds weight and complexity, but it's necessary insurance. The most vulnerable moment comes during each close flyby. Radiation intensity increases dramatically as Clipper drops toward Europa's surface. The spacecraft spends only minutes in the most intense zones, but those minutes accumulate. After 49 flybys, cumulative radiation exposure will reach levels that would kill a human in hours. Some spacecraft systems will certainly fail before the mission ends. The question is which ones and when. What happens if a critical system fails during flyby number 20? Mission planners have contingency protocols. If the main computer crashes, the backup takes control and executes pre-programmed safe mode procedures. The spacecraft points its antenna toward Earth and waits for instructions. Ground controllers assess the situation and upload new commands. This recovery process takes days. The spacecraft misses its next flyby opportunity, but the mission continues. Total mission failure becomes likely only if multiple redundant systems fail simultaneously. Probability calculations suggest this scenario is unlikely but not impossible. Radiation damage is partly random. A particularly energetic particle might strike a critical component in just the wrong way, causing cascading failures. Or gradual degradation might weaken multiple systems until a minor problem triggers total collapse. NASA accepted a calculated risk by approving this mission. Previous Jupiter orbiters, like Juno, stay farther from the planet and experience less radiation. Clipper ventures closer because Europa's science value justifies the danger. But there's no guarantee the spacecraft will complete all 49 planned flybys. Mission success is measured in data returned, not flybys completed. Assuming Clipper survives long enough to complete its primary mission, what comes next? The spacecraft carries enough fuel for potential mission extensions. If key systems remain functional after the planned flybys, NASA might approve additional observations. But Clipper can't stay at Jupiter indefinitely. Eventually, radiation damage will accumulate beyond recovery. When that happens, the spacecraft has one final task. Planetary protection protocols require that Clipper not contaminate Europa with Earth microbes. The spacecraft was assembled in clean rooms, but complete sterilization is impossible. Some hardy bacteria almost certainly survived the construction process, hiding in cracks and crevices. If Clipper crashed into Europa, those microbes might contaminate the subsurface ocean, compromising future searches for indigenous life. To prevent this, mission planners will deliberately crash Clipper into Jupiter or one of the other Galilean moons when the mission ends. The intense heat of atmospheric entry will vaporize any remaining biological contamination. This controlled destruction ensures Europa remains pristine for future missions. It also means Clipper is a one-way mission. The spacecraft will never return to Earth. Understanding what Clipper might find requires understanding what scientists already know about Europa's ocean. Galileo provided the first strong evidence for liquid water beneath the ice. Magnetic field measurements showed that something electrically conductive exists below the surface. In Europa's case, that something is almost certainly a global ocean of salty water. How salty? Estimates suggest Europa's ocean contains dissolved salts at concentrations similar to Earth's oceans, roughly 35 grams per liter. Magnesium sulfate appears particularly abundant based on spectroscopic observations of surface ice. That composition matters because it affects the ocean's chemistry and potential habitability. Recent analysis of old Galileo data revealed ammonia-bearing compounds on Europa's surface, concentrated near fractures where subsurface material might have emerged. Ammonia is chemically interesting for several reasons. It contains nitrogen, an essential element for life as we know it. Ammonia also lowers water's freezing point, potentially allowing liquid to exist at temperatures where pure water would freeze. Where did Europa's ammonia come from? Two possibilities exist. It might have been present in the original material that formed Europa billions of years ago, trapped in ice and rock. Or it might be produced by chemical reactions in the subsurface ocean today. Distinguishing between these scenarios requires understanding Europa's internal chemistry. The ocean's temperature provides another clue about habitability. Tidal heating from Jupiter should keep the ocean slightly above freezing, perhaps near 0 degrees Celsius. But the ocean isn't uniformly cold. Heat flows from Europa's rocky interior toward the ice shell. Temperature gradients create circulation patterns, potentially mixing nutrients throughout the water column. Does Europa's seafloor host hydrothermal vents like those found in Earth's oceans? This question sparked intense debate in early 2026 when researchers published calculations suggesting Europa's tidal heating might be insufficient to drive seafloor volcanism. Their models indicated that Europa's rocky core cooled long ago, leaving the seafloor geologically quiet. On Earth, hydrothermal vents support rich ecosystems independent of sunlight. Microbes harvest chemical energy from compounds dissolved in hot vent fluids. These ecosystems demonstrate that life doesn't require photosynthesis. Chemical energy alone can sustain biological communities. If Europa lacks hydrothermal activity, one potential energy source for life disappears. But the debate isn't settled. Other researchers proposed alternative mechanisms that might support habitability without requiring active volcanism. Radiation from Jupiter bombards Europa's surface, breaking chemical bonds in ice and creating reactive compounds. These radiation-produced chemicals might work their way down into the ocean through a process called crustal delamination. Here's how that might work. Dense, chemically altered ice on Europa's surface becomes heavier than the ice below it. Gravity pulls the dense material downward while lighter ice rises, similar to how Earth's tectonic plates move. This overturning process could transport surface chemicals into the ocean over millions of years, providing nutrients that life might use. Another possibility involves serpentinization, a chemical reaction between water and certain types of rock. When water percolates through olivine-rich rock, it triggers reactions that produce hydrogen gas and other compounds useful to microbes. This process occurs on Earth's seafloor even without volcanic activity. If Europa's rocky interior contains the right minerals, serpentinization might generate chemical energy regardless of whether the seafloor is geologically active. These competing models highlight how much remains unknown about Europa's interior. Clipper's measurements will constrain the possibilities. Magnetic field observations can reveal how thick the ocean is and how conductive it is, providing clues about salt concentration and temperature. Gravity measurements during flybys will reveal density variations in Europa's interior, indicating how the Moon's mass is distributed between ice, water, and rock. The ice shell's thickness matters tremendously for future exploration. If the ice is only a few kilometers thick, a future lander mission might drill through it to reach the ocean directly. If the ice extends 15 or 20 kilometers deep, drilling becomes far more challenging. Clipper's ice-penetrating radar will measure thickness by timing how long radio pulses take to bounce off the ice-ocean boundary. Surface features provide additional clues about ice thickness. Chaos terrain, regions where the surface appears jumbled and disrupted, might form when warm ice rises from below, partially melting the overlying crust. The size and distribution of chaos terrain features can constrain thermal models of the ice shell. One particularly intriguing feature is Terra Regio, a region where recent observations detected carbon dioxide concentrated on the surface. Spectroscopic analysis suggests this carbon dioxide came from the subsurface ocean, not from asteroid impacts. That finding implies relatively recent exchange between the ocean and surface, possibly within the last few million years. If material from the ocean does reach the surface, it might carry chemical signatures of whatever exists in the water below. Organic molecules, if present, would be broken down by radiation quickly. But inorganic compounds would persist longer. Clipper's spectrometers will search for these chemical fingerprints, mapping their distribution across Europa's surface. The mission's most ambitious goal involves detecting life directly, though few scientists expect this outcome. One of Clipper's instruments, SUDA, will analyze tiny ice grains and dust particles as the spacecraft flies through the tenuous cloud of material surrounding Europa. Laboratory tests showed that SUDA can detect bacterial cell material in ice grains even when only 1% of the grain consists of biological matter. If Europa has plumes that occasionally erupt from the surface, SUDA might sample them. Previous observations from Hubble suggested plumes might exist, rising as high as 200 kilometers above the surface. But more recent observations with the James Webb Space Telescope found no evidence of active plumes during the periods observed. This doesn't mean plumes don't exist. It means if they do exist, they're sporadic, weak, or happening in places we haven't looked at the right times. Europa might be venting material only occasionally, perhaps when tidal stresses reach certain thresholds during specific points in its orbit. The Moon experiences maximum tidal flexing when it's farthest from Jupiter, and that's when plumes would most likely occur. Think about trying to photograph lightning. You might point your camera at the sky for hours and see nothing, but that doesn't prove lightning never happens. You need to be looking at the right place at the right time. Europa might work the same way. The surface could be quiet for months or years, then suddenly release a burst of water vapor that lasts only hours before subsiding. Clipper's trajectory was designed with this uncertainty in mind. The spacecraft won't orbit Europa directly. Instead, it will orbit Jupiter and make close flybys of Europa every few weeks. Each flyby will take the spacecraft through different regions above Europa's surface at different times in the Moon's orbital cycle. This approach maximizes the chances of intercepting a plume if one happens to erupt during the mission. The spacecraft's path will carry it as low as 25 kilometers above Europa's surface during some passes. That's remarkably close for a spacecraft traveling at several kilometers per second. At that altitude, SUDA will be positioned to capture ice grains ejected from any active plumes. Even if no dramatic eruptions occur, the instrument should still detect particles knocked off the surface by micrometeorite impacts or sputtered away by Jupiter's intense radiation. Radiation poses both a challenge and an opportunity. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than Earth's Van Allen belts. Europa orbits within these belts, and the Moon's surface receives a radiation dose that would be lethal to any exposed organism within hours. This radiation constantly bombards the ice, breaking chemical bonds and creating reactive compounds. On one hand, this makes Europa's surface inhospitable. No life could survive exposed on the surface for any meaningful length of time. But on the other hand, the radiation creates oxidants, molecules with extra oxygen atoms that can participate in chemical reactions. These oxidants might accumulate in the ice and eventually make their way down to the ocean through the processes discussed earlier. If they do, they could provide an energy source for life independent of sunlight. Earth's deep ocean vents support ecosystems using chemical energy rather than photosynthesis. Microbes near these vents metabolize hydrogen sulfide and other chemicals released by geological activity. Europa's ocean might host similar communities, except the energy would come from radiation-produced oxidants rather than volcanic chemistry. Testing this hypothesis requires understanding what chemicals actually exist in Europa's ocean. Clipper's infrared spectrometers will map the composition of surface ice in detail, identifying organic molecules, salts, and other compounds. Different materials absorb infrared light at different wavelengths, creating unique spectral signatures. By analyzing these signatures, scientists can determine what's present and in what concentrations. The mission will pay particular attention to regions where subsurface material might have recently reached the surface. Chaos terrain and the areas around large fractures are prime targets. If ocean water has indeed been exposed at these locations, it might still retain some of its original chemistry before radiation alters everything beyond recognition. Temperature measurements add another layer of information. Europa's surface averages around -160 degrees Celsius at the equator and drops to -220 near the poles. But thermal cameras can detect warm spots where heat from below might be reaching the surface more easily. These thermal anomalies could mark places where the ice is thinner or where liquid water has recently been present near the surface. One instrument, reason, will be especially important for understanding ice thickness. This ice-penetrating radar transmits radio pulses downward and measures how long they take to bounce back. Ice and water reflect radio waves differently, so the radar can distinguish between solid ice and liquid water below. By measuring the time delay and signal strength of return pulses, scientists can map the ice shell's thickness across different regions. If the ice varies in thickness significantly, that tells us something important about Europa's interior dynamics. Uniform thickness would suggest a relatively stable ice shell with consistent heat flow from below. Variable thickness implies more complex processes, perhaps convection cells in the ice or localized heating from tidal friction. These variations would affect how easily material can move between the ocean and surface. The radar will also search for liquid water pockets within the ice itself. Some models suggest the ice shell might not be a solid block but rather a mixture of pure ice, slushy layers, and isolated liquid reservoirs. These subsurface lakes, if they exist, could be important intermediate environments between the ocean and the surface. They might be more accessible than the deep ocean while still being protected from surface radiation. Gravity measurements during each flyby will reveal Europa's internal structure more broadly. As Clipper approaches Europa, the Moon's gravity will pull slightly on the spacecraft, changing its velocity in ways that can be measured precisely using radio signals sent back to Earth. By analyzing these velocity changes during multiple flybys, scientists can construct a gravity map of Europa. This map shows where mass is concentrated within the Moon. A thick ice shell and deep ocean would produce one gravity signature. A thin ice shell and shallow ocean would produce another. The measurements will also reveal whether Europa's rocky interior is differentiated, with heavier elements sinking toward the core, or whether it remains a more uniform mixture. Magnetic field measurements will complement the gravity data. Europa's induced magnetic field arises because Jupiter's powerful magnetic field sweeps past the Moon every 11 hours as Jupiter rotates. This changing magnetic field induces electrical currents in any conductive material inside Europa. Salt water conducts electricity far better than ice or rock, so the strength and behavior of Europa's induced magnetic field provides information about the ocean's thickness, depth, and salinity. The magnetometer aboard Clipper will measure Europa's magnetic field during each flyby, building up a detailed picture of how it varies across the surface and over time. These measurements, combined with the gravity and radar data, will constrain models of Europa's interior structure more tightly than ever before. All of these investigations point toward a single overarching question. Does Europa have the conditions necessary for life? Notice that's different from asking whether life actually exists there. Clipper wasn't designed to search for life directly, though SUDA might accidentally detect it if organisms happen to be present in surface ice grains. The mission's goal is more fundamental, determining whether Europa could support life. That requires three things. Liquid water. Check. Europa almost certainly has a global ocean. Chemical building blocks. Probably. We've detected carbon dioxide, salts, and ammonia on the surface, all of which likely came from the ocean. Energy sources. This is the uncertain part. If the seafloor is geologically active, hydrothermal chemistry could provide energy. If not, radiation-produced oxidants might fill that role, assuming they can reach the ocean in sufficient quantities. Clipper will address each of these requirements. The mission will confirm the ocean's existence beyond any doubt, measure its properties, and determine its composition. It will assess how much exchange occurs between the ocean and surface. It will search for evidence of recent geological activity. And it will evaluate whether the Moon's internal heat budget allows for seafloor processes that could generate chemical energy. The spacecraft will also document Europa's geology in unprecedented detail. High-resolution cameras will image the surface at scales of less than 1 meter per pixel in selected areas, revealing small-scale features that might indicate recent activity. Wider area images at lower resolution will provide context, showing how different terrain types relate to one another. Scientists will use these images to construct detailed maps of Europa's surface, identifying regions of interest for potential future missions. If plumes are detected, their source locations will be prime targets. If certain areas show strong evidence for thin ice or recent water exposure, those become candidates for a future lander or even a mission that could penetrate the ice. But all of that comes after Clipper arrives in April 2030. Between now and then, the spacecraft must survive a journey of nearly 3 billion kilometers through deep space. It must execute a precisely timed gravity assist at Earth in December 2026, using our planet's gravity to accelerate toward Jupiter. And it must withstand Jupiter's intense radiation environment once it arrives, a challenge that required extensive shielding and radiation-hardened electronics. The mission engineers designed Clipper's trajectory specifically to minimize radiation exposure. Instead of orbiting Europa directly, which would subject the spacecraft to constant bombardment, Clipper orbits Jupiter in a highly elliptical path. Each orbit brings it close to Europa for a brief flyby, then carries it far away from Jupiter's most intense radiation belts. This approach allows the spacecraft to accumulate the necessary science data while spending minimal time in the harshest environment. Even so, the radiation dose adds up. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than anything near Earth. By the end of its mission, Clipper will have received a total radiation dose equivalent to several million chest X-rays. That would kill a human instantly, but the spacecraft was built to withstand it. Critical electronics sit inside a thick-walled vault made of titanium and aluminum. Cables are specially shielded. Software can detect and correct errors caused by radiation hitting computer chips. Every component was tested to ensure it could survive. But there's another challenge nobody talks about much. The spacecraft has to work autonomously for long periods. Radio signals take nearly an hour to travel between Jupiter and Earth, so real-time control is impossible. If something goes wrong during a flyby, the spacecraft must recognize the problem and fix it before ground controllers even know there's an issue. That requires sophisticated onboard systems capable of monitoring spacecraft health, diagnosing problems, and executing contingency plans without human intervention. NASA tested these systems extensively before launch. Engineers simulated every failure mode they could imagine, then programmed responses into Clipper's software. The spacecraft knows how to save itself if it detects anomalies. It can switch to backup systems, adjust its orientation, or abort a flyby if necessary. This autonomy is essential because each flyby happens fast. At closest approach, Clipper races past Europa at several kilometers per second. The entire science observation period lasts only a few hours. Miss that window and you have to wait weeks for the next opportunity. The 49 flybys are carefully choreographed. Each one targets a different region of Europa's surface, gradually building up global coverage. Some passes focus on the leading hemisphere, the side that faces forward as Europa orbits Jupiter. Others examine the trailing hemisphere. Several flybys are dedicated to high-priority targets like Terra Regio, where carbon dioxide and salts indicate recent exchange with the subsurface ocean. The lowest altitude passes, skimming just 25 kilometers above the surface, are saved for later in the mission after engineers gain confidence in the spacecraft's performance. What happens after Clipper completes its mission in 2034? The spacecraft won't have enough fuel left to return to Earth, and leaving it in orbit around Jupiter poses a contamination risk. There's a small chance, probably very small, that microbes from Earth could have hitched a ride despite NASA's strict sterilization procedures. If Clipper eventually crashes into Europa, those microbes might contaminate the subsurface ocean. That would be an ethical disaster, potentially compromising one of the solar system's best chances for finding life. So NASA plans to deliberately crash Clipper into Jupiter or one of the other Galilean moons at the end of its mission. This is called planetary protection. The Galileo spacecraft met the same fate in 2003, plunging into Jupiter's atmosphere to prevent any possibility of contaminating Europa. Clipper will likely follow suit. The exact disposal method depends on what orbit the spacecraft is in when it runs out of fuel, but the principle remains the same. We don't contaminate worlds where life might exist. Assuming Clipper succeeds, what comes next? The mission's findings will shape future exploration strategies. If the ocean appears highly promising, with strong evidence for recent geological activity and abundant chemical nutrients, NASA and other space agencies will likely prioritize a Europa lander. Such a mission would face enormous technical challenges. Landing on Europa's icy surface is difficult enough, but the real goal would be to access the subsurface ocean. That means drilling through kilometers of ice, an engineering problem we haven't solved even on Earth in comparable environments. Antarctica's Lake Vostok sits beneath nearly 4 kilometers of ice. After decades of effort, Russian scientists finally reached it in 2012, but the drilling process was slow, difficult, and raised contamination concerns. Europa's ice is colder, harder, and possibly thicker. It exists in a vacuum with no atmosphere to moderate temperature swings. And any mission there must be completely autonomous because of the communication delay. You can't have a human geologist making decisions in real time. Some mission concepts bypass the drilling problem entirely. Instead of landing, they would fly through Europa's plumes, if those plumes actually exist and can be reliably detected. A spacecraft passing through a plume could sample ocean water directly, analyzing it for signs of life without ever touching the surface. But that approach depends on plumes being active when the spacecraft arrives. Current evidence suggests they're intermittent at best, possibly erupting only when Europa is at certain points in its orbit. Timing a mission to coincide with a plume eruption is risky. Another possibility is an ice-penetrating probe. This concept envisions a nuclear-powered device that melts its way down through the ice, trailing a communication cable behind it. Once it reaches the ocean, it could deploy sensors to measure water properties, search for organic molecules, or even look for moving organisms. This sounds like science fiction, but NASA has funded preliminary studies. The technology isn't ready yet, but it might be within a few decades. All of these future missions depend on what Clipper discovers. If the spacecraft finds that Europa's ice is thicker than expected, or that the ocean has less interaction with the surface than hoped, enthusiasm for a follow-up mission might cool. If it finds strong evidence for thin ice, active plumes, and rich chemical exchange, the case for a lander becomes compelling. That's why Clipper's reconnaissance is so crucial. It sets priorities for everything that follows. There's also the broader question of what Europa tells us about life in the universe. If we find even simple microbes in Europa's ocean, that discovery fundamentally changes our understanding of biology's prevalence. Life on Earth might not be a unique miracle but rather an inevitable consequence of liquid water and chemical energy. And if it happened twice in one solar system, it probably happened countless times across the galaxy. On the other hand, if Europa has all the right ingredients but remains lifeless, that suggests life is rarer than we thought. Either answer matters. Europa represents something profound in human exploration. For most of history, we could only wonder about other worlds. Now we build machines capable of traveling billions of kilometers to investigate them. We design instruments sensitive enough to detect molecules in ice grains. We write software that lets spacecraft think for themselves. And we do all of this driven by a single question that humans have asked since we first looked up at the stars. Are we alone? The answer might be waiting beneath Europa's ice. In April 2030, Clipper will begin its search. The spacecraft will spend 4 years mapping an alien ocean world, measuring its properties, testing its chemistry, and evaluating its potential to support life. We won't know what it finds until it looks. But either way, what we learn will reshape how we understand our place in the universe. Because if life can exist in the cold, dark waters of a moon orbiting Jupiter, then the cosmos is far stranger and more alive than we ever imagined. That's worth the journey. The spacecraft carrying humanity's best instruments for detecting alien life is already on its way. By the time you're watching this, Clipper has left Mars behind and is accelerating toward its December 2026 Earth flyby. That gravity assist will slingshot it toward Jupiter at speeds we can barely comprehend. Every second brings us closer to answers we've been seeking for generations. Think about the audacity of this mission. We built a spacecraft the size of a basketball court, packed it with instruments sensitive enough to detect a single % of bacterial material in a microscopic ice grain, wrapped its electronics in radiation shielding thick enough to survive Jupiter's particle bombardment, and launched it on a 6-year journey to a moon where temperatures would freeze your breath solid in seconds. All to answer one question: could something be alive in Europa's ocean? The weird part is we might already know the answer before Clipper arrives. Not from the spacecraft, but from the data it's designed to collect. If Europa's plumes turn out to be real and active, and if one of them happens to erupt while a ground-based telescope is watching during the 2020s, we might detect organic molecules or chemical signatures that suggest biology. That would fundamentally change Clipper's mission from reconnaissance to confirmation. But here's what makes Europa different from every other place we've explored. Mars might have had life billions of years ago. Venus might have been habitable before its atmosphere went rogue. Europa potentially has life right now, swimming in an ocean that has existed for most of solar system history. If organisms evolved there, they've had 4 billion years to adapt, diversify, and spread through a water volume twice as large as Earth's oceans. That's not a marginal environment clinging to existence. That's a world. The implications split in 2 directions depending on what Clipper finds. Discovery of life, even microbial life, would prove biology isn't unique to Earth. It would suggest that given liquid water, chemical building blocks, and energy, life emerges almost inevitably. That would make the universe less lonely but more mysterious. Because if life is common, why haven't we detected any signs of intelligence? Either technological civilizations are rare, or they don't last long, or they exist but remain invisible to our searches. None of those options is comforting. The alternative might be worse. If Europa has everything life needs but remains sterile, that suggests something is missing from our understanding. Maybe the origin of life requires conditions we haven't identified yet. Maybe the jump from chemistry to biology is so improbable that even 4 billion years in a massive ocean isn't enough time. If Europa is dead, it raises uncomfortable questions about how rare Earth's biosphere might be. Either way, Clipper's data will reshape astrobiology. The mission will establish whether Europa's ocean is habitable in practice, not just in theory. It will measure the ice thickness, map the chemistry, evaluate the energy budget, and determine how much exchange occurs between the ocean and surface. Those measurements will tell us whether a future mission could realistically access the ocean and what it might find there. The engineering challenges facing any follow-up mission are staggering. Drilling through kilometers of ice in a vacuum at -200 degrees with no human supervision isn't something we know how to do yet. But neither was landing on Mars, or flying a helicopter in its thin atmosphere, or catching a rocket booster with mechanical arms. We solve problems like this by trying, failing, learning, and trying again. Europa might require decades of development before we can touch its ocean. But the fact that we're seriously planning for it means we've crossed a threshold as a species. There's something almost absurd about the whole endeavor. Humans, creatures that evolved to survive in Earth's oxygen-rich atmosphere at comfortable temperatures, spending billions of dollars to investigate whether microbes might exist in a freezing ocean beneath 20 kilometers of ice, 390 million miles from home. We can't eat anything we find there. We can't colonize it. We can't extract resources from it. The entire mission serves pure curiosity, our need to know what's out there. That might be the most human thing we do. Every civilization that has ever existed has looked at its boundaries and wondered what lies beyond. We crossed oceans not knowing what was on the other side. We climbed mountains because they were there. We went to the moon partly to prove we could. Now we're sending robots to investigate an alien ocean because we need to know if we're alone. The question drives us in ways that practical concerns never could. The timeline stretches ahead. Clipper arrives at Jupiter in April 2030. First science operations begin shortly after. The 49 flybys will take 4 years to complete, ending in 2034. Data analysis will continue for years beyond that as scientists work through the measurements, compare them to models, and piece together a comprehensive picture of Europa's interior. We might not have definitive answers about habitability until the late 2030s. And if those answers justify a follow-up mission, that spacecraft won't launch until the 2040s at the earliest. Most people reading this will live to see the results. That's remarkable when you think about it. Previous generations could only speculate about other worlds. This generation will know whether at least one of them could support life. Your children might grow up in a world where the existence of extraterrestrial biology is an established fact, not a hypothesis. The implications of that shift are difficult to grasp. But we're not there yet. Right now, Europa remains a mystery. Its ocean stays hidden beneath ice that has never felt sunlight. Whatever exists down there, if anything, has never been observed by human eyes or instruments. Clipper will change that. In April 2030, when the spacecraft makes its first close pass, we'll begin seeing Europa as it actually is, not as we imagine it might be. Some of our assumptions will prove correct. Others won't. The moon will surprise us because nature always does. What we're witnessing is the beginning of a new phase in human exploration. For centuries, we explored Earth's surface, mapping continents and oceans. For decades, we've been exploring space, sending probes to planets and moons. Now we're starting to explore the interiors of those worlds, investigating oceans and atmospheres and geological processes happening beneath surfaces we can barely see. Europa is the first target of this deeper investigation, but it won't be the last. Saturn's moon Enceladus also has a subsurface ocean and active plumes. So does Saturn's largest moon Titan, though its ocean is probably too cold and too far beneath the surface to access easily. Other candidates exist throughout the outer solar system. The search for life is expanding from a question about Earth's uniqueness to a systematic survey of potentially habitable environments across multiple worlds. This is the future of astrobiology, not waiting for signals from distant civilizations, but investigating the places where life might exist right now in our cosmic neighborhood. Europa leads that investigation because we can actually get there with current technology and because the evidence for its ocean is so strong. But it's part of a larger project that will occupy humanity for generations. When Clipper completes its mission in 2034, it will have generated more data about Europa than all previous missions combined. That data will feed into models, simulations, and predictions about what the ocean contains. It will guide the design of future missions. It will answer old questions and raise new ones. And somewhere in those terabytes of measurements might be a signature that changes everything, a chemical anomaly that can't be explained by geology alone, a pattern that suggests something other than sterile water beneath the ice. Or maybe not. Maybe Europa will turn out to be a magnificent but lifeless ocean, a reminder that water and chemistry alone aren't sufficient. We'll learn something profound either way. That's the nature of genuine exploration. You don't know what you'll find until you look, and the act of looking transforms your understanding regardless of the outcome. Europa forces us to confront possibilities we can barely articulate, questions about the nature of life and its distribution in a universe that we're only beginning to learn how to ask properly. The spacecraft flying toward Jupiter right now carries more than instruments and computers. It carries our best attempt to answer whether Earth's biology is an isolated accident or part of a broader pattern. In 4 years, when Clipper begins its flybys, we'll start getting answers. Those answers will shape how we think about our place in the universe for the rest of human history. Because knowing whether we're alone changes everything about how we understand ourselves and our future. Europa might tell us that story. We just have to wait for the spacecraft to arrive and start reading what's written in the ice.